Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 1 on hypothesis testing. So in this lecture, we'll talk about hypothesis testing. We'll go over some general rules for hypothesis tests, mostly in the context of one-sided hypothesis tests. We'll cover briefly two-sided hypothesis tests. We show that there's a duality and a connection between hypothesis test and confidence intervals, and then we'll briefly cover p-values. Hypothesis testing is concerned with making decisions using data. A null hypothesis is specified that represents the status quo. Usually this is labeled H0. The null hypothesis is assumed true, and statistical evidence is required to reject it in favor of a research or alternative hypothesis. So one might think of this in terms of a court of law, where a person is presumed innocent until evidence is presented to convict them. In this case, the null hypothesis is presumed true, and then evidence is required to, in this case, convict it or reject it. So let's go through an example. A respiratory disturbance index of more than 30 events per hour is considered evidence of severe sleep disordered breathing. Here, the respiratory disturbance index is usually abbreviated RDI. 30 events per hour is quite a bit. What this means is that a person's upper airway either collapses or partially collapses while they're sleeping 30 times in an hour, and on average 30 times in an hour over the night of sleeping, which is quite a bit because they're being deprived of oxygen every time this happens. And then they wake up a little bit and then they fall back asleep. This is a disease called sleep disordered breathing. Suppose that, and let's assume 30 events per hour is some sort of cutoff for severe sleep disorder breathing. Now, actually, just in case you're interested in this, the cutoff for diagnosed sleep disorder breathing is far lower. I picked 30 for whatever the reason here, but so keep that in mind. So imagine if you had, let's say, overweight subjects, and you were interested in whether these overweight subjects were drawn from a population that has an RDI, a population RDI greater than 30. So your null hypothesis is that the RDI, average RDI for this population is 30 versus the alternative that the RDI is greater than 30. Now notice this mu that we're talking about here refers to the population mean, not the sample mean. Here we're assuming that the sample mean was 32 events per hour. So we want to test whether, with respect to the model of IID sampling from this population, and we're going to make Gaussian assumptions, and with respect to Gaussian assumptions about the respiratory disturbance index, is there enough evidence in the fact that the mean was 32 events per hour and the standard deviation was 10 events per hour to conclude that the population mean is in fact bigger than 30? That's what we'd like to test. The alternative hypothesis that we specified on the previous page was that mu was particularly greater than 30, but there's different versions of the hypothesis tests for our purposes where we could test less than, greater than, or not equal to. And there's maybe some philosophical discussion about whether or not testing whether the mu is exactly 30 versus not equal to 30 is a sensible thing to do. And we'll talk about that a little bit later. But for the time being, we'll think that the alternative is going to come in 3 varieties: greater than, less than, or not equal to. And then, there's basically, we could create this 2x2 table of the kinds of decisions that we could make. So we could, if the truth was in fact the null hypothesis, we could decide the null hypothesis, and that would, in that case, we'd correctly accept the null. If the truth was the null hypothesis and we decide the alternative hypothesis, then we will have made what is called a type 1 error. If the falsely rejecting the null hypothesis. If the truth is the alternative hypothesis and we decide where we fail to reject the null hypothesis, then we've made a so-called type 2 error. And then if the truth is the alternative and we reject the null hypothesis, then we will have correctly rejected the null. So that encapsulates the decision space for hypothesis testing. So let's revisit this court of law example again. So in general, in most courts, the null hypothesis is that the defendant is innocent. And then we're going to require evidence to reject the null hypothesis or convict the person. If we require very little evidence, then what happens? Well, we increase the percentage of innocent people convicted, which in this case would be type 1 errors. However, we would also increase the percentage of guilty people convicted. So this would be correctly rejecting the null. On the other hand, if the court requires a lot of evidence to convict someone, then we increase the percentage of innocent people let free. In this case, that's correctly accepting the null. But then we would also increase the percentage of guilty people set free. This case would be type 2 error. So this also goes to show, basically in all decision spaces, not just in statistical decision spaces, but certainly the same thing happens in policies for law, is that the type 1 and type 2 errors are associated. As you increase one, you decrease another, and vice versa. And what we'll see is we'll kind of set up our statistical decision making in a particular way to minimize the chance of type 1 errors. And as doing so, then we kind of hamstrung ourselves a lot about what what kind of type 2 errors we can make. And so that'll cloud, I think, a lot of our kind of framework and rubric that we talk about for hypothesis testing, is that we're going to very specifically control type 1 errors. And then we'll talk maybe later on about how we can control type 2 errors and try and minimize them. Now obviously, to control type 2 errors while also keeping type 1 errors low, you have to do something. You have to get better evidence, not just more or less, but better evidence, and we'll talk about that. So let's talk a little bit about what's the kind of standard way to implement hypothesis testing, and we'll go back to our example with the respiratory disturbance index. And the kind of obvious strategy, we want to test whether or not the population mean is bigger than 30. The obvious strategy would be to say, well, is the sample mean larger than some constant, where we pick the constant in some reasonable way? Well, the traditional way to do this now is to pick the constant so that the probability of a type 1 error is low. And there's a standard benchmark that occurs very commonly, which is 5%. But the idea is that the type 1 error rate is controlled so that the probability of making a type 1 error is low. And there's a couple of reasons why people do this. One is maybe there's some logic to it, right? That we want to, the null hypothesis is our status quo hypothesis, so we want to make sure that we don't reject that hypothesis idly, and so if it's true. And so maybe there's some scientific sense of conservatism, scientific conservatism built into it. It's also, I think, rather practical in terms of the mathematics, in that the fact that under the null hypothesis, the mean is sharply specified at mu equals 30, that makes the math a little easier as well. And it turns out you can also say whether that mu is not just strictly equal to 30, but less than or equal to 30. You wind up with the same test. But the fact that the null is this sharp null hypothesis also helps with the mathematics a little bit, which maybe isn't the best reason to do it, but still, nonetheless, it's a good reason, right? It's a part of the reason why I think people do it. But maybe the main reason is this idea that we want to control for type 1 errors and have that probability be low. So the type 1 error rate, we usually assign the letter alpha, the Greek letter alpha, and that's the probability of a type 1 error. So the probability of rejecting the null hypothesis when in fact is true. And we want the type 1 error rate to be 5%. So what we're going to do is we're going to choose this constant C in such a way that it factors in the uncertainty associated with the sample mean and in such a way that our type 1 error rate, probability of a type 1 error rate, is 5%. So let's go ahead and do that. Okay, so we want this value C here to be chosen so that the probability of getting a sample mean larger than it, given that the population mean is actually 30, to be 5%. That would be the probability of a type 1 error if we're going to observe the rule that we're going to reject for an x bar larger than this constant. Okay? Well, so either by the central limit theorem or supposing our data is Gaussian, we can normalize x bar so that it's zero mean unit variance under the null. Okay, so in this case we can subtract off 30 from both sides of this equation because that's the actual population mean. And then we can divide by the standard error of the mean, which in this case is 10 over square root 100. 10 because that's, let's assume, known standard deviation of the population, and then square root 100 because 100 observations, the mean is comprised of 100 observations. So this quantity right here, x bar minus 30 over 10 divided by square root 100, that is that's a standard normal now, or it limits to a standard normal if the data are IID. And so we can just take this whole quantity here and replace it with a z. Okay, and on the right hand side we have c minus 30. And we want to calculate this. Remember, the reason that this quantity is a z random variable is because we're calculating this probability under the condition that the null hypothesis is true, so mu equal 30. You'll see here this point that I was making earlier, that when the null is true, we have a sharply specified parameter, helps, right? Because we can actually plug in exactly 30 here. Okay, so we want 5% to be equal to the probability a z random variable is bigger than c minus 30. So we could just set c minus 30, well, I put divided by 1 here just to remind ourselves this standard error in the denominator. We want it to be set to a value that has the probability of a z being larger than it, 5%. Well, we know what that value is. It's the 95th percentile of the standard normal, which is 1.645. We can solve for c, and c is 31.645. Since our mean is 32 in this case, we would reject the null hypothesis. Okay, very briefly, I'd like to just show how to get this normal quantile in R. Here I have a cutout of RStudio, and I'm just typing in the appropriate command. Okay, so very briefly, let's just illustrate with a picture what that calculation is giving for us. So here I have my RStudio window, just to remind ourselves the 95th percentile of the normal. It's about 1.645. We do that with the qnorm function. So let's visualize it. Let's create some grid points to plot. And so this is just sequence from -3 to +3.2, and that covers most of the normal distribution. The y value here is evaluated at the normal density of the x values. So let's plot that. So we see a plot of the bell-shaped curve from -3 to +3 about. Let me define the sequence that we want to shade in that represents 5% of this. I'll shade it in with a polygon. There it is now shaded in salmon colored. And then just remind us that's 5% of the curve. And then the number that represents that 5% is 1.645. Okay, so we went through some extra steps there. In general, we don't convert our constant that we're interested in back to the original scale, right? We just take the standardized mean and compare it to standard normal quantiles. So in this example, remember 32 was our empirical mean, 30 is the mean under the null hypothesis, and then the standard error of the mean in this case was 10 divided by square root 100. So the mean expressed in standard error units from the hypothesized mean works out to be 2. 32 minus 30 divided by the standard error, 2. So our mean is 2 standard error units away from the hypothesized mean. Then we would compare that to the 95th percentile from the standard normal distribution, which is 1.645. So we would directly compare 2 and 1.645. So that's just a quicker way to do it. So we can codify these rules for a normal test for a single mean into a couple of simple rules. So let's just call this the z-test because we're talking about testing a single mean. We're either assuming that our data, we're willing to assume that our data is Gaussian, or that our data, or that the central limit theorem is a good enough approximation to apply. Suppose we want to test the null hypothesis that mu equals mu naught, h naught is that mu equals mu naught, versus one of the three alternatives, the mu being less than mu naught, mu being greater than mu naught, and the middle one here, mu not equal to mu naught, and that one we'll have to talk a little bit about. In all three cases, we're going to say, well, we're going to reject for h1, say, if our sample mean is small enough, right, and if it's enough below mu naught. We're going to reject in the case of h3 if our sample mean is enough above mu naught. And then in the second case, we're going to just reject if our sample mean is enough different from mu naught, either too large or too small. And again, just like before, the logical way to do this is to express the mean in standard error units, in standardized units. So when we calculate our test statistic, it's x bar minus the hypothesized mean under the null value, mu naught, divided by the standard error, s over square root n. That then is a z-score. It is a sample mean expressed in standard error units. So if we get, for example, a 3, we would know that the sample mean is 3 standard deviations above the hypothesized mean, right? And so we observed a sample mean that is 3 standard errors above the hypothesized mean, which would be unlikely, right? So that maybe casts some doubt on the hypothesized mean. If we observe a sample mean that is, say, 4 standard deviations below the hypothesized mean, again, that would be evidence in favor of H1. If it was 4 standard deviations above the hypothesized mean, that would be evidence in favor of H3. And so we can actually force, if we want an alpha level error rate, so in our previous example, alpha was 5%. So alpha, again, remember, is the probability of a type 1 error, falsely rejecting the null hypothesis when in fact it is true. Then under H1, we would reject if our test statistic was less than negative z1 minus alpha. So in this case, if alpha is 0.05, then we would look up the 95th percentile and then take the negative of it. We could equivalently look up the 5th percentile because the 5th percentile is the negative of the 95th percentile, but I want to just say use the same quantile every time. So in that case, it would be negative 1.645, okay? In H3, then we're going to do exactly what we did in our example. We would compare it to the positive, the positive upper quantile, z1 minus alpha, so the 95th percentile of our alpha, if the error rate we want to control for is 5%. And then for the second case, H2, we will reject if our test statistic is either too large, bigger than z1 minus alpha over 2, or too small, smaller than z1 minus alpha over 2. And the reason we divide alpha by 2 is because we remember we want a 5%, well, alpha percent chance of rejecting the null hypothesis falsely. So if the null hypothesis is true, we want only a 5 alpha percent chance, 100 times alpha percent chance of rejecting the null hypothesis. So the way that we're going to do this now is we're going to say, okay, well, we'll divide that probability into half of it being accidentally rejecting too large and the other half being accidentally rejecting too small. And that seems like a pretty sensible rule to do. So, and the execution of that rule is just to say, well, take my test statistic. If it's negative I throw out the negative sign. If it's positive, I just leave it alone. And then I compare it to the upper quantile from the normal distribution, but instead of looking at the 5% error rate, I look at the 2.5% error rate. If I want a 10% type 1 error rate, then I would look at a 5%, the 95th percentile, and so on. Okay? So let me just describe briefly more this two-tailed test idea. So just to let you know that, that alpha over 2 in this case, if alpha is 0.05, then 1 minus 0.05 divided by 2, that works out to be 0.975, and the 0.975th quantile of the normal distribution works out to be about 1.96. And what we're doing, let's let me get some x and y values and then plot the standard normal again, which you can see over there. And then, so what we have is we have a test statistic that we calculate, and then we're going to reject if it's too large or too small. So take, for example, what we're going to do is take 1.96, and that puts 2.5% in the upper tail, and then we're going to take negative 1.96, and that puts 2.5% in the lower tail. Of course, then that puts 95% in the middle. So we're going to reject if our test statistic is above positive 1.96, which has a 2.5% chance under the null hypothesis, or if our test statistic is below negative 1.96, which has a 2.5% chance under the null hypothesis. So the union of those two events yields a 5% chance under the null hypothesis. And rejecting whether something is bigger than positive 1.6 is the same thing as rejecting if the absolute value is bigger than 1.96. So in the way that we're executing hypothesis testing, we've forced the type 1 error rate to be small. It's usually 5% or so. So if we reject the null hypothesis, either our model is wrong or several other things maybe could have gone wrong, or there's a low probability that we've made an error. On the other hand, we have not fixed anything to do with the type 2 error rate, which is usually called beta. So therefore, we tend to say fail to reject H naught rather than accepting H naught. The kind of, to give you kind of a classical example of this is, imagine if you have a very small sample size and you want to test some scientific hypothesis and you fail to reject the null hypothesis. Well, you've controlled, regardless of your sample size, you've controlled the type 1 error rate so that there's only a 5% chance that you will have rejected the null incorrectly. But if the alternative is true, it's possible that your small sample size leads to variability in the mean, right? Because remember, the standard error of the mean is sigma divided by square root n. So if n is small, our variability of the mean is going to be larger. So if your sample size is small and you fail to reject H naught, it's not fair to say that you should conclude H naught. If you only have, say, a sample of size 3, then maybe you didn't have a good chance of rejecting the null hypothesis anyway because you didn't collect enough data to really evaluate it. So at any rate, that's a bit of nomenclature. So that's why there's a tendency in basically every statistics textbook that teaches hypothesis testing to say fail to reject H naught rather than accept H naught. If you want to say that you want to accept H naught, there's an implicit notion that the type 2 error rate is small, which usually in most problems less is known about the type 2 error rate. And we'll talk. This goes to the subject of things like power, which we'll talk about later on in study design. One of the ways to try and combat this problem, issues like this, is prior to conducting the study, to design it in such a way that you will have a high probability of rejecting the null hypothesis if in fact the alternative is true. And one of the things you have under your control for doing that is to have a large sample size. So that's one point. And so anyway, so the tendency is to say fail to reject H naught rather than than rejecting H naught. You know, I think a classic phrase too that people always say is absence of evidence is not evidence of absence is another way to put that. That's one point. The other point I'm making on this slide is that statistical significance is not the same thing as scientific significance in the context of hypothesis testing. So the most common argument in favor of this point is, we have these, for most of our hypothesis testing procedures, we have very, sharply specified nulls. H naught is that mu is exactly 5 or something like that, depending on the problem. And so it's possible, let's say you have an enormous sample size, to get a sample mean that's 5.01 with an incredibly small standard error because you have an enormous sample size, and still reject the null hypothesis, even though 5.01 isn't in any scientific sense different from 5. And so that's a point that's often made, is that just because you reject the null hypothesis in the terms of executing a statistical test, that doesn't mean that the difference that you've detected is in fact meaningful. I read an argument at one point by a person saying that in some instances, for example, when you have randomized comparative trials, that sharp null hypotheses are still meaningful, and even small deviations are important. But these are kind of subtle issues. I think that the main basic issue that's sort of at least generally understood is that it's not always the case that statistical significance and scientific significance are the same thing. So I would like you to at least be aware of that, and you can read more about it. But and then in the previous slide, we said, well, we'll reject if our test statistic is above this value. In the case where we're testing H1, we'll reject if it's either if its absolute value is above this particular value in the case of H2, and then we'll reject if it's below this value in the case of H3. That was our rules that we came up in the previous slide. So in H1, the upper normal quantile and above, that's called the rejection region. And in the case of H2, the upper quantile and above, or the negative quantile and below, in other words, the absolute value being above a large value, is the rejection region in that case. And in the third case, the normal quantile and below is the rejection region. So just the collection of values of test statistics for which you reject the null hypothesis is called the rejection region. Just a bit of nomenclature there. So the z-test that we're talking about requires the assumptions of the CLT and for n to be large enough for it to be applicable. If n is small, then you can just do Gossett student's t-test. In the same way, you're just replacing the normal quantile with the student's t quantile. The probability of rejecting the null hypothesis when it's false is called power. Remember, we set the type 1 error rate, which is the probability of rejecting the null hypothesis when it's true. So we force the type 1 error rate to be small. The type 2 error rate, which is the probability of failing to reject the null hypothesis when in fact the null hypothesis is false, is called a type 2 error rate. Power is 1 minus that. It's the probability of rejecting the null hypothesis when it is false. And so power is a good thing. You want to reject the null hypothesis when it's false. And unfortunately, power is not typically under our control after the experiment has been conducted. So the way that people combat this is, prior to conducting this study, they do a power calculation where they vary the sample size, or if it's simple enough, just calculate the sample size needed to obtain a certain level of power, using guesses for what they think the standard error and hypothesized significant effect would be. And that's what we'll talk about next lecture. Okay, so let's actually go through the t calculation for this example. Suppose that n is 16 rather than 100 as we were considering before, so we have to, so we're going to use a t-test. Then look at this equation right here. we want 5% to be the probability that x bar minus 30, the value under the null hypothesis, divided by the estimated standard error now, s over square root 16, we want to be the probability that that quantity is larger than the t quantile now instead of a z quantile. Again, the 1 minus alpha quantile with 15 degrees of freedom. So our test statistic now is the standardized observed mean, so 32 our observed mean, minus the hypothesized value, divided by the standard error, 10 over square root 16. Square root 16 then moves up in the numerator. And that works out to be 0.8. And the t critical value is 1.75. And so now we fail to reject, and it shouldn't be surprising, right? We're changing what used to be multiplication by a square root 100 to now square root 16, and so the test statistic went down substantially while the quantile that we're comparing it to went up, because remember the t is a heavier tailed distribution than the normal, so it shouldn't be surprising that we now fail to reject. Okay, so in the previous slide we did the one-sided test. Let's now do the two-sided test, and we're going to move through these things quickly because I'm hoping that at this point in the class that you'll be getting used to these kinds of calculations. So we want to now test whether mu is different from 30 as the alternative, and maybe you can say that doesn't make a lot of sense in this case because the way I framed the problem was that we're looking at a particularly susceptible population to having a high RDI, so why don't we just test mu greater than 30? And well, let's just, for the sake of argument, just to show you the calculations do different from 30, but also I would say that in many journals and avenues of scientific inquiry, they demand two-sided test, even if the one-sided test is the natural direction to consider. So let's do a two-sided test. So what we want is to test whether or not our observed mean, x bar, is significantly different from our null hypothesized value for the population mean, 30. So that would be if it's significantly larger than 30, or significantly smaller than 30. So we could just say, well, maybe we will look at the absolute value x bar minus 30, which would look at whether it's too small below 30 or too large above 30. And then, of course, because we want to standardize our statistics, we're going to divide by the standard error of the mean, s over square root 16, and we know that x bar minus 30 over s over square root 16, if the data are IID Gaussian, that follows a t-distribution. And so if we want alpha, the type 1 error rate, to be specified so that the probability that this test statistic is too large or too small, the probability of that occurrence is exactly alpha, well, what we could then pick is the t quantile, t 1 minus alpha over 2, and 15 degrees of freedom. And what this does is this says this random t statistic, the probability of it being larger than this quantile is alpha over 2 probability. The positive part of the statistic, the probability of it being larger than the t1 minus alpha over 2 quantile gives alpha over 2 probability. The probability that this test statistic on the negative end is less than the t alpha over 2 quantile with 15 degrees of freedom, which is a negative value, is also alpha over 2. So we put alpha over 2 in the lower tail, alpha over 2 in the upper tail, and that yields a total probability of alpha. And in the next slide, I'll describe that a little bit. And this calculation is, of course, all done under the null hypothesis that mu equals 30. So we'll reject if our test statistic, which in this case, x bar minus 30 over s over square root 16 is 0.8. So when we take the absolute value, it remains 0.8. We're going to reject if it's either too large or too small. But again, remember the critical value is calculated now using alpha over 2 rather than alpha, because we want alpha over 2 probability of rejecting for too large and an alpha over 2 probability for rejecting if the test statistic is too small negative. So in this case, the critical value is 2.13, and notice, of course, that's a larger value than when we just used alpha because we're going further out into the tail, so it's harder to reject for the two-sided test than it is for the one-sided test. So since we rejected for the one-sided test, we're of course going to reject for the two-sided test. Okay, let's just briefly again show you the two-sided calculation and where the alpha over 2 comes from. So here I'm setting a sequence of x values from -4 to +4. I'm evaluating the t density with 15 degrees of freedom at those points, and then let me plot, and there's my t distribution. Okay, now I'm going to shade in that area right there. That's 2.5%. Let's say my type 1 error rate that I want is 5%, and that value right there is 2.13. So for the t distribution, the 97.5th quantile is 2.13 when you have 15 degrees of freedom. And let's do the same thing for the lower quantile. Sorry about that. There we go. That's better. And that's 2.5% right there, and that's negative 2.13, and then that's 95%. So what we're saying is we calculate our normalized test statistic, x bar minus 30 over s over square root 16, and the probability that the absolute value of that statistic is bigger than 2.13, or in other words, the probability that that statistic is too large positive above 2.13 is 2.5%, or too small negative is too small negative in the form of being less than negative 2.13 is 2.5%. So that the probability that its absolute value is bigger than 2.13 is 5%, including the upper tail 2.5% and the lower tail 2.5%, so that the probability the test statistic lies in the rejection region is 5%. Okay, so now is a good time to talk about confidence intervals and their connection to hypothesis testing, since we've talked about hypothesis testing and two-sided hypothesis tests. So now consider testing h0 mu equal to some value versus ha mu different from some value, like we just discussed in the previous slide with respect to the respiratory disturbance index. And then take the set of all possible values for which you fail to reject h0. Now think about this set. These are in some level the values of mu that are supportable as null hypotheses. So they're reasonable values of mu. And so it doesn't make so it isn't that big of a stretch to acknowledge that or to guess that this will form a confidence interval for mu. What's interesting is that it forms exactly a 1 minus alpha % confidence interval for mu. So if you have a 5% type 1 error rate for the set of tests, then you have a 95% confidence interval, which is nice. And then the same works in reverse, which is probably even the more useful direction for us. If a 95% interval, say, contains mu naught, then we fail to reject mu naught, right? Which makes sense, right? The value of mu naught was supported as a potential value when we created the confidence interval, so it would make sense that we'd elect to fail to reject h naught than to conclude that mu was different from mu naught. And in the next slide we'll go through the argument. Okay, let's just briefly go through this argument. So consider that we do not reject h naught for a two-sided test of mu equal to mu naught versus mu different from mu naught if our test statistic, absolute value x bar minus mu naught divided by the standard error s over square root n, if that's less than the t quantile evaluated at at n minus 1 degrees of freedom and 1 minus alpha over 2 quantile. So you remember, when we reject if it's bigger than that particular t quantile. Okay, so we can just The s over square root n is positive, so we can just move it over to the right-hand side, and we haven't done anything to the inequality. And this inequality here, absolute value x bar minus mu naught less than or equal to this t quantile times s over square root n, that's exactly equivalent to the statement below, that mu naught lies in between x bar minus t times the standard error and x bar plus t times the standard error. And so that is exactly the same as saying mu naught lies inside the confidence interval. So this is equivalent to saying if mu naught lies inside the confidence interval, then we would have failed to reject h naught, and then you can obviously reverse this argument to get the other direction. So that proves the statements we've made from the previous slide, and it shows that this sort of inherent duality between confidence intervals and two-sided hypothesis test. And this has several uses. First of all, it tells you if you create, say, a 95% confidence interval, it conveys a little bit more information than the result of a hypothesis test, because A, you can do the hypothesis test, but B, it also gives you a sense of what values of mu are sort of well supported. And this helps to combat things like the difference between scientific significance and statistical significance, where statistical significance, if we have a giant sample size, and our x bar is, from our respiratory disturbance index example, if our x bar is 30.01, well, that isn't very different from 30, and it may not be scientifically meaningful. The confidence interval would both show us what values of mu, what range of values of mu are estimated, and that in fact our interval is quite close to 30, even if 30 isn't right in it. Plus, we can actually mechanically perform the hypothesis test. So that's why I think in general people have a preference if you could report a confidence interval rather than simply the result of a hypothesis test. Okay, let's introduce the concept of p-values. So when we had a sample size 100 and we were doing the z-test, we rejected the one-sided hypothesis test when alpha was 0.05. Would we have rejected if alpha was 1%, or how about 0.1%? Okay. Now, of course, at some point we're going to get to the point where the z quantile is larger than our observed test statistic, and that will correspond to a specific alpha level, and that value, the smallest alpha for which you still reject a null hypothesis, is called the attained. That's exactly called the attained significance level, and this is equivalent, but philosophically, I guess, a little bit different from an entity called the p-value. The p-value, on the other hand, which again is the same number, but conceptually is a different thing in my opinion. The p-value is the probability under the null hypothesis of obtaining evidence as or more extreme than would be observed by chance alone. Where here chance is governed by the null distribution, the null probability distribution. So here's p-values were invented by the great statistician Fisher. And here's the logic. So the attained significance level has a kind of an easy logic there to it, right? It would just say, why don't we just report the smallest significance level for which you fail to reject? Then if I give someone that number, then they'll know whatever their alpha level is, whether or not they reject. If their alpha happens to be bigger than the smallest significant level, then they would reject. If it's smaller than the smallest significance level, then they would fail to reject. So the thinking about the p-value as an attained significance level, at that level it's merely just a convenient thing to report, because regardless of a person's alpha level, then they can compare it to the p-value and tell you whether or not they reject. The p-value, on the other hand, has a more interesting interpretation, because the idea is that it's at some level people claim that it's a measure of evidence. So here's the logic. If the p-value is small, then either the null hypothesis is true, and we've observed something that's very unlikely given that the null hypothesis is true, or that the null hypothesis is false. And that's why Fisher introduced the p-value. The p-value he thought was a convenient, calibrated entity, because it was a probability, that would tell you sort of in a sense whether or not getting a test statistic as or more extreme than you observed was rare under the null hypothesis. And if it was rare, then that casts some doubt on the veracity of the null hypothesis. And I think this use of the p-value as a measure of evidence is a little bit more controversial of an entity. The attained significance level, which is again the same exact number, it's just a different interpretation. The attained significance level is maybe a less controversial entity. It's merely just telling you it's the mere mathematical answer to the question, what's the smallest alpha level for which I would have rejected the null hypothesis? Okay, so let's calculate our p-value from our example. Let's do it for our t-statistic. So we're thinking that the sample size is 16. Our test statistic was 0.8. What's the probability of getting a t-statistic as or larger than 0.8? Well, this is PT, stands for t probability, 0.8, 15 degrees of freedom, and this lower tail equals false just means that we want above 0.8, not below 0.8. So this works out to be 22%. Of course, it's larger than, say, 5%, which we knew because we failed to reject the null hypothesis. If the p-value is larger than alpha, you're going to fail to reject. If it's smaller than alpha, you will reject. Okay, so the probability of seeing evidence as or more extreme than actually obtained, that probability calculated under the null hypothesis is 22%. Okay, let's just show the computing of the p-value in this case. So our test statistic, x bar minus 30 over s over square root 16, worked out to be 0.8. So the probability, let's just see, the probability of being 0.8 or larger from the t-distribution with 15 degrees of freedom works out to be 22%. So here, let's draw a picture. So there's our t-distribution. And then, so right here is where our test statistic is, 0.8. The probability of lying above it from the t-distribution is 22%. And so you can see this area right here. Obviously, 0.8 then is below the fifth upper quantile, which would be up here somewhere. And so we would know that we would reject, but we also know that because 22% is larger than 5%, just given our p-value, that we would fail to reject. Okay, let's do some notes. So by reporting a p-value, the reader or whomever can perform the hypothesis test at whatever alpha level he or she chooses to. That's because the p-value is mathematically equivalent to the attained significance level. So if the p-value is less than alpha, you reject the null hypothesis. If the p-value is bigger than alpha, you fail to reject. For two-sided hypothesis test, my recommended p-value calculation is just going to be to double the smaller of the two one-sided hypothesis test p-values. That's an easy procedure, and it's generally right. So don't just report p-values, by the way. Just give confidence intervals. And it's a little hard when the problem is higher than one dimensional. But if it's a one-dimensional problem, then you have no excuse. Give a confidence interval, not just a p-value. Okay, some final thoughts about the p-values. So, one of the problems with p-values is they only consider significance, unlike confidence intervals, which p-values, it's difficult to distinguish practical significance from statistical significance. It's by itself, it's just a little bit too crude of a summary of your data. It's a tremendously useful quantity, but it needs to be used with care. There's quite a bit of work on the philosophy of whether whether p-values measure evidence, and the argument against the p-value is that absolute measures of the rareness of an event are not necessarily good measures of evidence for or against hypothesis, and that's the intrinsic philosophy behind the p-value, is that it's a measure of evidence by virtue of being a measure of the rareness of the null hypothesis in a certain sense. And certainly p-values have become somewhat abusively used and frequently misinterpreted. And that's one of the main issues, is that the actual interpretation of a p-value is kind of hard. It's the probability of obtaining a test statistic as or more extreme in favor of the alternative where the calculation is done under the null hypothesis. That's the actual interpretation of a p-value. And then people try to interpret p-values in all sorts of different ways because that interpretation sounds a little complicated, but that is the actual interpretation. So the p-value is a confusing quantity. Sort of get used to just regurgitating the whole definition correctly so that you don't take shortcuts and give incorrect definitions, because, let me also say, people love to complain about p-values as well. So you should get your p-value interpretations correct. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 2 on the subject of power. So in this lecture, we're going to talk about power, calculating power, power specifically for the t-test, and because the t-test involves maybe a little bit of math that we don't want to get into, we'll talk about how you can do it using Monte Carlo, which is a standard way to estimate power. So, as its name would suggest, power is a good thing. You want more power. So power is the probability of rejecting the null hypothesis when in fact it's false. So the opposite of power, 1 minus power, is the type 2 error rate. And that's the probability of failing to reject a null hypothesis when it's false. And we usually label that as beta. So consider our previous example involving the respiratory disturbance index. Here we were testing whether or not mu was 30 versus the alternative that mu is specifically greater than 30. Then the power is exactly the probability that our test statistic lies in the rejection region. Recall that we calculated the rejection region was if the normalized mean, x bar minus 30, the value under the null hypothesis, divided by the standard error of the mean, s over square root n, if that normalized mean was greater than a t quantile, specifically t1 minus alpha n minus 1 quantile, where alpha is the desired type 1 error rate. So if the statistic is larger than that t quantile, then we reject the null hypothesis. So then the power is the probability that we reject the null hypothesis. In other words, the probability that our test statistic is larger than that quantile. But instead of calculated under the null hypothesis that mu is 30, calculated under the assumption of the alternative hypothesis that mu is specifically greater than 30. So in the event that mu a approaches 30, then this probability approaches alpha, the type 1 error rate. But on the other hand, if it's not specifically 30, if it's actually a power calculation so that mu is not 30, then this calculation depends on the specific value of mu a that we plug in. So to do a power calculation, you actually have to know the value under the alternative that you want to plug in, and then you can perform the calculation. So let's actually go through this calculation. So remember, beta is the type 2 error rate, so 1 minus beta is the power. And let's assume n is large so that we can just do standard normal calculations rather than t calculations. Okay, so here notice our s is replaced by sigma, the true value of the population standard deviation. So here we have our test statistic, which is x bar minus 30 over sigma over square root n, which under the null hypothesis that mu equals 30 is a z statistic. So our rejection region, since we're rejecting whether or not mu is larger than 30, will be as if this mean is large. Hence, if this normalized mean is larger than a standard normal quantile, If we want an alpha level error rate, we grab the Z1 minus alpha level standard normal quantile. So for example, if we wanted a 5% error rate, we would pick the 1.645, the number 1.645, which is the 95th percentile of the standard normal distribution. Then 1 minus beta, right, is the probability that we reject. The probability that the statistic is larger than the cutoff, the critical value, under the alternative hypothesis, given that mu is in fact mu A. So now this statistic is no longer a z statistic because we're considering the alternative hypothesis, not the null hypothesis. It's a normal, of course. If the data is Gaussian distributed, then this is of course still normally distributed, just with a different mean. And if n is large and we're applying the central limit theorem, then this is again not converging to a z statistic. So what we need to do is convert it to a z statistic. So the easiest thing to do would be to maybe add and subtract the mean under the alternative, and we do that in this line here. Then in the next line, we simply take the correctly normalized mean, x bar minus the mu under the alternative, which is what we're assuming to be true, divided by the standard error, sigma over square root n. And now we're calculating the probability that that is larger than z1 minus alpha minus this quantity over here, mu a minus 30 over sigma over square root n. Now again, this standardized mean is a z statistic because we're doing the calculation under the alternative, so we want the probability z is larger than this quantity over here, which we can perform this calculation because we know z1 minus alpha. We're assuming we know sigma. We of course know n. We know 30, of course. So mu a is the only thing we have to plug in, and that is the fact about power calculations, is that you have to plug in the particular value of the mean that you're interested in. Okay, so let's actually do a specific version of this calculation, and suppose that we want to calculate the power of detecting an increase in the mean RDI of at least 2 events per hour above our null hypothesis of 30. So we want to calculate what's the power if the alternative mean, the population mean respiratory disturbance index is 32, when our null hypothesis is that it's 30, and we'd like to calculate the power of detecting that. Now again, under the assumption where the type 1 error rate is 5%. So again, assume normality, and that the sample in question will have a standard deviation of 4 events per hour. What would be the power if we took a sample of size 16? Okay, so here our z 1 minus alpha is 1.645. Our mu a minus 30 over 4 over square root 16 works out to be 2. So we want the probability that a standard normal is bigger than 1.645 minus 2, which is the probability the standard normal is bigger than negative 0.355, which is 64%. So under these set of assumptions, the probability of detecting an alternative of 2 events above the hypothesized value per hour is 64%. And this is of course a bound if the power only gets larger as the alternative goes away from 30 events per hour. This makes sense, of course, right? Because the bigger the difference is from the null, the easier it should be to detect, right? If the true population mean is 100 events per hour, we shouldn't, we should have a high probability of detecting that, a higher probability of detecting that than if the true mean is 30.01 events per hour, which seems like it would be very hard to detect relative to 30 because it's such a small change. So this power, 64%, is a bound for all values above 32. So instead of calculating power given a sample size, a variance, and a value of the alternative, we could flip the question around and say, imagine we have a power that we'd like to achieve for a particular value of the alternative. What sample size would we need to achieve it? And this is called a sample size calculation. In both of these calculations are typically done at the phase of designing a study. So when you actually want to figure out how many subjects to have in a study, or whether or not to conduct a study if your number of subjects is constrained. So here we do this calculation exactly, where we calculate the sample size we would need to get 80% power. 80% is a very common benchmark standard in the field of science. You can argue whether or not 80% is enough power, but it is somewhat of a benchmark in say, for example, clinical trials. I would admit, though, most clinical trials do two-sided tests, and here we're calculating power for a one-sided test. So here we want 0.8 to be the probability that our test statistic, which appropriately normalized is a z-statistic under the alternative, is greater than this, the standard normal quantile, z1 minus alpha. But remember, when we converted our test statistic so that it was normalized appropriately under the alternative, we have this extra term mu a minus 30 over the standard error, sigma over square root n. And this calculation is then, of course, calculated under the alternative, which is when when we normalize with respect to mu a, and you get this extra term out here. So if we want this probability to be 80%, then we know this entity here on the right, z1 minus alpha minus mu a minus 30 over sigma over square root n, we know what it has to be. It has to be equal to the 20th percentile from the standard normal distribution, right? So we have to set, and so we know what z1 minus alpha is. We know what mu a is. We obviously know what 30 is, and then sigma over square root n. We know all of those except n, and we can just solve for n. And that is a so-called sample size calculation. And logic would dictate, and of course the mathematics works out this way, that if we solve this power calculation for a particular value of mu a, it's going to be applicable for every larger value of mu a because the direction of the alternative is larger. We're not going to need a smaller or we're going to need a smaller sample size to detect bigger effects. So once we do this calculation for a specific value of mu a, it holds that sample size will give us 80% power or higher for all larger values of mu a. And so usually you pick mu a to be the smallest effect that you could reasonably detect, that you would reasonably want to detect. Okay, so the calculation when when your alternative is less than the null value is very similar. You can, if you're taking this class, you should be able to do it. For the unequal to hypothesis, things change a little bit, and here's the procedure I'm going to recommend. Pick one of the two sides. Let's say, in general, it's probably easier maybe to do the bigger side, say mu a being bigger than mu naught. So pick the bigger one-sided hypothesis. You have to pick, again, to do a power calculation, you have to pick the value of under the alternative that you're going to check. And so let's assume you pick a value of mu a that's larger. So calculate the power for the one-sided hypothesis, for the test of a larger mu a, calculate that power, but using alpha over 2 as the error rate instead of alpha for the error rate. And this is right enough. It excludes a little bit of probability in the power calculation, but it's kind of not a probability that you have to worry about so much because it's so small. And then basically what it omits is the probability, if your alternative mean is larger than the null mean, the probability of randomly getting a test statistic so small that you reject in the other direction. And so that probability is usually very small, so who cares? So you can just omit it. Fancy power calculators might include it, but usually that probability is so small it's irrelevant. So I should quit talking about it. As alpha gets larger, then the power goes up, right? If you're requiring less evidence to reject the null hypothesis, then you're going to detect more alternative hypotheses. Just like in a court of law, if you don't require much evidence to convict people, you're going to convict a lot of guilty people. You'll also convict some more innocent ones too. but that's not, power is only concerned with the probability of, under the alternative. Power of a one-sided test is obviously bigger than the power of a two-sided test. And you can see this in the calculation pretty easily in the way that I'm suggesting to do it, because when you calculate a quantile of alpha over 2, you move further out, say, into the normal probability tail, and then that value gets a little bit bigger, and you can see that the probability gets a little bit smaller. Let's see, and then the further your alternative mean gets away from your null mean, either larger if you're testing larger than, or smaller if you're testing less than, or absolute value gets further away from mu naught if you're testing not equal to, then the farther it gets away, the greater the power is, and that makes total sense in that the stronger the alternative hypothesis is, the easier it should be to detect it. And then, of course, as your sample size goes up, your power goes up. And this is why sample size calculations are so important, is because, of all the things we're discussing, the one that's only potentially under your control is usually n. So let's talk about calculating power for a t-test, because things get a little bit more complicated. So the power, just like we calculated, well, let's assume it's a greater than alternative. The power is the probability that our test statistic lies in the rejection region, so x bar minus 30 in our RDI, respiratory disturbance index example. X bar minus 30 over s over square root n is bigger than our t quantile. Now it's t with 1 minus alpha and n minus 1 degrees of freedom, with this calculation being executed under the alternative hypothesis that mu equals mu a. So now if we were to do the same trick we did before, where we were to add and subtract mu a and drag the term under the other side, we'd still have an s, which is random, to contend with on the right hand side. So that's a problem that doesn't yield a collection of things that we know that we can solve for them. Let's manipulate it around and see what we can figure out. So this probability here, this top probability, is equal to the probability square root n x bar minus 30 is greater than this t times s, and then we could divide the left-hand side by sigma and the right-hand side by sigma as well. Okay. Let's talk about how we can do this calculation given the tools that we have from the class. So here I've added and subtracted a mu a, so we get a z random variable here for square root n x bar minus mu a over sigma. Here we get something that we know, or we need to plug in values at least, so we get mu a minus 30 over sigma square root times square root n. Here, again, to remember to do any power calculation, you're going to have to plug in the value under the alternative. So even though we don't technically know mu a, we've got to be able to plug in potential values of mu a. We, of course, know our t quantile in the square root n minus 1. And then over here on this right-hand side, just in case you didn't notice it, I multiplied it and divided by a square root n minus 1. So this farmost right-hand quantity, n minus 1 s squared over sigma squared, we'll remember if the data are IID Gaussian that works out to be a chi-squared random variable. So we have over here the square root of a chi-squared. So I've just rewritten this equation now down here on the second line, where I've replaced the z random variable by z and the chi-squared random variable by a chi-squared notation. And we've stated it, we've never proved it, we've stated it that the z and the chi-squared are independent. So this probability statement is a little bit hard because it involves the bivariate distribution of a z and a chi-squared, which is a little bit tricky to work with. But we could actually do this via Monte Carlo very easily. We could simulate pairs of z random variables and chi-squared random variables and evaluate this inequality for every pair. So we would take a simulated z random variable, we would subtract square root n mu a minus 30 over sigma, we would add that, and then we would take a chi-squared simulant, and we would square root it and then multiply it by the t quantile divided by square root n minus 1, and we would just check to see which is bigger. If the left-hand side was bigger, we would record a 1, and if the right-hand side was bigger, we would record a 0. The percentage of ones from that simulation exercise, having generated lots of pairs of independent chi-squared and Gaussians, standard Gaussians, the percentage of ones would then be an approximation to this probability, and it would limit to this probability as we did more and more simulations. So if you wanted to do this more exactly, you would have to be able to numerically calculate the joint distribution of a normal and a chi-squared, which is not so hard. You can figure out how to do it, but R actually already has something. It's called power.t.test, and here I give the R code just for doing it for specific settings, and the result in this case is a power of 60%. So the function is power.t.test. Of course, you have to enter in the n. You have to enter in the delta, which in this case is mu a minus the mu under the null hypothesis. So let's assume that that's 2. Oh, a little fact that I should have alluded to before. If you look back at this calculation here, notice that this formula here only depends on the difference between mu a and mu naught divided by sigma. So I was actually incorrect when I said we needed to know mu a. We don't really, well, what we need to know is how different mu a is from mu naught in standard deviation units. So mu a minus mu naught over sigma. And notice mu a, mu naught, and sigma are all in the same units. So this quantity, usually called an effect size, is usually what these problems are sort of characterized in terms of, because it's a unit-free quantity that has some hope of being interpretable across experiments. So here, we don't actually have to plug in a sigma. We just have to know what mu a minus mu naught over sigma works out to be. If we were to put in here that delta equals 2, and then also add the argument that sigma equals 4, we'd get the identical answer, and you can try it to make sure. Okay, so let's do the same exact calculation but using Monte Carlo. Here I'm going to define the number of simulations. What is that, to 100,000? I'm going to set my n as 16, my sigma is 4, mu a, mu naught to be 32 and 30, and then I'm going to simulate 100,000 standard normals, 100,000 independent chi-squares. So now I have 100,000 pairs of normals and chi-squared. And of course, it doesn't matter how I match them up. I could permute the normals or the chi-squares and you'd still get the same thing. Here my degrees of freedom is 15 because I have 16 subjects, and my degrees of freedom is n minus 1. My t quantile is the 95th quantile of the percentile of the t distribution with 15 degrees of freedom, and that's this qt function right here. And then here this line right here, ignore the mean statement for a second. Imagine if I had just started with this z here and said z plus square root n times mu a minus mu naught divided by sigma greater than t divided by square root n minus 1 times square root x squared. X squared being the random chi-squared. That quantity would simply evaluate it would return a vector of ones every time the left-hand side was bigger than the right-hand side, and a bunch of zeros every time the left-hand side was smaller than the right-hand side. So this vector now is just a vector of zeros and ones. 1 every time z plus square root n mu a minus mu naught divided by sigma is bigger than t divided by square root n minus 1 times square root x sq. Okay, so that returns a vector of that type, and then the mean of a vector of zeros and ones is just the proportion of ones, and you can type this in. The result is 60%, or 60% up to Monte Carlo error, so you get 60 point something, of course. But by the way, for these calculations, the error rate for the mean is on the order of 1 over the square root of the sample size. So, we're getting decimal place accuracy on the order of 1 over square root 100,000. So if you want higher accuracy, you got to run the computer longer. Okay, so let's just go through these calculations. I got my RStudio window open here. Let's see, so I'm going to first do the power t-test. Let me do that. And here's the output right here. It returns the values that you input, and you get power as 60%. And then just to check, I'm going to do it here where there you go. It was SD, not sigma. So here I set SD to be 4 and delta to be 2 instead of delta to be 2 over 4, and then it assumes that SD is 1. And so here you can see you get identically the same answer here. Let's see if I can. There you go. So 60.40329. Yeah, same thing. Okay, now let's go ahead and do our Monte Carlo calculation. We'll define our number of simulations, and then here, let me just enter this in just to show you. So I'm just going to show you a couple of values from this vector, and see it's actually not zeros and ones, it's trues and falses, which are the Boolean values in R. But in R, if you say let's just multiply them by 1, which does nothing, it converts whenever it needs to convert them to numerical values for operations. It just does it. Okay, so let's take the mean of those values, and it works out to be 60.608, which is very close to the very precise calculation. Okay, and then in these final slides, I just remind us that we have to have a true mean and a true standard deviation to do these calculations, but that really it's only the change in the means divided by the standard deviations that affect the calculation. So just reminding you of that point because it's incredibly useful. All right, that's the end of Lecture 2, and we'll see you next time for Lecture 3. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp Lecture 3, where we're going to talk about two-sample test. Okay, so today we're going to first talk about match data, then we're going to talk, and match data brings up a kind of an interesting immediate discussion on the topic of regression to the mean, which has a very famous history, and then we're going to talk about two independent groups. So when you're comparing two groups, one of the first things you want to ascertain is whether or not the data are paired or not. And so it's a little less clear than you might think at first. So the most obvious instance where the data are paired is when the observations are both on the same subject. So take as an example a trial where you have a treatment, say some medication. In one case, imagine if you randomize that treatment to one group of people and randomize, say, a placebo to another group of people, then that's clearly not paired. You have one group of people that received the treatment, another group that received the other treatment, the placebo. Instance where it's obviously paired would be, imagine if you, in some random order for every person, gave them the treatment, and then had maybe a washout period, and then gave them the placebo, or for some people you gave them the placebo first and then had a washout period and then gave them the treatment. In that case, it's obviously paired because you had the same person receiving both the treatment and control. So in both those cases, the question would be to compare the treatment versus the placebo, but in one case you'd have two independent groups of separate people, and in the other case you would have each person receiving both. So in the latter case, they would be paired. And in some cases, pairing is maybe a little less obvious. So for example, what might happen is you're not looking at something that's assigned. Let's say you want to compare, let's say, people with high blood pressure to people with low blood pressure, and you wanted to compare some other characteristic. let's say let's see, we used sleep as an example the other day. So imagine if you wanted to compare the low blood pressure people to the high blood pressure people and compare their RDI, their respiratory disturbance index. Well, that seems like it would be unpaired, because you would have the low blood pressure people would be one group of people and the high blood pressure people would be another group of people. But they could be paired, because often what people do in these kinds of experiments is they get, say, their low blood pressure people, and then for every person in that group, they then try and match in terms of age and gender and other characteristics, try to closely match for every person another person in the high blood pressure group. In that case, it would be sort of softly paired, in that it wouldn't be the exact same person, of course, because a person at one given instance can't have low blood pressure and high blood pressure at the same time. But what you could have is where a person one from the low blood pressure group is very closely matched in terms of age and other characteristics and weight or whatever, to a high blood pressure person, and then they are paired. They're just paired in a different way. So that's called matching. When you try to take for every person in one group, find another person in another group that has very similar characteristics for all these other variables that you're maybe not interested in, but you think could contaminate the comparison. That process is called matching, and it's a very effective way to deal with as I mentioned, variables that you think might confound the relationship that you want to look at. So in any case, the discussion for this slide for today is to simply, to distinguish between two different types of two-group comparisons, the two main types of two-group comparisons. One in instances where observations are paired, either by matching or something else. Okay, so let's consider the instance where the observations are paired. And this is the easy case, because then everything reduces down basically to a one-sample problem. So when the observations are paired, one strategy is to take the difference between the paired observations and do a one-sample t-test of the null hypothesis that the population mean difference is 0 versus the alternative that the population mean difference is non-zero, or one of the other two alternatives. And then that would be a very straightforward thing to do. Your test statistic would just be the ordinary one-sample test statistic, the average of the distances, minus the hypothesized mean, typically 0, divided by the standard deviation of the differences, divided by the square root of the number of pairs of observations. So you want to make sure that you're putting the number of pairs of observations in there, not the number of total number of observations, because when you start out, you wind up with 2n observations, one for the first measurement and the other for the second measurement. So when you subtract them, you wind up with half the number of observations that you typically started with. So at any rate, the principal way to do this is to simply take the differences, throw out the data, and treat the differences as if they were a one-sample test. And that's the ordinary paired two-group t-test. Okay, so here's a simple example of doing a paired t-test. So I took data from 2 exams from a particular class one year. So I had 2 exams, so clearly the data are paired because it's the same students measured twice. And so let's make up a question. So I have exam 1 and exam 2, and in the question I'm going to try and ask, is there any evidence that the second exam was easier or harder than the first? And that one way to investigate that question would be to ask whether the mean of exam 1 or 2, mean of exam 1 was different from that of the mean of exam 2. Now, again, we're testing a population mean, so at some level I'm trying to model this as if the students are some draw from some population of students, which, seems kind of reasonable in this setting, even though it wasn't, they weren't exactly randomly, they weren't randomly sampled, but it seems like a reasonable thing to try and do. Okay, so let me take the summary for test 1. So in R, I just take summary test 1, and I found that the worst that the students did, which wasn't so bad, was a 76%, and the best people did 100%. And then for test 2, similarly, the worst people did was a 71%, and the best a person did was 100%. Okay, so here's a plot, scatter plot, where I have test 1 on the horizontal axis and test 2 on the vertical axis. And let's see, I've arranged it so the axes are the same, so it's both starting at 70 and ending at 100. And maybe there's some suggestion that test 2, the scores were a little bit higher. It seems like more points are lying above the identity line here than below. The correlation was 0.21, and the standard deviation for test 1 was 6, and the standard deviation for test 2 was 6 also. Oh, and the mean from the previous slide, the mean for test 1 was 87, and the mean for test 2 was 90, sample mean. And then on this next plot, what I'm showing is the difference between test 2 and test 1 versus the average of test 2 and test 1. And this plot is basically the previous plot tilted 45 degrees, sort of like kind of turning your head like that. And the reason for doing that, this is called a mean difference plot, right? The difference on the vertical axis and the mean on the horizontal axis. And there's a very famous paper. So Tukey was the person who came up with the mean difference plot. But there's also a very famous paper on sort of retest reliability by Bland and Altman, where they promote mean difference plots and actually show how to do some inference associated with them, so that these plots are quite well known. And one of the reasons for doing them, it's maybe not so necessary for this data set, but if the correlation is high, then you wind up with a lot of blank space if you do the scatter plot in the upper left-hand corner and the lower right-hand corner, and rotating it in this direction actually gets rid of a lot of that blank space and makes for a far more efficient plot. So, at any rate, that's a well-known technique, and whenever you're looking at paired observation, I think for many people, looking at the mean difference plot is more natural and almost a starting point when looking at this kind of data. Okay, so now let's actually perform our test. I'm gonna show our code here. I'm hoping that everyone in the class at this point could actually do the test. So the difference, I'm going to do the paired differences. That's test 2 minus test 1. That's this first line. N is just the number of subjects. I put a comment here that worked out to be 49 subjects. The mean, in this case, worked out to be 2.88. The standard deviation worked out to be 7.61. This is, again, the standard deviation of the differences. Okay, so my test statistic is the square root of the sample size, because remember that's in the denominator, so we could just bring it up to the numerator, times the average difference. Our null value that we're testing against is 0, so I'm just going to leave that out, divided by the standard deviation of the difference, and I have a little comment here that works out to be 2.65. The two sample p-value works out to be 0.01, so we reject. We knew we were going to reject because 2.65 is a big value of a standard normal, and by the time we get to 48 degrees of freedom, we're pretty close to a standard normal. So we knew that 2.65 we were going to reject, and the exact way we calculate this p-value is we take twice the probability of getting a test statistic as large or larger than 2.65 for a t-distribution with n-1 degrees of freedom. I think whether you do this with pt or p-norm, you're going to get about the same answer. And then because we're doing a two-sided test, we multiply it times 2 here, so 2 times this t probability. and that gives us our p-value. It works out to be around 0.01. So we reject the null hypothesis and conclude that there does appear to be some difference in the means between test 1 and test 2. I would say you typically don't go through all these calculations. You calculate your differences, and then you just use a function to do the work for you. In this case, the function is t.test in R, but every statistical package has something to do paired t-test. Okay, so we're not going to spend too much more time on paired differences. I'm hoping for everyone in this class that this discussion is no great stretch for them. But let me raise some points. One thing that when you're doing t-test, paired t-test, it's generally worthwhile to ask the question: are ratios more relevant than pairwise differences? And if ratios are more relevant, then consider doing the paired t-test on the log observations rather than the observations themselves. So another thing is, when considering matched pairs data, you always want to do some plots first. Plot the first observation by the second, and then I showed you this mean difference plot, a more efficient plot of the average versus the difference. And again, if you're interested in relative quantities, then do everything on the log scale. What I mean by that is take the natural log of every observation and then proceed with the analysis with the log data, treating it like you would treat the data normally. So anyway, this plot is called the mean difference plot. It was invented by Tukey and is often called a Bland-Altman plot, from the very well-known paper by Bland and Altman, who added quite a bit of inference on top of it. Okay, so as a bit of an aside, since we're talking about paired data, I thought maybe I'd talk for a minute about regression to the mean, because it's a sort of historically famous topic, and it involves one of the sort of eminent characters in the discipline of statistics. That person's name is Francis Galton. And Francis Galton was the cousin of Charles Darwin, and he invented quite a few topics in statistics. And he was the first to mention to recognize that this phenomenon, that when you have matched data, high initial observations tended to be associated with lower second observations, and low initial observations tend to be associated with higher second observations. So the example that he gave was sons of very tall fathers tended to be a little bit shorter, still tall, but tended to be shorter. And paradoxically, not paradoxically, but seemingly paradoxically, fathers of very tall sons tended to be a little bit shorter. And as an example from what we were talking about today, second exams for those who scored very high on a first exam tended to be a little bit lower, whereas first exams for those who scored very high on a second exam tended to be a little bit lower. So let's talk a little bit about why this phenomenon occurs. Okay, so the reason this occurs is, imagine if the test were completely random. Then and the students were IID draws from that distribution. The probability, so the highest observations on test 1 were just random observations. So the probability of a second observation being that high is quite low. It's more likely to be in the center of the distribution. So conversely, a very low test, something that had a very low probability of occurring, given that it's already low, the probability of a second test being that low is small. And so if it's perfect, or if it's exactly noise, if the pairs of observations are exactly noise, then you'll get a lot of regression to the mean. Let's consider the other extreme. Let's imagine if the test was a perfect adjudicator of students' abilities, then and it was perfectly calibrated instrument, and there was no noise, then a student should ideally get exactly the same score on both exams, at which point there would be no variation around an identity line on this plot here that says test 1 by test 2. Okay, now those are the two extremes. One is complete variation and no trend, and the other is 100% correlation, basically all trend, where the test was a perfect instrument. And of course, every practical case lies somewhere, usually somewhere in between. So here's as an example of the 8 people who got below 80 on a test. All but one did better on test 2, and of the 5 people who got above a 95 on test 1, 3 did worse on the second test. So it's not a tremendous amount of regression to the mean, but some certainly is there. And here I draw the identity line. Okay, so let's discuss this phenomenon a little bit more, and we're going to assume that the data has been normalized. So what does that mean? That means we want the data to have mean 0, variance 1. So in this case, the mean of the first test was 87, the mean of the second test was about 90, and the standard deviation of the first test and the second test were both about 6. So for every first exam, we will have taken the exam, subtracted off 87 and divided by 6, and then for every second test, we would have subtracted 90 and divided by 6. So, and of course we would have done it with the exact numbers, not just the rounded numbers like I'm suggesting. And then in that case, we'd have the empirical mean for test 1 would be 0, and the empirical standard deviation for test 1 would be 1, and the empirical mean for test 2 would be 0, and the empirical standard deviation for test 2 would be 1. So that gets rid of any sort of shift effects or scale effects. Now, when we're talking about testing about the paired data, we were exactly looking at shifts in the mean. So here we've gotten rid of the mean information by recentering the data at 0. So if there was no regression to the mean, the data would just scatter about an identity line. Well, if there was exactly no regression to the mean, it would fall perfectly on an identity line. But the more scatter there is about the line, the more regression to the mean there is. So the best fitting line goes through it actually goes through the average, and since we normalized our data, it goes through the point 0, 0, and it has slope. I wrote it out here, the correlation between test 1 and test 2 times the ratio of the standard deviation of test 2 to the standard deviation of test 1, which we normalized the standard test 2 and test 1, so these standard deviations are exactly 1. So the best fitting line goes through the has slope correlation test 1 by test 2. Okay. Okay, so just rehashing something from the previous slide, the best fitting regression line has slope correlation test 1 time correlation of test 1 and test 2, which in general is going to be less than 1. In a case where it's 1, there isn't much statistics left to do. So this will be shrunk towards a horizontal line, telling us our expected normalized score for test 2 will be this correlation times the normalized test 1 score. So if the correlation is 0.95, then your estimated test 2 score will be 0.95 times your estimated test 1 score. And this line sort of appropriately adjusts for a regression in the mean for test 2, conditioning on test 1, or equivalently, test 1 conditioning on test 2. If we knew your test 2 score and we wanted to guess what your test 1 score was, normalized test 2 score is, and we wanted to guess what your normalized test 1 score is, we would multiply by the same correlation. On our plot, the slope of the line will be test 2, will have this slope correlation test 1, test 2, where here I'm assuming test 2 is the vertical axis and test 1 is the horizontal axis. If we wanted the slope going in the other direction, the slope would obviously be the inverse. Well, I don't know how obvious that is, but the slope will be the inverse. So just to rehash, in either case, if you want to adjust for regression to the mean, you're multiplying the test, the normalized test that you have, and the one that you'd want to predict, you would multiply it by that correlation. But let me just show you a plot here. This will probably make it a little bit easier. So here I have normalized test 1 score on the horizontal axis, and normalized test 2 score on the vertical axis, and the slope of this line here is the correlation between the two, which is about 0.21, and that's the regression line of test 1 on test 2. I show an identity line here in the middle, and then if you wanted to do the same thing, as if you had test 1 on the vertical axis, then you would use this almost vertical-ish looking line here, and that's just the inverse. That has slope inverse of this correlation here. Notice both these lines pass through the point 0, 0. Okay, and this phenomenon, and so this line, notice how it's you know, when now we're looking at test 2, when we want to predict our test 2 score from our test 1, it's very flat, right? It's very flat, suggesting that there wasn't a lot of correlation between the two tests, and that amount of noise means that there's a fair amount of regression to the mean, and so that if we want to predict our test 2 score from our test 1 score, we're shrinking it quite a bit. And then you can see the same thing in the other direction, that it becomes the adjustment for the regression to the mean becomes very vertical, and that's because the correlation was quite low because there was quite a bit of noise. Notice as the points, if they were to fall more and more on an identity line, so they would kind of collapse around this identity line, then these two cross-haired lines would sort of go like this, and they would converge to the identity line themselves, and that would mean that there was very little regression to the mean. Anyway, it's a neat historical story that Francis Galton figured this out, and his discovery of this was something that led to the discovery of the far more advanced topic of regression. But let's just make some final comments about this. So an ideal examiner, I guess I'm not an ideal examiner from this test I gave, there would be little difference between the identity line and the fitted regression line. And the more unrelated the two exam scores are, the more pronounced the regression to the mean. So, and this is something I heard a talk about this once, that there was a question of how much of our discussion of sports is really discussion of regression to the mean. So the idea is that there's a lot of noise in, say, teams or players' performances, and the ones that do the best in any one given year is a combination of them just being better plus random variation. If that random variation is very high, then there's a good chance that the following year, the following season or whatever, they'll have a far lower performance in whatever statistic or measure you're talking about. So, for example, in U.S. In baseball, a popular sport in the U.S., if someone has a particularly high batting average early on in the season, there's a good chance they'll regress to the mean in the latter half of the season. And the reason for that is because there's a component of it that is performance, that's inherent, that's the player's skill, and then there's a component that's random variation. And the larger the amount of random variation, the more you'll see regression in the mean. And in that case, the discussion is a lot of discussion about sports, I think, actually amounts to discussing regression to the mean, that sometimes the players that have huge rebounds were just unlucky, and the players that initially and then got luckier in their when they were having their rebound, and the players that did extremely well and then did a lot worse, their intrinsic ability may not have had change too much, but simply they were lucky early on and then less lucky later on. Okay, so let's get back to some far more pedestrian points now. Anyway, regression to the mean is a very fun topic, and I would suggest you read up on it. I also read up on Galton. He was quite an interesting character. His name is Francis Galton, and he was just a remarkable figure in history. And so I suggest you read up on Galton just out of interest. Anyway, so let's get back to some of the more straightforward things we're going to talk about. The extension not to paired data but to independent groups shouldn't really come as a big surprise either. I'm hoping at this point in the class, after having taken Boot Camp 1, that a lot of this discussion will just come very naturally to you. So let's suppose we want to test H naught mu1 equal mu2, where we have two independent groups, versus that they are different, or one of the two alternatives. Then, assuming a common error variance between the two groups, we would have this statistic right here. Okay, our natural estimator of mu1 minus mu2 would be, let's say x bar is group 1 and y's are for group 2. Then our natural estimator of mu1 minus mu2 would be x bar minus y bar. Under the null hypothesis, that would have a hypothesized mean of 0, so we don't need to subtract anything off up here on the right. And then the standard error of x bar minus y bar is the common standard deviation across each group times square root 1 over the sample size in the first group plus 1 over the sample size in the second group. And I hope everyone's capable of deriving that. And this follows a t nx plus ny minus 2 distribution under the null hypothesis and the usual assumptions. And we covered this in Boot Camp 1 when we talked about confidence intervals. Basically, when we created the interval x bar minus y bar plus or minus this t quantile times this standard error. So it's exactly the same thing, and it follows exactly the same logic. Here it's, the normalized test statistic is estimator minus hypothesized value under the null hypothesis divided by standard error. It follows the same logic as we've been doing for one sample test, so it should be no great stretch for anyone. Then if you have large sample sizes, it shouldn't be surprising for you that the statistic on the previous page follows a normal distribution. If you're not willing to believe that the variance is the same in the two groups, then the standard error of x bar minus y bar works out to be square root sx squared, where sx squared is the variance in group 1 divided by nx, plus sy squared, which is the variance in the second group, divided by ny, which is the sample size in the second group, square root of the whole thing. And so, of course, if the variance were the same, then you would be able to pull it out, and you get the formula from the earlier part. So just to remind you, I don't think I mentioned it on the previous slide, that the s sub p from the previous slide is the pooled variance, whereas here now we're talking about the variance within group 1 sx squared and the variance within group 2. So anyway, this follows a standard normal distribution if nx and my are large, and it approximately follows a student's t distribution if the x and y's are normally distributed and independent both within and between groups. But there's this crazy formula for the degrees of freedom, and the approximate degrees of freedom are sx, this formula here, I'm not going to read it out loud. And you can plug into it if you want. And it turns out to be fairly accurate. The distributional approximation turns out to be fairly accurate. And so you can do this. It's a little bit of a crazy formula, and there isn't, as far as I know, a ton of obvious intuition as to why it works out this way. But what you want to think about it is that it's not surprising that x bar minus y bar divided by its standard error follows something, if the data are normal, that it follows a distribution that looks like a t distribution. And the fact that it doesn't follow exactly a t distribution falls out from the fact that we don't have the common variance. but it seems reasonable that you would be able to pick the degrees of freedom that approximate the actual distribution of this normalized statistic, to be as close as the one we're using with these approximate degrees of freedom. And note the degrees of freedom can be fractional, so it's okay that this doesn't work out to be an integer. And then a couple of notes. So our connection between hypothesis testing and confidence intervals still holds. If your independent group T interval it contains 0, then you will fail to reject the independent group t-test for equality of means, provided you calculated the standard error in the same way. And vice versa, if you construct a confidence interval by finding all the hypothesized values for differences of means for which you fail to reject, you would wind up exactly with the appropriate t confidence interval. Another thing that comes up all the time, which is people want to test for equality of means by constructing a confidence interval for group 1 and a confidence interval for group 2, and then seeing if those confidence intervals overlap. And that procedure works in one sense, that if the confidence intervals don't overlap and you reject, that's an accurate statement. But if the confidence intervals can overlap, and this the test statistic constructed correctly would reject, but the confidence intervals do overlap. So the fancier way of saying is that this procedure of checking whether independently constructed intervals overlap just has lower power than just doing the right test. Also, it has a potential really bad abuse that I've seen happen, is that people construct an interval for group 1 and an interval for group 2, but they fail to acknowledge that people are paired. And then they do this procedure. And then that's quite bad, because then you're throwing out an incredible amount of information in the pairing, right? And or the purpose of the pairing. Sometimes the purpose of the pairing is to account for confounders or something like that. So you're both either throwing out information or eliminating the entire reason for that the pairing occurred. So don't do that, but I know no one in this class would do that anyway. Okay, let's go through an example. Suppose instead of having repeated data on 2 exams, that we randomized to 2 teaching modules and each group took the same exam. So I'm going to treat the data from before as if it was independent group data. Just to illustrate performing the calculations. It wasn't actually what happened, but whatever. So imagine it, but here's a setting where we would analyze the data this way rather than treating it as paired. So, and the easiest way to recognize that you don't have paired data is if your n's are different. But that could also be misleading, because you could have some missing data and have different n's. So at any rate, the easiest way to determine whether your data is paired is ask yourself this question: are my data paired or not? And then you'll know. Okay, so here we have 2 modules that we randomized students to, 50 students in each. The mean for one was about 87, the mean for the other was about 90. We've thought it through and realized that no, there was no pairwise association. Student 1 from group 1 has nothing to do with student 1 from group 2, and so on. The standard deviations were both about 6. So here, the pooled standard deviation, because the n's are the same, works out to be the average 6.065 of the variances. Remember, the pooled standard deviation works out to be the average of the variances, not the average of the standard deviations. So that does work out to be 6.065. And then our test statistic is the difference in the means, 89.8 minus 86.9, divided by the pooled standard deviation estimate, which go back to Boot Camp 1 and look at how we do the pooled variance estimate. But when the sample sizes are equal, it works out to be the average of the variances. So in this case, it would be square 6.07 and average it with the square of 6.06, then square root. You wind up with 6.065 times square root 1 over 50 plus 1 over 50. And that's your test statistic, and you do the rest. You check whether this test statistic is big enough to reject. And the sample sizes are big enough to where you can just compare this to a z distribution. The difference between a z and a t is irrelevant for sample size this large. So we're moving through this stuff kind of quickly because we want to get to some more interesting stuff, and I feel like we've mostly already covered this stuff by covering independent and pair group confidence intervals. But just some final notes. Look over the review notes on formal test for equality of variances between two groups. I'm not a huge fan of this. Some books tell you to employ the following strategy: evaluate whether or not the variances are equal by performing a test of equality of variances, and then if you reject, do the unequal variance test, and if you fail to reject, do the equal variance. I never liked those kind of recipe approach to statistics. I would say, well, first of all, these tests aren't very good. They rely on the F distribution. They're heavily dependent on the normality assumption. So I would say just do a bootstrap. If you want to test equality of variances, do some sort of bootstrapping, resampling type thing. Don't do this F test. We have better things now, so just do them. And then for smaller sample sizes, just rely on exploratory data analysis. But in general, if you're concerned about equality of variances, just use the unequal one, and that solves the problem right there. Okay, and then some very final comments. I know I keep saying final comments, and then lying. Suppose you have equal numbers of observations for two groups, and let's label the groups X and Y, and the data. The data is random variables X and the random variables Y. If the data are matched or paired, then the standard error of the difference is estimating sigma squared Y plus sigma squared X, both over n, minus twice the covariance divided by n. And you can do this calculation if you'd like, or you can just trust me. Square root of the whole thing if you want to standard error. If you ignore the matching, then the standard error of the difference is estimating this square root. My point is, in many cases, by ignoring this correlation, you're unnecessarily inflating your standard error, right? If this covariance is positive, right, then this -2 covariance over n, you're throwing out a positive term, and this is the idea that, for example, if you're comparing exams and you want to know whether exam 1 was harder than exam 2, if you threw out the information that it was the same students taking it twice, then you discard the fact that some students study more than others, some students maybe have different backgrounds than others, and so on. And so some students will consistently do well on exams, and some students will consistently do poorly on exams, and that is encoded in this -2 covariance term. And that's saying that variation associated with inter-student variability, that you're throwing that away and absorbing it into the rest of the variance. So at any rate, the point is that if you treat group data you treat paired data as if it's grouped, you are missing out on you're missing out on an important term in the covariance, and we can actually characterize what that term looks like. Now you might think to yourself, why in the world would anyone ever run a non-paired experiment then? And I think, for more complicated settings, the rule isn't always the case that the pairing always yields lower standard error. So in more complex settings, other things can happen. As an example, if you're studying test, there might be there might be a learning effect, right? That you don't want to intrinsically study. Students may, on the second exam, might simply be better by virtue of having already taken the first exam. So it's not fair to say, is the second exam better, it's harder than the first exam, or easier than the first exam, when the students have had an exam to practice and get used to the teacher's style. That sort of learning effect is an obvious thing. So if you really wanted to investigate the intrinsic properties of exam 1 versus exam 2, you might want to study an independent group exam, because otherwise with only data where exam 2 has been tested after exam 1, you can never learn about that learning effect, right? You know, for all the data points, exam 2 was after exam 1, so you can't investigate that. Now, so there are study designs where they try to both take advantage of the pairing and investigate these sorts of learning effects. And I think you're probably thinking to yourself that what the obvious thing that you would have to do. Well, for some people they would have to take exam 2 first, and other people they would have to take exam 1 first. And you know, maybe in the setting of an exam, this isn't a reasonable thing to do. But in the setting of drug development, it is a reasonable thing to do. Let's suppose not 2 exams, but you're testing 2 headache medications. Then you might, for every patient, give them headache medication 1, have a washout period, then give them headache medication 2. And then for another set of patients, give them headache medication 2 first, and then give them headache medication 1 second. And those kinds of designs are called crossover designs, and they've randomized the order in which the people receive the treatment in order to adjust exactly for this learning or carryover or whatever you'd like to call it effect. But at any rate, my larger point being that the point of this slide is not to say pairing is always better than independent groups, but simply to say that if your data are paired, treating them as if they're independent is both wrong from the point of view of assumptions, but also in some cases can actually hurt you in terms of actually making you less likely, you know, inflating your standard error. Oops, I guess that means I gotta go. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 4 on two-sample binomial tests. Okay, in this lecture we're going to talk about the score statistic, which is a specific two-sample binomial test that will serve as motivation for creating a confidence interval as well. We'll talk about how you can do exact test for 2 binomial proportions, and then we'll talk about comparing 2 binomial proportions. And then we'll go over a little bit about Bayesian and likelihood methods for comparing binomial proportions. We'll actually spend quite a bit of time on binomial proportions because later on we'll also talk about relative risks and odds ratios and that sort of thing. Okay, so let's put some context on this. So imagine a randomized trial where there was 40 subjects, and 20 each were randomized to 2 drugs, and the 2 drugs had the same active ingredients, but let's assume they had different expedients. That ways in which the drugs were delivered. One, let's just say one was a capsule and one was a different kind of pill. Okay. So consider counting the number of side effects for each drug among the 40 people. So here we have a table where there's 40 total people, 20 in drug A, 20 in drug B. So this margin is fixed, 20 and 20, that margin is fixed. And then 11 from drug A received side effects, and then 9 didn't, and then 5 from drug B had side effects, and 15 didn't. So on face value, there seems to be a greater propensity for side effects from drug A than from drug B. And what we'd like to do is to do a test of whether or not the side effects are, the propensity for side effects is the same within the two drugs. And there's a lot of different ways we could formulate this problem, even from this simple data set. And we'll talk about some of the ways. to do that. But for right now, let's just start with talking about score test. So the scores test should seem fairly familiar to you because it's just going to be constructed in the same way that the ordinary test is, the sort of ordinary z-tests are constructed in the way that we have before. So let's consider a single binomial proportion, not two binomial proportions, but a single binomial proportion, and later on in the lecture we'll consider two binomial proportions. So imagine only looking at drug A and saying, well, let's test whether or not drug A has a specific population proportion of side effects. So we want to test H naught P equal to P naught, and so our obvious estimate of P naught is P hat, the sample proportion of side effects. Okay, so our obvious metric of the discrepancy between P hat and P naught would be the difference, or maybe we could do a log ratio or something like that. But for right now, let's do the difference. Okay, but in order to compare this to a statistical distribution, let's normalize it by the variance of P hat. Well, the variance of P hat is P times 1 minus P over N, and under the null hypothesis, that's P naught times 1 minus P naught over N. So the standard error is the square root of that. And notice that we're plugging in the P naught under the null hypothesis, not plugging in P hat, which would give us the estimated standard error that we used, for example, in the construction of the confidence interval. So at any rate, this test, when you plug in P naught in the denominator here, performs a little bit better than the so-called walled test, where in the denominator, rather than plugging in P naught, we plug in P hat. So remember how we can invert this test statistic to perform to create a confidence interval, and we can, of course, we can use the test statistic to just perform the test. So I should have said this on the previous slide, but that z statistic you compare to quantiles from the standard normal distribution, the upper alpha over 2th quantile if you're doing a two-sided test, the upper alpha over 2 quantile if you're doing a one-sided greater than test, the upper alpha quantile if you're doing a one-sided test where the alternative is greater than P naught, and the alpha quantile if you're doing a one-sided test where you're testing P less than P naught. Okay, so and this should be obvious to you at this point in the class, how you would take a z statistic and then use it to perform a test. And then of course we've already talked at length in other settings, for example in inverting the t-test and the standard z interval, on how we can invert a confidence interval and invert a hypothesis test and create a confidence interval, namely calculate those values of P naught for which we'd fail to reject. If we invert the walled test, we get the walled confidence interval, P hat plus or minus z 1 minus alpha over 2 square root P hat 1 minus P hat over N. And if we invert the score test, we get a so-called score interval, which is a lot more complicated. We get P hat times this quantity plus 1/2 times this quantity plus or minus our normal quantile, our upper alpha over 2 normal quantile, and then this standard error formula. I want to point out one thing about this is not a numerator here, by the way. This is this quantity, P hat times this thing plus 1/2 times this thing, and then I ran out of space, so then on the next line I put plus or minus the normal quantile times the standard error. So this is P hat times n over n plus z squared, and then plus 1/2 times z squared over n plus z squared. So look at these two factors, n over n plus z squared and z squared over n plus z squared. They add up to 1. So they're two proportions that add up add up to 1. So in other words, a point on the two-dimensional simplex is what you might say in mathematical parlance. But what's important is as n gets very big, this first term gets very big and P hat dominates. if n is small, then this term in front of the 1/2 gets a little bit bigger, and well, the 1/2 probably hopefully doesn't dominate, but there's more greater fraction placed on the 1/2. And just to give you context, the z 1 minus alpha over 2, well, z, that's usually going to be around 2, so this is about 4. So it's about n over n plus 4 plus 1/2, 4 over n plus 4. At any rate, and as n gets very large, it just becomes very similar to the Wald interval. So what this does is it takes p hat and it shrinks it towards 1/2. And that turns out to be a good thing to do, because the binomial confidence interval, you don't want it centered exactly at p hat, because the binomial distribution as p hat is further away from 1/2 gets more asymmetric, it gets more skewed, and because of that you don't want that point right in the middle. At any rate, so we talked previously about confidence intervals for binomial proportions, and plugging in z1 minus alpha over 2 equal to 2 yields the so-called Agresti-Cool interval that we talked about before. So this is actually the motivation for the Agresti-Cool interval, is that most people do 95% intervals, and if we take our 1.96 and just round it up to 2, and plug it into the score interval, we get exactly the Agresti-Cool interval. Okay, so let's do our example. In our previous example, consider testing whether or not drug A's percentage of subjects with side effects is greater than 10%. So I made up 10%. So let's assume that the FDA gets really mad for this kind of drug if you have more than 10% prevalence of side effects. So H naught PA is equal to 0.1 versus HA PA greater than 1, where PA is the population proportion of side effects for drug A. And then our p hat is 11 over 20, which is 0.55. Our test statistic is 0.55 minus 0.1 divided by square root. Remember to plug in the p naught from the null hypothesis. 0.1 times 0.9 divided by 20, you get 6.7. We reject the p-value. We reject, our critical value is going to be, for a one-sided test, is going to be about 1.65, or a two-sided test, if it would be about 2. Either way, 6.7 is going to be bigger than it. And then our p-value, the probability of getting a z bigger than 6.7, is of course nearly around 0. 7 standard deviations away from 0 for a standard normal is quite far out in the tails. Remember that 3 standard deviations covered the majority of the distribution. And then if we were doing a two-sided test, remember that we would double this p-value. Okay, now let's discuss this problem a little bit. So what do we have to do to get this to work? So mechanically, I hope you find this easy, but let's talk a little bit about the thinking of this. So we're postulating that the number of side effects out of 20 is a binomial trial. Well, that implicit in that is the idea that then we have IID data. Every person is independent and identically distributed, draw from a population. So we're using those assumptions, the IID assumptions, to create the idea of a population, superpopulation that has a prevalence of side effects of PA. Of course, we cannot, in general, you can't know that unless you're actually in a setting where people are going to great pains to actually sample independently from the population they're interested in, which is usually not the case. In general, the sample is, what you're doing is you're doing a statistical model where you're hoping that the people are a representative sample. You're hoping that there's no crossover of side effects. So let's suppose some of the people receiving the drug are friends or in the same family or in the same neighborhood or something like that, that there's no reason that if one person gets side effects that it's more likely for anyone else around them to get side effects who also receive the drug. So no interference is what they would call that. And so our IID model is what's giving us here this idea of a population proportion, and then we're testing relative to that proportion. But it's good, I think, whenever you're doing these kinds of tests to actually think about what you're modeling is random and what your population model is that you're trying to do it, because modeling is a
modeling, the calculations here are very simple, right? I hope we all agree that the calculations are very simple. But the principles, the idea of how the modeling is going is a lot more delicate and actually on a lot more shaky ground. So that's why it's a good idea to always sort of think through your modeling assumptions and what they imply for your actual hypothesis. So just to give you an example, let's assume that our sample of people are all people who are professional drug takers for pharmaceutical companies, sort of professional guinea pigs. They, whenever a drug company says, "Oh, well, we want to test out this headache medication," they sign up. And there are people who do this, of course, right? It's you can. You can make maybe not a tremendous living doing it, but the drug companies, of course, pay people for their time to test out these sorts of drugs. Then it would be hard to declare that population IID draw from the general population, because this is a very, very different sort of people. They probably adhere to their medication schedule very precisely, and other things like that. They're probably very good takers of medications. They probably do the instructions quite well. They know, and so on. So at any rate, my larger point being is that when you get this number 6.7, which is very easy to obtain, think about what it means in the context of the model that you've used. And in this case, the model is seemingly very benign, but the big part of the model is the IID draw from a population. Think about what that means in the context of the problem that you're studying. Okay, so in the previous slide, our assumptions depended on having a large enough sample for the central limit theorem to be applicable. We can't actually do an exact binomial test, which by exact I mean the calculation utilizes the binomial distribution rather than the asymptotic distribution of the normalized sample proportion. So in this case, the event of getting, so we observed 11 people with side effects in the sample. We're testing greater than, that our sample proportion is greater than something else. So the probability of getting evidence as or more extreme than we obtained would be the probability of getting more people than we observed, which is 11 side effects. So this is the probability of XA, which is the count of the number of people with side effects for drug A, being bigger than or equal to 11. That's the sum from 11 to 20 of the binomial proportion. And then you might ask, well, where does the null hypothesis come in? Where does the fact that we're under the null hypothesis that P naught is 0.1? Well, right here, so it's 0.1 to the x, 0.9, which is 1 minus 0.1, to the 20 minus x. So in other words, this calculation, the probability of getting more than 11 people with side effects out of 20, is done under the null hypothesis that P naught is 10%. So this is the probability of getting evidence as or more extreme in favor of the alternative, with the probability being calculated under the null hypothesis. So this is a p-value. If you do this calculation, the probability of getting 11 or more out of 20 with a probability of 0.1, if you do that calculation, that probability is around 0. There's very little contribution of these numbers are quite small. And you can do this in R very easily. Just p binom 10, 20, 0.1, lower dot tail equals false. Now, I just want to point out the small little detail here. If we did p binom and didn't have this lower dot tail equals false, if we had lower dot tail equals true or omitted it because the default value is true, then it's going to calculate the probability of 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0. If we do p binom lower dot tail equals false, in other words, it wants to calculate the greater than probability, it does strictly greater than. So if you do lower dot tail equals true, it does less than or equal to, so includes 10. If you do greater than, if you do lower dot tail equals false, hence you want greater than, it does a strictly greater than, so it starts at 11. So if you put p binom 10, 20.1 lower dot tail equals false, it's going to calculate the probability of 11 plus 12 plus 13 plus 14 plus 15 plus 16 plus 17 plus 18 plus 19 plus 20. Okay, so in other words, p binom 10, 20.1 lower dot tail equals true, that number, plus p binom 10, 20.1 lower dot tail equals false, those two numbers add up to 1. 10 is only included in the instance where lower dot tail equals true. In the instance where lower dot tail equals false, it goes above 10 to 11 and higher. Anyway, it's a small point, but you get the wrong answer if you don't do that. And then if you want to avoid this discussion, you could just do binom.test and say, well, we had 11 successes out of 20 trials, and we want to test the hypothesis that it's 0.1, and I want my alternative to be greater, and binom.test does it. Binom.test is maybe a little bit nicer to use because it actually does gives you the exact confidence interval as well. Okay. So one of the reasons this test is called exact is that unlike the asymptotic error rates, where the alpha that we use to get the normal quantile is an approximate error rate for the test. So if you perform a 5% level asymptotic test, the alpha level is not necessarily 5%. It might and there's been work to show that in some cases it can be substantially higher than 5%. On the other hand, this exact test, this guarantees that the alpha level is, let's say you pick alpha equal to 0.05, it guarantees that the alpha level is 5% or lower. The problem being or lower is that it's exact but conservative, so it's 5% or lower. So in some cases with very small sample sizes, the exact level can be much less than the observed level, than the desired level. And then, for two-sided tests, what I'm going to suggest is calculate the two one-sided p-values. It should be obvious which one is going to be the smaller one, and then double it. And that just kind of follows our rule we've been using in normal tests, and this is good enough. There are maybe slightly better procedures, but they change the numbers only a little bit. So given that we can do a two-sided test, either by this way or maybe by better ways, we could calculate every value of p naught, let's say by a grid search, for which we would fail to reject the null hypothesis in our two-sided test, and that would yield a confidence interval, and that confidence interval would have an exact coverage rate. So it would have coverage, if you did a 5% test, it would have coverage 95% or higher. That's right. So all these things are slightly conservative, so it would be 95%, maybe much higher, maybe 97% if it's a very small sample size. And this interval is given a name. It's called the Klopper-Pearson interval. But the benefit of it is it guarantees your coverage rate. You get coverage 95% or better, or higher. The problem is that in the event that it's or higher, you've potentially unnecessarily widened the interval, right? Because if you want higher coverage, you're generally going to get a wider interval. So there's no such thing as a free lunch. And exact intervals fall under that category just as well as everything else, in that they do guarantee your error rates, but then they have this tendency to be conservative. Wider intervals being a little bit less likely to reject the null hypothesis are the consequences of using them. On the other hand, you do get the assurance that the error rate is exactly adhered to given your assumptions. I just wanted to show a picture from an American statistician paper that I was involved in based on earlier work by Agresti and Brant Kuhl. And here, what we did is we compared the coverage rate of the walled interval versus the approximate walled interval obtained by using inverting the score test and just simply plugging in 2 rather than 1.96. And what you see in these top lines is that the jagged, they're jagged because of the discreteness of the binomial distribution. Here we show, let's just look at this top row for 95%. Okay, what you can see is that this solid line, the Agresti-Cool interval, it hovers right around 95%. Sometimes it's a little low, sometimes a little high, but it still hovers right around. The walled interval can be quite a bit off. Now this is a small sample size, so that there's no reason to believe the asymptotics have kicked in and done very well. But even if you get up to, say, a sample of size 20, the closer the true value of p is to 0 and 1, you can get coverage that is very low, 70 below. Here I think it's truncated at 70%, but it dips down and touches 0 at 0 and touches 0 at 1. So the point being that switching away from this walled interval where you put p in for the confidence interval, where you put p hat in the standard error calculation, to the Agresti-Cool interval where it's a simple fix, really improves performance quite a bit at no conceptual or computational cost. So that's just the point I'm trying to make here, and it relates to this discussion of it's basically saying that the score interval is performing a lot better than the walled interval in this case, and that tends to be a general rule of thumb. Okay, so now let's actually get to comparing two proportions rather than simply looking at one proportion. So we want to test whether the side effects is the same in the two groups or different. So imagine if A is some new formulation and B is the standard, and you want to test whether or not the new formulation has more side effects than the standard. So in general, for 2x2 tables, I'm going to use the following notation. I'm going to have x, n1 minus x, and n1 plus y, and n2 minus y, and n2 plus. And then if I need to, I'll refer to the four cells, indexing them by their matrix coordinates n11, n12, n21, n22. I'll call n1 the right margin, n2 the right, n1 the right top margin, n2 the right bottom margin. But if in the case that I'm referring to both margins, I'll say n1 plus, n2 plus, n plus 1, and n plus 2 for the respective margins. In other words, just summing, the notation meaning summing over that index. Okay, so now let's do a score test type test of a hypothesis that P1 equals P2. So our null hypothesis is H naught P1 equals P2 versus not equal to, greater than, or less than. And then the score test for this null hypothesis, our numerator is P1 minus P1 hat minus P2 hat, the sample proportion in group 1 minus the sample proportion in group 2. And then if we were assuming that this difference was a constant other than 0, we would put that in the numerator here, the null hypothesis difference. But typically, the null hypothesis is that they're equal. So there's minus 0 here, the hypothesized null value of the difference. So we can just omit that. And then in the denominator, under the hypothesis that P1 equals P2, then the variance of P1 hat minus P2 hat is P times 1 minus P quantity times 1 over N1 plus 1 over N2, where P is the common proportion P1 equal to P2. So under the null hypothesis, we need an estimated version of that if we're going to actually get a number here that we can use compared to a normal quantile. So we need a value of P to plug in there. So we say plug in P hat. If under the null hypothesis the sample proportions are identical, then group A is a bunch of IID draws, IID Bernoulli draws from group 1. Group B is a bunch of IID Bernoulli draws from group 2, but they have the same proportion, so we really just have N1 plus N2 Bernoulli draws, and our estimate of the proportion would simply be the total number of events. So that P hat is X plus Y over N1 plus N2, and that is exactly the MLE for P, the common proportion under the null hypothesis that the two proportions are equal. So we plug that into the denominator, P hat times 1 minus P hat, and then we get our test statistic, which is again just estimate minus hypothesized value divided by the standard error. And then this statistic is normally distributed under the null hypothesis for large n, standard normally distributed under the null hypothesis for large n1 and n2. So if we want to invert this to create a confidence interval, well, we don't have a closed form like we do in the score test for a single proportion. The walled interval is p1 hat minus p2 hat, and then it doesn't utilize the fact that under the null hypothesis the proportions are equal, so then you just have a separate p1 hat 1 minus p1 hat over n1 plus p2 hat 1 minus p2 hat over n2 in the denominator, square root the whole thing. And you can of course invert that to get a confidence interval, p1 hat minus p2 hat plus or minus z 1 minus alpha 2 times the square root of the standard error. By the way, do you see why you can't invert the score test? The reason being that if you change the denominator was explicitly calculated under the specific null hypothesis that P1 equals P2. Here in this test statistic, if we were to have a different null that P1 minus P2 wasn't just equal to 0 but was equal to some other value, we would add that in the numerator and then the denominator wouldn't change, whereas in our score test we wouldn't have any way to adapt that denominator, and that's or no immediate way to adapt the denominator, and that's why you have to use some programming to get the confidence interval from that one. But this one, the walled test, we can invert very easily, and we get an interval that should be fairly familiar to us. P1 hat minus P2 hat plus or minus the normal quantile times the square root of the standard error. That's the so-called walled interval. It's very easy to calculate, and it's taught in nearly every statistics textbook. So this performs poorly, this walled interval performs poorly, and it's relative to the score interval and test. The walled test and the walled interval perform relatively poorly, but their decrease in performance is less so in the one sample case. In the one sample case, there's a huge decrease in performance, but the subtraction of the two proportions, subtracting two things tend to make them more normally distributed, so it helps a little bit, and the decrease in performance for the walled interval isn't anywhere near as bad as it is in the single proportion case. So for testing, I would just say always use the score test. That's easy. For intervals, inverting the score test is hard, and it's not in standard software. So our simple fix that we propose in an American statistician paper is to add one success and one failure in each group. So calculate P1 tilde, which is x1 plus x plus 1 over n1 plus 2, n1 tilde, which is n1 plus 2, P2 tilde, which is y plus 1 over n2 plus 2, and n2 tilde, which is n2 plus 2. So this is exactly taking this 2 by 2 table that has the successes and failures for each group and adding one to every cell. That's exactly what this is. And then just treat that as if it's the data and construct a walled interval. And this interval, it doesn't approximate the score interval like in the Agresti-Cool interval, but it does perform better than the walled interval, and I'll have a slide in a second to show you this. Okay, so let's just perform the test, the score test, test whether or not the proportion of side effects is the same for the two drugs. PA hat is 0.55, PB hat is 5 over 20, which is 0.25. P hat, the common proportion, is 16 over 40, 11 plus 5 over 20 plus 20, which is 0.4. So our test statistic is 0.55 minus 0.25 over 0.4 times 0.6 times square root 2 over 20. Square root the whole thing. Anyway, you can plug in the formula, you get 1.61, and then we fail to reject H naught at the 5% level. In other words, you compare with 1.96 for a two-sided test. The two-sided p-value, calculate the probability that the absolute value of a standard normal is bigger than 1.61, which is that the positive part of a normal is bigger than 1.61, plus the probability that the negative part of a normal is below negative 1.61. That's, I guess, 0.055 in either tail. So we fail to reject, there's our p-value. And so hopefully everyone can do this calculation very easily at this point in the class. Okay, so here's the same picture as before, where in the previous picture I showed the true value of the proportion by the coverage rate of the interval for the single proportion. Now here there's two proportions, P1 and P2. So here by the true value of P1 and P2, here's the coverage probability. On the left I have the walled interval. On the right I have this Agresti-Caffo interval where you add one success, one failure to each group, one to every cell in the 2x2 table. And you can see that you get these big kind of dips down towards 0 in the walled interval if either of the proportions is either of the proportions is either very low or very high. You get very bad performance, and you get performance that's well below 0.95, and this shrinkage towards 0.5 for each of the means for each of the proportions, it improves things dramatically, and it's a very easy thing to do. And then here's a simple, another exact same plot, just some cross sections through it of different sorts. And in the top ones I have where P1 minus P2 equals particular values, and then on the bottom one I have ones where ratios of P1 and P2 are fixed. In other words, it's just sort of slices, maybe not slices or curves through that two-dimensional picture. And it just shows the in a nice easy 2D plot what the relative performance of the Agresti-Caffo interval is relative to the walled interval. Okay, let's briefly go over some likelihood plots and Bayesian analysis of two binomial proportions. So likelihood analysis requires the use of profile likelihoods or some other technique to reduce the dimension down if you want to do a 1D likelihood plot. And we can actually show you later on a way you can use the so-called non-central hypergeometric distribution to get an exact likelihood plot for the odds ratio. But for the difference in the proportions, it's a little harder. Probably doing a profile likelihood would be the way to go. So it's a little hard, so let's leave that discussion for elsewhere. So instead, let's talk about being a Bayesian. So we talked about for a single binomial proportion, putting a beta prior on a probability to get a posterior. So imagine putting an independent beta alpha 1 beta 1 prior and a beta alpha 2 beta 2 prior on P1 and P2 respectively. Then the posterior, so remember how the calculation goes. You take likelihood times prior equals posterior. So here the likelihood is P1 to the x1, 1 minus P1 to the n1 minus x1, P2 to the y1, 1 minus P2 to the n2 minus y2. And then the beta prior is P1 to the alpha 1 minus 1, 1 minus P1 to the beta 1 minus 1, P2 to the alpha 2 minus 1, 1 minus P2 to the beta 2 minus 1. So if we multiply all those together, we get this formula right here, which exactly shows that if we have two independent binomials and then we multiply them by two independent betas, we wind up with an independent a pair of independent beta posteriors, one beta posterior for P1, one beta posterior for P2, where now the beta parameter is no longer alpha 1 but alpha 1 plus x1 for P1, and the beta parameter for P1 is n1 plus beta 1. The alpha parameter for P2 is y plus alpha 2, and the beta parameter for P2 is n2 plus beta 2. So it's basically like alpha 1 and beta 1 are the beta alpha and beta parameters for P1. A priori, after you factor in the data, you add the successes to alpha and the failures to beta. You add and the same for P2, and then you get the beta posteriors. And the easiest way to explore this posterior is with Monte Carlo simulation, and I'll show that right here. So it's very simple. So here I define my x, my n1, my alpha 1, my beta 1, my y, my n2, my alpha 2, and beta 2. And here I just did a uniform plot prior. So if I have a beta with a 1 and a 1, that's just uniform. So I put a uniform on both P1 and P2. Then I'm going to sample from the posterior, so I just simulate random betas. I simulated 1,000 beta pairs, where now my alpha parameter is x plus alpha 1, n minus x plus beta 1. And then for P2, my alpha parameter is y plus alpha 2, and n minus y plus beta 2. So imagine if I want to look at the risk difference, here the risk of side effects. P2 minus P1 is the parameter that I want, and it does, so here P1 is a bunch of posterior P1 simulations, P2 is a bunch of posterior P2 simulations. If I subtract them, R does it component by component, so I get a collection of 1,000 risk differences. I could plot the density of the risk differences in the next line. I could calculate the lower 25th and the upper 97.5th quantiles of these simulations to get a Bayesian credible interval for them. I could calculate the posterior mean, and I could calculate the posterior median. And in the next slide, you see exactly this. I have some R code called 2-binom post, which which is on the GitHub repository, but also will be on the I'll put on the course website. It puts out the mean, risk difference, relative risk, and odds ratio, the median for those three, the mode for those three, and equitail confidence intervals. Boy, what I mean by equitail confidence intervals, I mean is 25% in the lower tail and 2.5% in the lower tail and 2.5% in the upper tail, which I think we discussed for the one sample binomial case. We discussed that maybe it's better to not do equitail confidence intervals, but credible intervals. But in this case, it's easy enough to do it that way. So why don't we just do it that way? And go through the 2-binom post code. It's very simple to do this. And here, what I'm showing is the posterior for the risk difference. And this is what's nice about Bayesian intervals. So here, we're simulating P1 and P2 a posteriori. So we're getting the posterior joint, draws from the joint posterior distribution of P1 and P2. Any function of P1 and P2 that you then want to investigate, it becomes very easy to do. And so here I took the risk difference and plotted the density. I put some blue lines where the credible interval occurs, and the red line is identically at 0. And so you can see that 0 does lie within the credible interval. But you can also see with the posterior where the kind of what points are better supported by the data for the risk difference. And even though 0 is in our credible interval, it's not a terribly well supported value in the data. I should say it's not a terribly well supported value a posteriori. Well, that's the end of the lecture. That was a whirlwind tour of risk difference style intervals for 2 binomial proportions. I'm hoping at this point that a lot of these topics in the class will start to come very easily to you because we're just kind of using the same techniques over and over again. And I look forward to seeing you for the next lecture. Okay, hi troops. My name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp Lecture 5, where we're going to be talking about relative risks and odds ratios. So the goal of today is to talk about some relative measures like the odds ratio and the relative risk. And there's many reasons why you might want to consider a odds ratio or a relative measure rather than an absolute measure like a risk difference. So as an example, if you're considering comparing an event that's somewhat rare, so say for example if you're interested in whether or not some environmental effect causes a fairly rare disease, where you're comparing a small proportion of people who contract the disease among the unexposed group and a small proportion of people who contract the disease among the exposed group. And so it might be interesting to know that even though the absolute difference in rates is very small, the relative difference might be very large. So frequently we're interested in relative differences rather than absolute differences. And two particular in the case of proportions that are interesting are A, dividing the two proportions, that's the relative risk, and B, dividing the two associated odds, which is called the odds ratio for obvious reasons. Okay, so let's put some context on this where we use a data set similar to or exactly the same as we've used before. So consider a randomized trial where 40 subjects were randomized 20 each to two drugs with the same active ingredient but say different expedients. So one's a capsule and one's a tablet or something like that, let's say. So consider counting the number of subjects having side effects for each drug. So drug A had 11 people with side effects, 9 with none, 20 total. Drug B had 5 people with side effects, 15 with none, and 20 total, which left 16 total people with side effects, 14 with none, and 40 total. And the interest is whether drug A has a statistically higher percentage of side effects than drug B, accounting for what would be expected by chance. So let's look into that. So there's several ways to approach this problem. In fact, the 2-by table is a surprisingly complex set of 4 numbers. But we're going to approach it from the following way. We're going to assume that the count of the number of people with side effects from group 1 is binomial, with n1 equal to 20, and p1 a proportion that we'd like to know. And y, the proportion of the count of people with side effects from drug B, will also be binomial, with number of subjects n2, which is 20 in this case, and p2 being the proportion of people with side effects from that group. The obvious estimate of p1 is p1 hat, which is x over n1, and the obvious estimate of p2 hat is y over n2, of course. So we're going to use the following notation below in addition to the x and y notation. So x is the count for drug A, y is the count for drug B, and so on. But we'll also, given that it's a little 2-by-2 matrix, we can index the elements by I and j. So n11 is the upper left-hand cell, n21 is the lower left-hand cell, and so on. And then if we need a margin, a point that's fixed by the a point that aggregates over either rows or columns, we'll mark that with a plus. So n plus 1 means that we summed over the two first indices, and 1 plus would mean we summed over the two latter indices. Okay, so last time we considered absolute changes in proportions. But what about relative changes? And as I said, relative changes are often of interest. For example, when the proportions are small, you might have, in the example we were discussing earlier, a 10-fold change in the exposed group contracting the disease over the control group or the non-exposed group, but the absolute difference be very small, less than a fraction of 1%. And in that case, it's very natural to consider relative amounts rather than absolute amounts. Well, the most obvious thing to do in the case of proportions is to define the relative risk, which is simply just one of the proportions divided by the other. And then, of course, it doesn't matter which one you put in the numerator and which one you put in the denominator, as long as you remember what you did. So, and just to remind you, so we have P1 and P2 population parameters defined here because remember on the previous slide we actually talked about a model where our data, our IID draws from a population. There's other ways to think about this problem, but that's how we're going to think about it. Okay, so the obvious estimator of the relative risk is the estimated relative risk, which is P1 hat divided by P2 hat, which is of course just x over n1 divided by y over n2. So the relative risk is obviously, there's an issue if y has 0 counts, right? You're dividing by 0. So that's potentially a problem. But also, if we want to create an asymptotic confidence interval where we treat our data, our estimator as if it's normal, there's a problem that this is, of course, bounded from below by 0. And it turns out that the log relative risk, the log estimated relative risk, has much better asymptotic behavior, and the confidence interval looks a little bit better. So what people do is they say, okay, and often when you're working with ratios, we know already that it's very convenient to look at logs. So the log relative risk is just the log of this quantity here, x over n1, y over n2. And that quantity has an asymptotic standard error that you can calculate. And in fact, in one of the next lectures, one of the next 2 lectures or so, we'll show you exactly how to get this standard error. That standard error works out to be 1 minus p1 over p1n1 plus 1 minus p2 over p2n2, all raised to the 1/2 power. And that's the standard error of the log relative risk. So what you do to create a confidence interval for the relative risk is you log the estimated relative risk, you add and subtract a standard normal quantile, and then you multiply that standard normal quantile times this standard error of the log relative risk. That will give you a confidence interval for the log relative risk, and if you then want a confidence interval for the relative risk, you then exponentiate the endpoints. Okay, so we could equivalently take the ratio of odds instead of the ratio of probabilities if you prefer. There's a variety of reasons to do that, but one is maybe what if you just prefer to interpret things in terms of odds rather than probabilities anyway. Some people like to think about things in terms of odds, saying an odds of, say, 10 to 1 is more interpretable to them than saying a probability of 10/11ths. So the odds ratio, the population odds ratio, would just be p1 over 1 minus p1 divided by p2 over 1 minus p2. So the odds associated with probability 1 divided by the odds associated with probability 2. So this would be the ratio of the odds of contracting side effects comparing drug A to drug B. And of course, just like the relative risk, you'll be comparing the odds ratio to 1. If it's bigger than 1, it's going to suggest a greater propensity of side effects for drug A, and if it's less than 1, it's going to suggest a smaller propensity for side effects of drug A. And then, of course, the obvious estimate of the odds ratio is p1 hat divided by 1 minus p1 hat, p2 hat divided by 1 minus p2 hat. And you can plug in the x and n1 and y and n2 into that formula, and what you'll find is that it works out to be, if we go to our other notation where we talk about the cell counts, the n11, n22 times n21 times n12. And the easy way to remember that is its so-called cross-product ratio. So the product along the, let's see, when I'm recording, it's not, the product along that diagonal divided by the product along this other diagonal. And so that way you can always remember how to do it. Some people tend to, if you label the elements of the 2x2 table A, B, C, D, some people tend to remember it in terms of the specific letters. But I think it's probably better to remember it in terms of it's the product along one diagonal divided by the product along the other diagonal, the off diagonal. So just like for the relative risk, the odds ratio, the estimated odds ratio, has better asymptotic Gaussian behavior if you log it. So we can calculate a standard error for the log odds ratio that works out to be an incredibly convenient formula. It's the square root of 1 over all the cell counts added up. So 1 over n11 plus 1 over n12 plus 1 over n21 plus 1 over n22, square root of the whole thing. So you shouldn't forget the standard error of the log odds ratio because it's super easy. So again, to create a confidence interval for the population odds ratio, you calculate the odds ratio, log it, calculate the standard error of the log odds ratio, add or subtract a standard normal quantile, say 1.96 if you want a 95% confidence interval, to your log odds ratio, and that will give you an interval estimate for the log odds ratio, exponentiate the endpoints, and that gives you an interval estimate for the odds ratio. Now, again, we have a little bit of a problem if n12 or n21 is 0. And there's some fixes for that, often involving adding small amounts to every cell is a common fix. Okay, so some comments about the odds ratio. So one interesting fact is if you transpose, so the little 2x2 table is a matrix. If you transpose the matrix, so simply record it, in this case, we had side effects versus none labeled on the columns, I believe, and drug A versus drug B labeled along the rows. But what if we correctly entered in the data with side effects entered along the rows and drug A versus B entered along the columns, and then calculated an odds ratio? Well, you'll get identically the same number. So the odds ratio doesn't care what is the sort of predictor and what is the response. You get the same exact answer. And for both the odds ratio and the relative risk, taking logs helps with the adherence to the error rate. So again, because it's asymptotics, you don't necessarily, if you want a 95% confidence interval, you don't exactly get a 95% confidence interval because it's all based on the central limit theorem. It's only true in the limit. So the taking logs helps adherence to that error rate. And then the interval is just at log estimate, right, log odds ratio or log relative risk plus or minus the appropriate normal quantile, then times the standard error of the estimate. And then exponentiating yields the interval on the natural scale. And I would also add, though logging helps, these intervals still do have some issues. They're better than the risk difference, which I think they're better than the risk difference. But still, there's ways you can improve on these confidence intervals, but they involve a little bit more lengthy calculations, so we won't go over them. These are the quick versions. Okay, so let's go over our example next. Okay, so for the relative risk, our PA hat worked out to be 11 over 20, which is 0.55. PB hat worked out to be 5 over 20, which is 0.25. So the relative risk is 0.55 over 0.25 for just, I think it's probably a good habit to write that we're comparing A over B in the relative risk, just to remind ourselves what order we divided in. That works out to be 2.2. Quite a large difference, quite a large indication of a difference, but is it actually statistically significant? Is it something that would be of interest? That in the sense that it could be more than just a chance association. Okay, so let's calculate the standard error of the log relative risk. Here I plug into the formula, I get 0.44. The interval for the log relative risk is then log 2.2, log of our relative risk, plus or minus 1.96, the standard normal 97.5th quantile, times 0.44. That gives us negative 0.07 to 1.65. We're interested on the log scale in comparing whether or not this interval contains 0, and then if we were to exponentiate it back, the interval for the relative risk is 0.93 to 5.21, which again shows an indication that drug A has a greater propensity for side effects than drug B, but isn't exactly significant because this interval contains 1, and on the log scale the interval contains 0. Of course, because log is a monotonic function. If it contains 0 on the log scale, it will contain 1 on the natural scale, and vice versa. So whether you check for 0 on the log scale or 1 on the unlog scale will always yield the identical answer. Okay, let's go over the odds ratio. The odds ratio for A divided by B, well, let's just do this cross product formula. 11 times 15 divided by 9 times 5. That gives us 3.67. The standard error then is square root 1 over the addition of 1 over the cell counts. That works out to be 0.68. So the interval for the log odds ratio is log 3.67 plus or minus 1.96 times 0.68. That works out to be negative 0.4 to 2.64. The interval for the odds ratio is 0.96 to 14.01. Now, so this is on the natural scale. Okay, and then just to finish off our thinking about this problem, consider the risk difference as well. So the risk difference would be here. I think it's a good idea to put that you're subtracting A minus B there. PA hat minus PB hat. That works out to be 0.30. The standard error of the risk difference is given in this formula here. It works out to be 0.15, and the interval is again given here. There's issues with the risk difference formula. as well, and we covered some of that before, and showed that you can maybe improve on its performance a little bit by adding 1 to every cell, for example. And that was covered when we in the last lecture, I believe. And then the final thing I wanted to just show were 2 plots, just to finish some thoughts from the last lecture, where we talked about Bayesian analysis. So if you recall, if you look back to the last lecture, what we did was we postulated a prior for P1 and P2 that were independent beta priors. We found that if we did that, then we got independent beta posteriors for P1 and P2. We saw that an efficient way to explore the posterior was to do a simulation from it, and that would allow us to calculate things like the posterior mean, the posterior variance, and so on. So if you go back to that lecture, you'll hopefully be reminded of exactly what we did. When you conduct these posterior simulations, you get a PA and a PB, P1 and P2. You get lots and lots of pairs of those things that represent draws from the posterior distribution. And it's convenient to do that because it's just a convenient numerical way to investigate the posterior. If you take the arithmetic mean of those posterior draws, right? You would get the posterior mean for PA and the posterior mean for PB. You could get the posterior mean then for the risk difference, the posterior mean for the odds ratio by taking every pair PA and PB and calculating the odds ratio and so on. Well, here what I did is I calculated for every PA, PB pair simulated from the posterior. I then simply plotted a histogram of them. And this is just an approximation of the posterior, where the accuracy of the approximation only depends on how many Monte Carlo samples I elected for the computer to generate. So if I let the computer run for a really long time, I get a near perfect representation of the posterior. So in this case, it's the posterior for the risk ratio. So again, I took PA, divided it by PB, right? And then for all of those pairs, I plotted a density estimate, and there's the density. This gives you a lot of information about where the evidence concerning the risk ratio, the relative risk, lies. Here I drew the blue lines for the 95% credible interval, where there's 2.5% above either below the lower blue line and above the upper blue line, and then I put a reference line at 1 in this case. And as we saw when we calculated the confidence interval, the lower endpoint is just below 1, so that if you were sort of interested in something like significance, you wouldn't get significance. But I think the posterior displays a lot of information and does a lot, gives you a lot more than just a confidence interval or the result of a hypothesis test, or just even worse, giving the asterisks on how significant the p-value is, which some software does. Okay. And then on the next slide, what I'm showing here is the same exact calculation done for the odds ratio. So this is just to give you a flavor of what the sort of output or the desired output from a simple Bayesian analysis would be. The posterior is the quantity that you would use to investigate the relative proportions, either through the odds ratio or through the relative risk. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 6 on the delta method. So in this video, we're going to recap a little bit about the odds ratio, the relative risk, and these measures. And then I'm going to describe basically how you get the standard error and test statistics for these methods using this technique called the delta method. And then I'll briefly derive the delta method, but in a very general way, not in a highly technical way. Okay, so recall we had a setting where x was binomial, n1, p1, y was binomial, n2, p2, and then we could have this 2 by 2 table here as well. And we define the risk difference as the difference in the proportions. And this is because this is just an average, we can derive the standard error very quickly. We have the relative risk, which is p1 over p2, and the associated estimator, p1 hat over p2 hat. And we have the standard error of the log relative risk, which is given here. And it's not clear how we derive that yet. And then we have the odds ratio, which is the odds associated with group 1, p1 over 1 minus p1, divided by the odds associated with group 2, which is p2 over 1 minus p2. The associated estimate is p1 hat divided by 1 minus p1 hat, whole thing divided by p2 hat divided by 1 minus p2 hat. And if you were to plug in the elements, the cells of the 2 by 2 table into that estimate, you would see that it's the cross product ratio, the main diagonal n11 times n12 divided by the off diagonal n12 and n21. We also gave you the standard error for the log odds, the estimated standard error for the log odds ratio estimate, and that is square root of 1 over the cell entries from the 2 by 2 table. This 1 over n11 plus 1 over n12 plus 1 over n21 plus 1 over n22. And then in any of the cases, the confidence interval is the estimate plus or minus the normal quantile times the standard error of the estimate. Now, a couple of notes are in order. First, in terms of the risk difference, we saw that maybe we can improve on this confidence interval by adding to the cells in a particular way. So hopefully you can recall back to that lecture. In addition, for the two other estimates, the relative risk and the odds ratio, you have the issue that the estimate here is the log relative risk and the log odds ratio. You add and subtract z1 minus alpha over 2 times the standard error of the log estimate, and then if you want an estimate for the relative risk or odds ratio respectively, then you have to exponentiate the endpoints of the interval. Okay, so I hope you remember that as well. So this is our starting point, and during this lecture we're going to show you how to get these standard error estimates, or at least describe how they're obtained, and then hopefully you'll get a pretty good sense of how it's done and think very reasonably how it could apply far more broadly. Okay, so the delta method is a method that we can use to obtain standard errors for these instances where things aren't just a simple difference of averages or a simple average itself, like in the risk difference case, so like in the case of the log relative risk or the log odds ratio. So here's formally what the delta method states. It says that if you have an estimator, theta hat, and its estimand, theta, divided by the estimated standard error, if that tends to a normal 1 in distribution, then take a sufficiently smooth function f of theta hat, minus f of theta over f prime of theta hat times this standard error again, also converges to a normal 0, 1. So in a sense, what this is saying is sort of the asymptotic mean of f of theta hat is still f of theta. So if you want to estimate this function of theta, then the obvious estimate is f of theta hat. And this is saying that, well, maybe if we're going to use f of theta hat as an estimate of f of theta, we'd like a standard error. And it says, okay, we'll take the standard error that you would use if you weren't taking the function, standard error hat here of theta hat, and then simply multiply it times the derivative of f evaluated at theta hat. And that's what the delta method says. Okay, so let's go through an example. So theta, let's consider an instance where theta is p1. We're only going to consider x at this point. Our theta hat is p1 hat, x over n1. Our estimated standard error, right, the standard error for x over n1 is square root p1 hat 1 minus p1 hat over n1. I hope that's not news to anyone in this case. And let's assume the f we want to estimate is log. So we're interested in log p1, for example. So f of x in this case is log x. Then f prime of x is 1 over x, okay? And then we know that theta hat minus theta over its standard error, that tends to a standard normal by the ordinary central limit theorem. In this case, theta hat is a simple average, okay? And we're just simply subtracting off its mean and dividing by a consistent standard error, so it converges to a normal 0, 1 by the ordinary central limit theorem. So then it's saying that the standard error, the estimated standard error of the log of the sample proportion is f prime theta hat times standard error of theta hat. So let's go through that calculation. So f prime of theta hat in this case is f prime is 1 over its argument. So in this case, in theta hat is p1 hat. So it's 1 over p1 hat times the standard error, which is square root p1 hat 1 minus p1 hat over n1. Rearrange terms and you get square root 1 minus p1 hat divided by p1 hat divided by n1. And so what this is saying is that log p1 hat minus p1 divided by this standard error, square root 1 minus p1 hat over p1 hat times n1, that tends to a normal 0, 1. So if I want a confidence interval for p1 for log p1, what I could do is take log p1 hat and add and subtract a standard normal quantile, let's say 1.96 for a 95% interval, times this standard error here, square root 1 minus p1 hat over p1 hat n1 hat, and that would be an interval. And so that works out to be very convenient. The only complexity in this whole calculation, and it was very mild complexity, was calculating the derivative of the function that we're interested in. The rest of it was simple arithmetic, and that's why the delta method is so powerful. Okay, so that actually doesn't give us a standard error for the log relative risk. And honestly, to do that in its full glory, you need a multivariate version of the delta method, which there is, but we don't really cover it in this class. So let's look at the asymptotic standard error for the log relative risk. Let's just kind of heuristically do it. So the variance of the log relative risk is the variance of log p1 hat divided by p2 hat. And so let's just say, so that is the variance of log p1 hat plus the variance of log p2 hat, because we're assuming that x and y are independent. The group 1 and group 2 binomial counts are independent. And so this, from going from these first three statements, this variance to this variance to this second line here, these are all exact equalities. We haven't done anything. Now, if we were to use our delta method estimate of the variance for each of these things that we calculated on the previous page, then we get 1 minus p1 hat over p1 hat n1 plus 1 minus p2 hat over p2 hat n2. And if we square root that is exactly the standard variance estimate for the log relative risk that we gave at the beginning of the class. Okay, and so that's where it comes from. And you could do exactly the same thing for the odds ratio. And you may have to do a little bit of arithmetic to show that it works out to be 1 over n11 plus 1 over n12 and so on. But the same exact rule applies, and it's relatively easy to do. There's one small bit of fudging that we're doing here, in that we're saying that delta method variances add in the same way that random variable variances add, and that is the case. That is the case. If you work out the multivariate delta method, the delta method estimated variances of independent things works out to be the sum of their delta method estimated variances worked out independently. But for the purposes of the class, this is not an issue. I think hopefully what you can follow is that for the log relative risk works out to be, for the variance of the log relative risk, we work out to needing the variance of the two component parts, log p1 hat and log p2 hat, and that we can calculate those associated variances with the delta method. Now notice, the delta method doesn't just give you a standard error and a variance calculation. It also gives you the asymptotic normality, so that not only do you get the variance estimate, but you get the inference too. You get the actual confidence interval that you want to create as well, or the hypothesis test that you'd like to perform. So the delta method isn't just the standard error variance calculation. That's just the neat part of it. The rest of it, the delta method also tells you can put the whole thing together as a confidence interval estimate. So for my final thought on the delta method, I thought I'd just show you quickly why it works. And it's very easy. It's surprisingly easy to prove. Now we're going to do a heuristic here, but the actual full proof is just not that different. So let's assume you have a large sample size, and the delta method is an asymptotic technique, so we can assume there's a large sample size. And if theta hat is close to theta, all right, then f of theta hat minus f of theta over theta hat minus theta, well, that should be approximate to approximately close to f prime of theta hat. Now, why is that? Well, on the left-hand side here, as theta approaches theta hat or theta hat approaches theta, either way, this is just the definition of a derivative of f. Okay, that's if you're not familiar with it, just go look up the definition of a derivative. It's the change in the function divided by the change in the arguments as the change in the arguments goes to 0. So this is exactly just the derivative of f. Okay, and then here we're assuming that theta hat is close to theta because theta hat converges to theta. It's a consistent estimate. Okay, so this first line's true. And let's just assume we multiply both sides by theta hat minus theta and divide both sides by f prime of theta hat, and we get this left-hand expression here and this right-hand expression here. And then let's just suppose we divide both sides by the standard error, the estimated standard error. And then what you get is that the right-hand side is roughly equal to the left-hand side. And so since the right-hand side converges to a normal 0, 1, the left-hand side should similarly converge to a normal 0, 1. And it also kind of gives you the heuristic of kind of why it works. If we assume f is a smooth enough function, right, and we appropriately divide by the derivative, then we're really kind of estimating the same thing as theta minus theta hat, as provided theta hat is close to theta. And that's ultimately why it works. It's nothing other than an instance of applying the definition of differentiation. And if you want the formal proof, if you really want that kind of detail, incidentally, by the way, my office is, we're on a medical campus, and I'm right near the emergency room, which is probably why you constantly hear the sirens going by. So those are the ambulances going to the emergency room, in case you were wondering. So anyway, if you want to prove the mean value theorem identically, right, if you want to prove the delta method exactly, what you have to use is a thing called the mean value theorem, and then you get a very formal proof of it. This heuristic is just based on the definition of a derivative, but if you use the exact mean value theorem, then you get the full proof. And that's it. And so in case you're wondering where, how in the world do people pull out these crazy standard errors for the odds ratio and the relative risk? Where do these formulas come from? It's a surprisingly easy little argument involving this quantity, this concept called the delta method. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 7 on Fisher's exact test. So in this lecture, we're going to talk about Fisher's exact test. We're going to talk about the hypergeometric distribution, which plays a central role in Fisher's exact test. And we'll talk about some practical implementations. And then we'll talk about how you can execute Fisher's exact test using Monte Carlo. Fisher's exact test is a historically very famous test, and it's going to be one of the first instances where we're able to test equality of, say, binomial proportions using a formal exact test rather than relying on asymptotics. So what does exact mean? So Fisher's exact test is exact because it guarantees the alpha rate. So when you do a asymptotic test and you use the nominal type 1 error rate, say of 5%, if you, say, for example, calculate a 95% confidence interval for the risk difference and declare the difference in the proportions as being significant if the confidence interval for the difference doesn't include 0, that's a nice valid testing procedure. However, that doesn't guarantee you a 5% error rate. It only guarantees you a 5% error rate in the limit as the sample sizes go to infinity. Fisher's exact test, in contrast, guarantees you the 5% limit provided the IID assumptions are met for each of the two groups.
And the background on Fisher's exact test is that the famous example is that of the so-called lady tasting tea. And in this case, Fisher was at a party and there was a wager about whether or not a lady at the party could determine whether the cream had been put in place first or the milk had been put in place first into her tea. And Fisher devised a blinded experiment where he put tea in first for a couple of cups and put the milk in first for a couple of examples, and then had her declare which she thought was the case. So here's a kind of more medically oriented version of that. So here we had a chemical toxicant with 10 mice, and we treated 10 of them with this toxicant and we treated 5 of them with the toxicant and 5 with the control. And then here we have the counts of in each group of tumors versus in each group of treated versus control, what number had tumors. So here, just looking at this, 4 exposed to the toxicant received tumors, 2 controls received tumors out of 5 in both cases. So there's maybe some amount of indication that there's a difference, that the toxicant may have some association with the tumors, but we'd like to test that formally. And there's a lot of ways, there's actually a surprising number of ways you can wind up at Fisher's exact test. And so we're going to go through a particular development. So the way we're going to develop Fisher's exact test is we're going to assume that we have 2 binomials and we want to test equality of the proportions. When Fisher originally developed this test, it was quite interesting. So in our case, we're going to fix these margin, the 5 and the 5. So we have 5 treated and 5 control, and we're going to model the probability that a random mouse from this population of the treated mice has a tumor as having binomial probability P1 and similarly P2 for the controls. Fisher thought about this problem differently. He said, I know that let's just assume this was the tea tasting experiment, and he had randomized 5 cups to have the tea put in first and 5 cups to have the milk put in first. And he says, I know that these margins should be fixed. Then it would have made sense given that the lady guessing would also know that this margin was fixed. It would have made sense for her to fix the second margin. Instead of 6 and 4, she would force 5 and 5. So he wanted to create a procedure that would force both margins, right? And it turns out the Fisher's exact test constrains the margins, right? It looks at all tables matching the margins. That gave him the motivation for designing the test this way. So he looked at so-called hypergeometric distribution, which is a way in which we can characterize this table in terms of having fixed margins. Now, when we actually implement the test now, we don't have to have 5 and 5 on both margins the way Fisher was thinking about it, but he was analyzing a particular experiment in a particular way. But the result of Fisher's exact test is constraining both of these margins and then looking at what tables satisfy the margins. And we'll go through the formal mathematical development of the way in which we're thinking about Fisher's exact test. There's other ways, and maybe I'll allude to some more of them later on. Okay, on this slide, so imagine that we want to test that P1 equals P2, where P1 is the probability that a treated mouse has a tumor, and then P2 is the probability the control mouse has a tumor. And so we're going to want the null hypothesis that these are equal, which let's just call the common proportion P. And just as a matter of practicality, we can't use a normal distribution or a chi-square test because the sample size is small. But also, we don't have a specific value of P, which is taken care of in the chi-squared and the z-test. They figure out a way to do that using the asymptotics, but we want to use small sample distribution, but making the small sample distribution, using a small sample distribution is hard because we don't actually know this probability P. Okay, so one way to think about Fisher's exact test, what it's testing, is imagine if we were to create the observed data, or list out the observed data as the individual data points. So mouse 1 was treated and got a tumor. Mouse 2 was treated and got a tumor. Mouse 3 was treated and got a tumor. Mouse 4 was treated and got a tumor. Mouse 5 was treated and had no tumor. Mouse 6 was a control and got a tumor, and so on. Okay? What I'm going to do right now is go through another way to kind of develop Fisher's exact test. And it winds up with the same test. All these different developments yield the exact same test. So in this case, imagine if the treatment and control were randomized, and we wanted to explicitly use the randomization process in analyzing the data. So treatment and control were randomized. Treatment and control status were randomized. Well, then if the null hypothesis is true, then it should be exchangeable for any mouse whether or not it got a tumor as to whether or not it was from the treated group or the control group, right? There should be nothing outrageous about the particular collection of treated and control mice that we see, how they line up with the tumor and non-tumor statuses that we saw. So what we could do is take this top row and permute the treatment and control labels, right? Permute the T's and the C's. And we see the second row here is one example of a permutation. Okay? And the result of that is that the total number of treated and the total number of controls remain fixed, and the total number of tumors and the total number of non-tumors also remain fixed. And that's exactly maintaining the margins of the table. But this seems like kind of a reasonable null distribution to investigate, right? In other words, that treatment and control status is exchangeable relative to tumor status. So we'll look at some test statistic relative to this distribution. And the consequence of this is every time we permute treatment and control labels, if we were to reform the little 2x2 table we had, it would have the same margins. It would have 5 and 5 on the row margins and 6 and 4 on the column margins. And this is exactly one way to develop the null distribution for Fisher's exact test. And this is an interesting way to develop it because it explicitly uses the idea of randomization. There's more than one way to think about it. We could think about this rather than explicitly using the randomization. We could say, well, maybe treatment and control status weren't randomized. Maybe just the first 5 mice got the treatment, the latter 5 mice got the control. And we believe that there's no ordering effect, like there's no light that in the lab that only turned on for the first 5 mice causing tumors and not for the controls. So in that case, we might think of not the relabeling as a process of re-implementing the randomization scheme, but instead as a process of, well, we think if the null hypothesis is true, relative to tumor status, treatment and control status are a bunch of exchangeable, permutable labels, and that you could do the same procedure for coming up with a null distribution. And that's another way to think of it. Yet another way to think of it is the development that we're going to go through next, was a mathematical treatment. But it is interesting that these very different methods of thinking about the problem result in the same test. And you see this very often in statistics where you wind up with procedurally the same approach, but that the interpretation differs quite a bit. I would argue that explicitly using the randomization, saying, well, this treatment and control was randomized, and so we're going to explicitly work that into our analysis, is a very fundamentally different process than what we're about to do, which is to assume that the data are binomially distributed, i.e., impose a model, a superpopulation model for the mice, and to work with that and wind up with the same procedure, but the interpretation, I think, is vastly different, and I hope you think so too after taking this class. Okay, so let's go through our more mathematical development where we're assuming a model, right? So now, before, when we were talking about it as a randomization process, we were kind of conditioning on the data. We said, oh, well, you have so many treated, you have so many control, you have so many tumors and so many non-tumors, and we're simply redoing the randomization process on the computer under the hypothesis that the randomization was irrelevant, right? That whether you received the treatment or the control was irrelevant. And that's one way to think about Fisher's exact test. Now we're going to talk about a different way. So let's let X be the number of tumors for the treated and Y be the number of tumors for the control. And where our null hypothesis is going to be H naught P1 equal to P2 equal to the common proportion, where we're going to assume that X is binomial with whatever its sample size was and success probability P, and Y is binomial with whatever its sample size was and binomial probability P under the null hypothesis. Under the alternative, they would have different probabilities. By the way, if this is true, right? If this is true, if both X and Y are a bunch of IID Bernoulli sums, then X plus Y is just the sum of more Bernoullis, N1 plus N2 Bernoullis, all with a common success probability P. And so it's an interesting and fairly obvious fact that if you add two binomials with a common probability, that the sum of the two binomials is also binomial with the total number of trials equal to N1 plus N2 and the same probability. And this is clear because if X is comprised as a sum of N1 Bernoullis with probability P, and Y is comprised as the sum of N2 Bernoullis with probability P, then X plus Y is simply the sum of N1 plus N2 IID Bernoullis with probability P. Hence, it's binomial N1 plus N2 and P. So now, the way we've characterized the problem now, we have two numbers, X and Y, that are random. In our 2x2 table, there are no other free numbers, right? If we know X and we know N1, then we know the number of non-tumors for the treated group. If we know Y and we know N2, then we know the number of non-tumors for the control group. So in that 2x2 table, we know the margin, that with that N1 and N2. And then if we know X and Y, then we know the second, which is the first column of numbers, then we know the second column of numbers. So we only have two free numbers in our four numbers in our 2x2 table there. But we still have one parameter that we don't know even under the null hypothesis. The null hypothesis says H naught P1 equal to P2 equal to P, okay? So what if we were to then try and figure out a strategy to get rid of that parameter, find a distribution that doesn't depend on it, and it turns out that the probability of one of the data points given the sum, and it doesn't matter, we just pick the first data point, you get the same procedure if you pick the second one. Probability of X given X plus Y equals Z, it turns out that this follows the hypergeometric probability mass function, and I give the hypergeometric probability mass function right there. Now, what's interesting about this is this hypergeometric mass function is exactly the probability distribution from our couple of slides earlier, where we have so many bins of T's and N's, and we have so many balls labeled T and C for treated and control, and how if we randomly allocate treated and control balls to the bins, that, you know, the first bin being able to hold 6 balls and the latter bin being the end bin being able to only hold 4 balls, and I need to allocate 10 balls, 5 treated and 5 controls randomly to that process, to those bins. That's the hypergeometric. The other way to think about it is this idea that it is the distribution of the 2x2 table where you're permuting the T's and the C's, leaving the T's and the N's fixed in the way that we described earlier. Of course, that's identical to permuting the T's and the N's, leaving the T's and the C's fixed. So again, you wind up, if you have the same data and you assume that the row margins are the margins that include the randomized treatment, or if you assume the column margins are the margin that had the randomized treatment, you wind up with the same procedure, provided you have the same data set. So that's interesting. Perhaps comforting, perhaps discomforting. But either way, now before, remember, we only had two numbers. We had the two success probabilities, X and Y, or in this case it's a tumor, so I'd hardly call that successful, but let's say two success probabilities using the convention of calling a binomial event a success regardless of how successful it is. we have the two success probabilities at the onset. When we know the value of the sum, then we only have one left. So in that whole margin, when we assume we only had two free cells, given that the row margins were fixed. Now we only have one free cell, given that the row margins were fixed, and now that the sum is fixed. And so this is exactly what Fisher's exact test really tells you, is that as you vary that upper left-hand cell, or any cell holding both margins fixed, you get the remaining three elements. You can obviously put in a value for the upper left-hand cell, and you can obviously go through the exercise of finding the other three cells very easily given the margins. But more than that, we also have this distribution on that cell, the hypergeometry distribution that arises if we take the distribution of the upper left-hand cell and condition on the sum. Note that this distribution does not contain P. It got rid of it. And there's a mathematical reason for that. It's a so-called conditioning on a sufficient statistic. So when you condition on the sufficient statistics for P, you get rid of it. In this class, we won't go over that. We won't go over the mechanics of why. We won't go over the mechanics of the logic of how Fisher came up to condition on X plus Y, or how that mathematical development works. Suffice it to say, for the needs of this class, that when you condition on the sum, you do get rid of that probability, and there is a very general mathematical principle that relies on the fact that X plus Y is sufficient for the parameter P. Okay, so let's derive this conditional distribution. So we know the probability of X, it's just the binomial probability here. We know the probability Y, and let's say Z minus X. This will make the derivation a little bit easier, but we can plug in anything here, provided Z minus X is an integer between 0 and N2. Then it's this binomial probability right here. And then we said already that X plus Y is binomial, so the probability that X plus Y equals Z is this probability right here. Okay, now putting everything together, the probability X equals X and X plus Y equals Z over the probability X plus Y equals Z, that's exactly this conditional probability, just using our rules of conditional probabilities that we know quite well from Mathematical Biostatistics Bootcamp 1. And then if X equals X and X plus Y equals Z, then that's the same thing as saying X equals X and Y equals Z minus X, of course. And then X and Y are independent, so we can factor these two probabilities. And then on the previous slide, we had all three of these expressions plug in, and you'll find that you wind up with the hypergeometric distribution that we described before. Okay, so let's discuss it a little bit. So in this case, we have more tumors under the treated and control, so we at least have an indication, but we'd like some sort of inference associated with that. So let's see if we can get a p-value. But we're going to want to calculate an exact p-value, and our exact p-value is going to use this conditional distribution. The conditional distribution fixes both the row and the column totals, and we talked about when Fisher originally developed this test, he developed it wanting to fix the margins because he had assumed that the lady who was guessing would have known that he would have randomized equal numbers to T first and milk first, so he assumed that she would have fixed those margins as well. So that went into why he thought that way. And we talked about how this yields the same test regardless of whether the rows or the columns are fixed. And that the hypergeometric distribution, which we derived as a conditional distribution, is identical to the permutation distribution that we discussed, randomly permuting treatment and control labels if we were to string the data out as the full data set, not just as the 2x2 table. And so let's actually, all kind of versions of, all one-sided versions of Fisher's exact test yield the same inference. For two-sided, the way in which, so we have the null distribution, but we need a test statistic. And it turns out that, all test statistics are not equal in two-sided tests, but I'm going to give you the easiest one, but it doesn't exactly match what, say, for example, R does, or exactly what was in Fisher's original version.
I just want you to be aware of that. Okay, so let's consider our example from before, where now we're testing that the tumor probability for the treated mice is higher than the tumor probability for the control mice. So the p-value would just require tables as or more extreme under the alternative than the one observed. Well, and recall we're fixing the margin totals, and the observed table was 4213. A more extreme table would be if not just 4 mice got tumors from the treated group, but if 5 did, right? So if we plug in 5, then we know this cell has to be 0, this cell has to be 1, and this cell has to be 4 because we're fixing the margins. And we can't find another more extreme table because if we were to say put a 6 in there, then that would have to be -1 instead of 0, which can't happen. So there's only one table that's more extreme that honors the margins. Okay, so plugging into the hypergeometric distribution, we get 0.238 for the observed table and 0.024 for the other table. And so the p-value, the probability, the conditional probability of obtaining a table as or more extreme in favor of the alternative than was observed is 0.238 plus 0.024, which works out to be 0.262. So as you can see, and you probably guessed, is in this data set, the only way we could have gotten a 5% significant test is with the most extreme table. And that's, part of the consequence of, exact testing of these tests, and it can be shown that these tests will guarantee the error rate, but only guarantee that the error rate is at most, say, 5%. Let's say you compare this p-value to 5%. It does not guarantee that the error rate is exactly 5%. You can't do that because the data is discrete and there's only so many probabilities available to the p-value. There was an effort at one point to introduce supplemental randomization to try and get truly exact p-values that not only honored the 5% level, but gave you exactly a 5% error rate. But no one is very few people are willing to accept that as a solution, where things not in your data yield have important consequences to the inference. So I think what you wind up having to do is, if your analysis demands an exact small sample test, then you just have to deal with the fact that these small sample tests tend to be a little bit conservative. I would say there's also another strategy that comes up too. That's pretty good. What some people will do is they'll calculate the so-called mid p-value. So they'll only attach half weight to the observed table. And that p-value is somewhere in between, of course, the observed table and the strictly conservative p-value and other strategies. But of course, it's no longer exact. So I figure if you want an exact test, do an exact test. And in this data set, for example, the only way you could reject is if you got the most extreme table. Okay, so let me just show you briefly how to do this in R. Matrix C4123, 2. We'll just create the matrix, type it in, and you'll see, type dat after you've assigned this matrix to it to double check. And there's a function in the stat package, I think, of R, which comes with the base installation of R, of Fisher.test. And you just do Fisher.test of a little 2x2 matrix. In this case, we say alternative is greater. Let's see, we get 0.2619, which is what we calculated when we did it directly. And it gives you all the information. It gives you an odds ratio estimate and a confidence interval, which in a subsequent lecture will show you exactly how they calculate this confidence interval. Or at least we'll give the intuition behind it. It uses the so-called non-central hypergeometric distribution. Okay, so that's pretty easy to do. Okay, so the two-sided p-value is a little bit hard. There's other ways to do it, and R uses another way. And, well, I'll describe them. But right now I'm saying for the easy thing is calculate double the one-sided p-value, the smaller of the two one-sided p-values.
You have to double, it makes, I mean, it's easy to remember which p-value, which of the two one-sided p-values you double, because if you double the larger of the two one-sided p-values, you wind up with a p-value bigger than 1 usually, or always, I think. And so you've done something wrong then. So the two-sided p-value, you double the smaller of the one-sided p-values. That mirrors exactly what we do in normal test and t-test and that sort of thing. So what Fisher did initially was the other strategy for creating a two-sided test is you need a two-sided test statistic, a test statistic that measures whether a table is as or more extreme than the observed table. So one example would you could do the chi-squared statistic. So you could calculate the chi-squared statistic of your observed data, and then calculate the hypergeometric probability for every 2x2 table satisfying the margins, and then add up the probabilities associated with those tables with a chi-squared statistic bigger, i.e. more in favor of the alternative, than the observed table. That's one example. And that's fine. That you could do that, right? So you could, given the information I've given you, you should be able to do that. You should be able to do it with any statistic that measures the direction of the alternative. Of course, so you might say, well, how do you pick a statistic in this case? Since you can do any one, right? Because you can calculate the associated hypergeometric probabilities of every table, you can calculate the associated statistics, then summing up the probabilities for those tables with statistics more extreme than the observed in favor of the alternative is easy. But what's conceptually hard is then picking the statistic. The problem being that there is no uniformly optimal statistic in this setting. There is no so-called uniformly most powerful statistics. So there's a trade-off of power for when you do statistics and for which statistic you choose and its properties, which is too bad, but it is what it is. There's no solution. You can work out for a given data set what constitutes. You can work out basically every statistic for a given data set and convince yourself that there is no uniformly most powerful solution. There's merely trade-offs. I should talk a little bit about what Fisher did in this case. So Fisher's statistic was really interesting. Fisher's statistic was the hypergeometric probabilities themselves. Okay, so when he did the test, he would calculate the probability, the hypergeometric probability, were both the statistics and the probabilities. So he would add up, he would calculate all tables that satisfied the margins and calculate every hypergeometric probability. And every table that had a hypergeometric probability smaller than the observed hypergeometric probability, he added all of those up plus the hypergeometric probability of the observed table, and that was his p-value. So what he's doing then is he's using the hypergeometric probability as the test statistic, because as we just talked about, you use anything as a test statistic. Any function of the table is a test statistic, and certainly the hypergeometric probabilities are a function of the table. His logic went something like this. If something arose out of not the null distribution, but out of the alternative distribution, then those tables would have a low probability under the null distribution. So he used that logic to say, okay, well, the probability under the null distribution is a reasonable test statistic. And that was his logic. Fisher was a smart guy. Okay, so p-values are usually large for small n is the second point. What do I mean by that when I wrote that? Yeah, that's a poor way to put it, but what I mean is the discreteness of the problem usually dictates that you wind up with a large p-value. For example, here we have the second most extreme table we could possibly obtain, and our p-value is 26%. That's a consequence of A, the discreteness, and B, demanding a exact test. It is what it is. So the Fisher's exact test doesn't distinguish between the rows and the columns. Transpose the table, you get the same p-value out. The common p under the null hypothesis is called a nuisance parameter. So the procedure that we're doing to get rid of it is called eliminating nuisance parameters. And conditioning on the total number of successes eliminates the nuisance parameters. And we're going to go through a couple more examples of this throughout the class, of conditioning on a sum or something like that to get rid of a nuisance parameter. And then Fisher's exact test guarantees the type 1 error rate, but it doesn't guarantee it's obtained exactly. It only guarantees that it's obtained as a bound. And there's a great fight that occurred in statistics. You might not think statistics nerd fights are fun, but I do. And there was an extremely hard-fought series of papers between Fisher and several other people about this procedure. And there was another procedure called an exact unconditional test. And the inventor of this, Barnard, who later I think came around to Fisher's way of thinking about things, said, well, why don't we calculate, say, for example, the probability of getting a proportion of tumors in the treated bigger than the proportion of tumors in the control. We can calculate that. It does depend on this. We can calculate that under the null hypothesis if we knew this common proportion, right? Then it's just a bunch of binomials, and sure, maybe it's tedious, but we could do it. And he says, okay, well, we have this probability for any given p. That's our p-value. Why not then just take the worst case version of p, right? The largest version of the p-value, and call it a day. It's super simple to describe. And that procedure in some cases has better power than Fisher's exact test. I think the math stat people find it conceptually maybe I think conceptually people tend to like Fisher's exact test, but I like the unconditional test too. It has a lot of logic to it, I think, in terms of, it's very simple, right? It's a lot easier to describe. The idea of conditioning is very hard to describe. I would say, however, the randomization idea and permutation idea of Fisher's exact test is very compelling. And so why don't we actually, at any rate, Barnard's test is interesting. You can read up about it. You can read about how they fought over it for decades. Very fun literature. If you go back to the biggest names of statistics from before the say 50s or 60s, they all weighed in on this problem. And if you get far enough into the world of statistics, it's an incredibly fun literature to read. Okay, last slide. I want to just expand on this idea of how you can, especially because we can generalize this idea to not just 2x2 tables. In the observed table, x equals 4, and the observed treatment was T, 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 5 T's, and then 5 C's, and the observed tumors were like that. And you could do this little collection of 2x2 tables. And say, for example, in R, if you had the data coded in this way, you could do table, and it would just give you the observed data. Okay, so one thing you could do is you could permute the treatment labels, and that is exactly the hypergeometric distribution. So you could do a Monte Carlo version of calculating this hypergeometric p-value. Of course, we don't need to, but I'm introducing it because later on in the class we'll do it in cases where it's hard to calculate the p-value analytically. And you could, in this case, we simulated a table and we got x equals 3, and we just do this over and over and over again and calculate the proportion of tables for which the simulated tables have an x bigger than or equal to 4, i.e. have evidence as or more extreme in favor of the alternative. And this is just a Monte Carlo estimate of Fisher's exact p-value. This is exactly a simulation process to give us this hypergeometric probability that we could calculate by hand. In the future, we're going to have harder problems where we'll need to do Monte Carlo to do it because there's no way to do it by hand. And that's the end of today's lecture, and next time we'll keep working on contingency tables. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 8 on chi-squared test. Okay, so specifically when we talk about chi-squared testing, there's lots of different variations of chi-squared testing. Here we're going to be talking about chi-squared testing for contingency tables. And the most classic contingency table test is testing independence. We'll relate that to testing independence of several proportions. We'll go through the natural generalizations to higher order contingency tables. And then we'll talk about Monte Carlo variations to get exact test of independence. We'll finish it off with a discussion of goodness of fit testing, which is a special kind of contingency table test that's useful for testing whether or not data arrive from a particular distribution. Okay, so we've talked about testing in a 2x2 table equality of two proportions, say binomial proportions. And an alternative approach to doing this is so-called chi-squared testing. And the form for all the chi-squared tests is the same. It's the summation of the observed data, the observed cell counts, minus the expected cell counts, and I'll talk about what that means later, squared divided by the expected. And we'll talk about where the motivation for this formula comes from as well. So here the observed are the observed counts, the expected are the expected counts under the null hypothesis, and the sum is over all of the cells of contingency table, successes and failures. And in the 2x2 table test for testing equality proportions, this winds up being a chi-squared. This distribution under the null hypothesis has a chi-squared distribution with 1 degree of freedom. And it turns out that, maybe I'll assign this somehow as a homework, the chi-square test is exactly the square of the difference in proportion score statistic where you have the common proportion in the denominator for the standard error. And notice notice basically the statistic is a distance. It's the distance between the observed cell counts and what you would expect to get under the model. But notice it's squared, so there's no directionality. It's just whether things are kind of different than what you would expect to see under the model. So under the model, under the null hypothesis. So it doesn't test directionality. It doesn't test whether it tests. It's effectively it's a not equal to hypothesis always. So let's go back to our familiar example where we had a treatment. Here the treatment is X and Y. Let's say X is the treatment and Y is the placebo. Probably more accurately, let's suppose we're comparing two equally effective treatments and we want to see if one has more side effects than the other. So X and Y are two different treatments and we want to determine whether or not one has more side effects. Here we assigned 100 people to X and 120 people to Y, and we're going to treat the binomial, the counts of the number of people with side effects out of the total as if they were binomial. That will be our model. Okay, and here are the rates of side effects in the two proportions, P1 for X and P2 for Y, and we're interested in whether P1 equals P2. Okay, let's see if we can logic our way through implementing this formula. So the chi-squared statistic I've said is the summation of the observed counts minus the expected over the squared over the expected. Well, part of it's easy, right? The observed counts, 011, 021, 012, and 022, if we label the cells of the rows and columns of the 2x2 table that way, then we have those, 44, 77, 56, and 43. Now, what about the expected counts? Well, let's kind of think this through. Okay, if the rate of side effects was the same for the two groups, for the two treatments, then our estimate of the common proportion, just like in the denominator of the score statistic, would have to be 121 over 220, right? And now we don't know that, so let's use that as our best estimate as for the overall proportion of side effects, regardless of treatment, because under the null hypothesis, the proportion or the true proportions are assumed equal. So that's our estimate of that. And then how many people would we expect to see with the side effects? Well, if that's the estimate of this common proportion, then 100 times that would be, we would expect to see 55. And so on. And then you go through it, we would expect to see out of the 120 receiving the second treatment, we would expect to see 120 times this proportion, or 66. I'm rounding here. The expected counts, by the way, don't have to be integers. They shouldn't be integers. You should carry out the calculations to, you know, to many decimal places. I just
I don't know why I rounded them. I think for didactic reasons I rounded them up for integers here. But in general, the expected counts do not have to be integers in the same way the observed counts must be integers. So anyway, just to remind you, you want to carry these calculations out, not just round them at 55. Okay, and so on, and then 1 minus this probability is then 99 over 220, and that's how many non-side effects we would, times 145 is how many non-side effects we would expect in the X treatment, and 99 times 120 or 54 is what we would expect in the Y treatment. So these counts here on the right-hand side represent what we would expect to see under the null hypothesis using our best estimate for the common proportion. So the margins, the 100 and 120, are fixed by the design, and the best estimate of our common proportion is that one. So this is kind of our best guess is what we would expect to see. And if these counts are very different from the observed counts, then that would shed some light maybe that the null hypothesis is not true. Okay, so then our test statistic is 44 minus 55 squared over 55, and so on. Add all those up, and that turns out to be 8.96. Compare that to a chi-squared with 1 degree of freedom, and again we're rejecting for large values, right? Because this is the distance between the observed and the expected counts. We favor the alternative the further away from the expected counts we are, so the bigger the test statistic is going to favor the alternative, so we're going to reject for large values. So let's do p chi-squared 8.96. It's 1 degree of freedom when you have a 2 by 2 table, and we'll give you a general rule for when you don't have a 2 by 2 table. And we say lower tail equals false because we want the upper probability, not the lower probability. The result is 0.002. The other way you can think about this, of course, is a chi-squared with 1 degree of freedom is actually the square of a standard normal. So it's unlikely for a standard normal to be above 2 or below -2, right? There's only a 5% chance of that happening. So chi-squared, it's unlikely going to be above 4, right? The square of 2 and the square of -2. That's going to have about 5% probability. So a chi-squared of about 4 is about the same benchmark as a normal of about 2. A chi-squared of about 9 is the same as a normal for a standard normal for about 3. Again, remembering that you're testing both bigger than 2 and less than 2, or bigger than 3 and less than 3, because remember the chi-squared is always does a two-sided test. So in this case, the result is 0.002. There is some evidence to suggest that there is a difference in the rate of side effects between the two treatments. Though, of course, the result of the chi-squared test doesn't tell you which direction it goes. Okay, so that's how we do it. And here's some simple R code for executing it in R, so you don't have to do the calculations with a calculator. So we just create a data matrix. It's this matrix command here, and then chi-sq.testdat. And then you'll notice if you do this, you don't get exactly the same test statistic that we got. And the reason is because the chi-squared approximation, it's an asymptotic approximation, but the counts are discrete, and you can improve the chi-squared approximation by fudging a little bit, in the way in a way that kind of, if you're doing kind of numerical integration with boxes, you can maybe do a little bit better with trapezoids or something like that. It's along that line of thinking, and that boils down to adding a little bit to every cell, and that's called a continuity correction, basically accounting for the fact that the cell counts are counts, and it can improve on the asymptotic approximation. So if you actually put in correct equals false, it won't do that continuity correction. You'll see, then you'll get the exact answer, same answer that we did. You do want to do so for didactic purposes, we're not presenting the continuity correction, but when you actually do the test, you want to leave correct equals true on there because it does yield a better approximation. That's why it's the default in R. Okay, so let's recap. We're going to reject if the chi-squared statistic is too large or is large. The alternative is always two-sided. You're always comparing whether the proportions are different. You do not divide your alpha by 2 even though it is a two-sided test. Remember, we're dividing the reason we're dividing the alpha by 2
in the standard Gaussian cases, because you're checking bigger than, you're checking less than, because we've squared the statistic and the chi-squared is only a positive statistic, we don't need to do that alpha divided by 2 for the quantile. A small chi-squared statistic implies little difference between the observed values and those expected under H0, so it supports H0. You could think of the chi-squared statistic as actually a distance. And then what we'll talk about, and it's really kind of a fun subject, I think, the chi-squared statistic and approach generalizes to other kinds of tests and larger contingency tables. And it's also one of these phenomenons that often occurs in statistics where the same procedure arises out of several different settings and data structures. And so the interpretation changes, but the actual procedure stays the same. And we'll go through another one next, where we think about this problem in a different way and we wind up with an identical procedure. And that happens a lot in statistics, where even though you think about the problem in a different way, you get the same procedure. The mean is frequently a good estimator, even if the data is IID exponential or IID normal, it's going to estimate the mean of the data well. And so the mean pops up all over the place. Well, the same sort of thing happens in chi-squared testing, where you get kind of equivalencies despite very different sampling strategies and assumptions underlying the data. Anyway, there's a neat computational form in the 2x2 case. It looks like this, where I'll have the notation on the next slide, but where here the nij's are the cell counts, and you put a little plus in front of an index if you're summing over that cell. So these are the margins. And here briefly is the notation I'm going to be using, where ij indexes cell count. I'll call n+1, meaning summing over the first index, so that's this margin, n+2 is this margin, n1+ is this margin, n2+ is this margin. And if I need to refer to n1 and n2, let's say those are the row margins, and then n will be the sum, this corner cell right here, the sum of the total number of observations. So, kind of an interesting fact about the chi-squared statistic, if you look at it, if you transpose the table, the statistics doesn't actually change its value, which is kind of interesting, right? It means it doesn't care about which margin is sort of fixed by the study design. It doesn't care about that, and if you errantly were thinking of side effects as being the outcome, you get the same thing as if you were thinking about which treatment they received was the outcome. You wind up with the same test, and only one of them's the correct way in which the experiment was conducted. So that's interesting, and it ties into its utility. Then ties into a lot of these instances where you really want to play around with the interpretation of the what variable is the outcome and what variable is the predictor, and we'll talk about that when we talk about case control studies. It's interesting that in case control studies, some of the fundamental work was done right here at Hopkins by a person named Cornfield. At any rate, the chi-squared statistic, it can arise. You can state a model for which the chi-squared statistic is kind of the obvious thing to do. If the rows are fixed, so you have binomial. You can do it if the columns are fixed, which is just maybe a different kind of binomial. If you're, again, here we're assuming binomialness of the data in either of these cases. But let's imagine if you didn't assume that the data were binomial, that the rows or columns are fixed. Let's say you assume that only the total sample size is fixed. So imagine, as an example of that, you collected, instead of randomly assigning 100 people to receive the treatment and randomly assigning 120 of the other people to receive the other treatment, imagine if you just happened to go out and collect a bunch of people and ask them what treatment they had and ask them whether or not they had side effects. Now, granted, it's a different experiment. The way in which you would interpret the result of a chi-squared test would be different, but there, you might think, oh, well, I sampled 220 people. That was really the part that was fixed by the design, and however people fell out in terms of side effects and And treatment, well, that's part of the randomness, and so I'm going to model that whole thing as if they were multinomial with 4 possible things. They could be taking treatment X with no side effects, treatment X with side effects, treatment Y with no side effects, treatment Y with side effects. I think I hit all 4, but you see what I mean. There's 4 possible elements in a 2x2 table. So in that case, it wasn't it wasn't fixed, but and I'll go through it right now. But you wind up with the same exact test statistic. You wind up with the same exact test statistic and chi-squared result if you assume multinomialness and a specific null hypothesis, namely a test of independence. So I find that cool. And that's why often people are a little bit loosey-goosey about their assumptions in multinomial settings because they kind of apply in different ways. And I do think there's a lot of problem with that because yes, the number of that comes out from the test statistic is the same, but it doesn't. The interpretation is very different. Different experiments lead to very different interpretations of the assumptions. In my example I just gave you, in one case we randomized a treatment, or in my fictitious case that I'm making up, in one case we randomized the treatment, and in the other case we just went out and sampled people observationally. Those are very different interpretations. I think most people would agree that the randomization would kind of average over confounding effects and other things that unobserved variables, where in the observational case that wouldn't necessarily be the case. So consider this next example where I took this modified a little bit from Agresti's wonderful book on categorical data analysis. So here we're looking at birth weight cross-classified by baby's birth weight cross-classified by maternal age, and so let's assume that the way in which it was sampled is there was, say, 400 people sampled, so that by design neither of the two margins were fixed. And we're kind of interested then in treating the cell counts as if they were multinomial, a 4-dimensional multinomial count with n equal to 400 total total observations. And then what we would like to know is if the variable birth weight is independent of maternal age versus the variable birth weight is not independent. So let's think about the problem this way and then see if we can logic our way to the expected cell counts. Okay? Okay, so let's first note that under the not necessarily even just under the null hypothesis, just regardless, our estimate of young maternal age is always going to be 100 over 400, and older maternal age will be 300 over 400, the margins of the table where we disregarded birth weight. And the same thing for birth weight, disregarding maternal age, would be 50 over 400, and then normal birth weight would be 350 over 400. Okay? And the cell probabilities would then give you the specific, combined probabilities. If we want to talk about younger maternal age and lower birth weight, that would be this, our estimate of this, regardless of the hypothesis, or under the alternative hypothesis, would be 20 over 400. But if we're under the null hypothesis, we're assuming maternal birth weight and maternal age and birth weight are independent, then we would kind of logically construct this probability as the multiple of these two marginal probabilities, because we're probably estimating the margins a little bit better. So that would be 0.25 times 0.125 here, because we're multiplying the marginal probability of young maternal age times the marginal probability of low birth weight. Okay? So we can only do that under the null hypothesis. So let's work on our expected counts. So our expected counts for the 1,1 cell of low birth weight and young maternal age is this probability. Then the number of counts we would expect in there is times the 400 sample size, and we get 12.5 as our expected counts. And then you can follow through for all the other 3 remaining cells in the same way and get the expected counts. and then compare them using the same formula, observed minus expected squared over expected, and we get our chi-squared statistic, which in this case is 6.86. We again compare it to a chi-squared critical value, which is around 4. Of course, we talked about it being the square of the z-statistic, so that makes sense that it would be around 4. Or we could just calculate our chi-square p-value, which would be the probability of getting a test statistic as large as 6.86 or larger. So I hope everyone can follow these calculations. And the idea is that we're basically calculating how distant our observed counts are from kind of our best estimate of what we would expect the counts to be under the hypothesis, under the null hypothesis of independence between the row and column variables. I should also add, before I complete this slide, that the answer we get from this test of independence is identical to the answer we get from the test of proportions. You get the same chi-squared value, the same p-value. Now the interpretation might be very different, as we talked about before. If in one case there was randomization as to which of the rows you lied in, versus in this case if it was a multinomial sample, the interpretation of the results dramatically different, and we don't really cover a lot of things like epidemiological style sampling designs in this class, but suffice it to say the interpretations can be very different, but nonetheless the actual number, the p-value we see is identical depending on identical regardless of which of the sets of assumptions you make. So that's interesting, and what's even more interesting is that you can formulate Poisson models that then again yield the same conclusions. So here's another example from Agreste's categorical data analysis book. Which is a book I highly recommend. I think it's a real classic in the area. But I should disclose a conflict of interest that Agreste is a great friend and close colleague of mine. Any rate, so in this example, he is looking at a different collection of occupations and cross-classifying it by alcohol use. So suppose the investigators in this trial or in this study, went out and found 300 clergy, 250 educators, 300 executives, and 350 retailers, and then asked them a question about their alcohol use. And we'd like to know whether alcohol use differs by occupation. So interest then lies in testing whether or not the proportion of high alcohol use is the same in the 4 occupations. So if we label P1, the clergy, the proportion of high alcohol use among the clergy, and so on, we want to test whether they're all equal, but we don't want to specify what proportion that is. So we, let's say P is the common proportion across all occupations, and then the alternative would be the opposite of that at least 2 are unequal. So our estimate of P, this common unknown proportion, that obvious estimate of it would be 233 over 1200, and the obvious then, and then of course the estimate of 1 minus P would be 967 over 1200. So our observed first count is 32. What would be our expected first count? Well, our estimate, if under the null hypothesis where occupation is irrelevant, we expect about 233 over 1200 percentage to be high alcohol users. So we multiply that times the row count, 300, and we would get the observed cell count. Then the low alcohol usage, 268. They have to, these have to add up to the margins. By the way, both the observed and the expected counts have to add up to the margins. So you could, take 300 minus the 1 cell count to get it, but otherwise you could just say 300 times the probability of low alcohol usage, which is then 1 minus 233 over 1200 or 967 over 1200. And you would repeat that down and down for each occupation. Calculate our chi-squared statistic, observed minus expected squared over expected, sum over all of them, you get 20, 20.6. and we need to compare it to a chi-square critical value, but the degrees of freedom change. And it turns out that the general rule for the degrees of freedom for the chi-squared in these settings is rows minus 1 times columns minus 1. So in this case, there's 1, 2, 3, 4 rows and 2 columns, so the degrees of freedom is 3. So then here's our p-value of p chi-squared, 20.59, 3 degrees of freedom, lower tail equals false. It's about 0. It's pretty clear that some of them are different. Okay, here's another example, and we're going to do. So this is from Rice's book, Mathematical Statistics and Data Analysis, which is another. First of all, I have no affiliation and never met Rice, so it's easier for me to say this, but I love this book. I think it's wonderful, this Mathematical Statistics and Data Analysis book. So if you're looking for a book recommendation, I like that one. In addition, I really like Agresti's book, but I'm willing to stipulate my conflict of interest in recommending it, but I do really like it. I read it all the time. So anyway, in this book, he had this interesting example where he had a bunch of words taken from some novels that were where one of them was purported, where two of them were known to be Jane Austen novels, and one of them was in question as to whether or not it was from written by that author. Let's say they found it later. And there's maybe other ways you would want to analyze this data for this reason, but we want to use it as an example for the chi-squared. So don't think too hard about specifically how you would analyze this data, because I doubt this would be what you would arrive at immediately. But it's not unsensible, by the way. It's reasonable. So imagine, let's say, book 3. I'm just spitballing here. Imagine book 3 is this book where you don't know whether or not it's from the same author. In this case, it was Jane Austen. And you want to test whether the word distribution of these words is equivalent across the 3 books, and you sampled so many words from each of the books. Okay, so that's the setting, and let's see if we can figure out some expected cell counts to do a chi-square test. Okay, here's another example, and we're going to do. So this is from Rice's book, Mathematical Statistics and Data Analysis, which is another. First of all, I have no affiliation and never met Rice, so it's easier for me to say this, but I love this book. I think it's wonderful, this Mathematical Statistics and Data Analysis book. So if you're looking for a book recommendation, I like that one. In addition, I really like Agresti's book, but I'm willing to stipulate my conflict of interest in recommending it, but I do really like it. I read it all the time. So anyway, in this book, he had this interesting example where he had a bunch of words taken from some novels that were where one of them was purported, where two of them were known to be Jane Austen novels, and one of them was in question as to whether or not it was from written by that author. Let's say they found it later. And there's maybe other ways you would want to analyze this data for this reason, but we want to use it as an example for the chi-squared. So don't think too hard about specifically how you would analyze this data, because I doubt this would be what you would arrive at immediately. But it's not unsensible, by the way. It's reasonable. So imagine, let's say, book 3. I'm just spitballing here. Imagine book 3 is this book where you don't know whether or not it's from the same author. In this case, it was Jane Austen. And you want to test whether the word distribution of these words is equivalent across the 3 books, and you sampled so many words from each of the books. Okay, so that's the setting, and let's see if we can figure out some expected cell counts to do a chi-square test. Okay, so our null hypothesis is that the distribution of these words is the same for every book, and that at least 2 are different. So in this case, we have kind of a multinomial for every column that we're interested in. We want to test equivalence of those multinomial probabilities across the columns. Okay, so if the book was irrelevant, we would look at these row margins,
and would say the word A should appear roughly 434 over 1017 times. Okay? So our 1-1 cell was 147, but in that book there were 375 words of this type that were sampled, and we're multiplying them times what we would expect to see of that word if book were irrelevant, and that's 434 over 1017, and that's how you get that expected cell count. Follow through, take the observed 1-2 cell. Now that's how many times the word A appeared in book 2. It came up 186 times. How many would we expect out of 440 words from our estimate viewing book is irrelevant? That would be 434 over 117 times 440, and you would compare that then to 186 to see how much the observed count deviates from the expected count. Now then you would move on to the next word, Anne, right? So Anne was disregarding book, seen 62 out of 1017 words, and so we would take 375 and multiply it times 62 times divided by 1017 and compare that to 25 to see if the number of ands in book 1 was different than what we'd expect. And so on. And you can go through all the calculations, and the sum of the observed minus expected squared over expected is 12.27. Degrees of freedom are 6 minus 1 times 3 minus 1 in this case, working out to be 10. Now again, and now at this point I would ask you as an exercise to figure out what the chi-squared probability is, the chi-squared p-value is based on 10 degrees of freedom using R. Now I should make some comments about sampling assumptions and these sorts of things about how the reasonableness of modeling the words this way. But this goes without saying. In all of these problems, we're making assumptions on how the experiment was conducted and that the model that we're applying is relevant. So in this case, you could probably say, yeah, that's not so bad about sampling assumptions. If you if you were to make some, assume that there's lots of words in the book. We're only sampling 300 or so of these very generic words, so that we could so that modeling that process as multinomial, that doesn't seem so bad to me, at least, assuming that's how the experiment was conducted. But you always want to think about that. How does what I'm doing, so the chi-squared test, how does its assumptions accurately reflect the way in which the experiment was conducted? Anyone can, of course, just take a table, click some buttons, and get a p-value, but that p-value is supposed to represent a probability. That probability is supposed to quantify the randomness in the experiment, and that randomness is only that is only being modeled through, or that's only being quantified through this statistical model, and so our results are only meaningful insofar as that model is a meaningful reflection of reality. Okay, so here's kind of a funny one. I also got this from Agreste's book. Both these books have lots of wonderful discussions of contingency table stuff. So in this case, they were rating couples, husband and wife's ratings of sexual fun. So N was never, F was fairly often, V was very often, A was almost always. And so let's say they sampled 91 couples, and then they cross-classified them. And let's talk about in this case, kind of the logical way, the logical or a logical first question to ask would be, are the ratings independent of one another? Is the wife's rating independent of the husband's rating, and so on? And so you can make all the relevant jokes about the experiment at home right now while we move on. Okay, so now in this point, we're going to talk about that the ratings between the row variable, which was husband's ratings, and the column variable, which is wife's ratings, that they're independent versus the alternative that they're not independent. So let's talk about what happens under independence. The probability that a husband rated N and the wife rated A would factor in the probability that the husband rated N times the probability that the wife rated A. Okay, so again, we don't have these probabilities, we're going to have to estimate them, but for the chi-squared test, we're going to estimate them under the null hypothesis and compare them to what we observe in the cell counts. So let me just do one of them. So the first row probability is 19 over 91, because if you disregard wife's ratings, the husband rated N 19 total times out of 91, and the wife rated N 12 times out of 91 if you disregard the husband's ratings. And so our expected counts under independence would be the probability of that specific cell, 19 over 91 times 12 over 91, which we can multiply these because we've made the assumption of independence under the null hypothesis. And then we multiply that times the number, 91, the total number of couples. To get 2.51, we're going to compare that to 7. Then you do that throughout, and you get the expected counts are this formula right here, if you'd like, the row total times the column total, then divided by n instead of n squared, because you multiply by n. So that EIJ is the cell you copy for every cell, but the logic is clear as to where that formula comes from. And the degrees of freedom are, again, rows -1 times columns -1. And I'm going to let you, again, now I'm going to do even less, and I'm going to let you calculate the statistic and compare it to the chi-square distribution. I would note, this is what, I find this fascinating, so I'll keep repeating it, but it is interesting that in all of the cases that we covered, you could just execute the formula or execute the chi-square test by using this formula, the EIJ equals Ni plus times N plus J over N. You wind up in every case with the identical chi-squared statistic, and I suggest you go back to some of these other examples and calculate the chi-squared statistic that way. So at any rate, and that's why often in textbooks the chi-squared statistic is only presented as this formula right here. But again, even though the statistic stays the same, the interpretation of the results depends on the design of the experiments and which margins are fixed by the design and so on. So I think that's an important caveat. But nonetheless, in terms of actually doing this stuff, if you have to program it, for example, you can always just use this simple formula and not have to really spend too much time thinking about, oh yeah, what's fixed and what's not while you're doing the calculations. Of course you want to think about that while you're doing the interpretation, but while you're doing the calculations you can just use this formula right here, which is extremely convenient then. Oh, and apparently I lied when I said I'm going to let you do this on your own, because here on the next slide I do it. So I define a 4x4 matrix here. The X matrix, you just do chi-squared chi-sq.test X, that'll give it to you. Again, remember doing the continuity correction, so if you do it by hand, you probably won't get exactly the same numbers. If you do this formula, observed minus expected squared over expected, you get around 17. The degrees of freedom are 3 squared, and the p-value works out to be just under 5%. So a couple caveats. I should say a couple caveats. One is the chi-squared approximation is an asymptotic approximation using the central limit theorem. Now it may not be clear how the central limit theorem is kicking in here, but it is. And so you have to worry about whether or not the central limit theorem is a good approximation. But fortunately for you, in a slide or two, we're going to talk about how you can do exact Monte Carlo finite sample approximations. So you should get excited about that now. so often I think in textbooks you'll see them talk about whether the cell counts are large enough to use a large sample approximation. My recommendation is just always use the small sample one. In chi-sq.test you can do an exact equals true argument and just get the exact small sample test, which then gets rid of the need to do that. And for the test of independence you can do it without actually too much computing. You have to have a pretty big table to not be able to do it. For more elaborate chi-square tests, you can't do the exact ones. I have an R package called exact log-lin test, which does kind of crazier distributions. But it's not maybe the most trivial R package to use. And then there's this software called StatExact where they do quite a few exact versions of contingency table tests. So at any rate, but all the chi-square tests in terms of comparing them to the chi-square distribution, that is an asymptotic test. It relies on the central limit theorem. You are, you can use these rules that say the cell counts have to be so large, but in reality, as with all chi-square with all asymptotic approximations, you're putting your faith in the idea that the cell count, the asymptotics have kicked in on your behalf. But checking that the cell counts are large is a way to give yourself some hope that that's true. I had one other point I wanted to make. So let's see. I think I made the point that the test, all of the test, if we had used this chi-squared independence formula, we would have gotten the same chi-squared statistic for all the tests. In every case, the degrees of freedom is always rows minus 1 times columns minus 1. Last thing. Yeah, now I remember what I wanted to say. So where in the world does this observed minus expected squared over expected, where does that statistic come from? It actually comes from the Poisson distribution. And it turns out that the expected value, the expected are the sort of expected cell counts, and it turns out in the Poisson the expected value is the variance as well of a Poisson random variable. So you can kind of think of this as each O is a Poisson count minus its mean, and then divided by its standard deviation. And if you square all that, right, then you wind up with this statistic, O minus E squared over E. So you might think of this guy, the O minus E squared over E, one of the elements of the sum, as being like a little Z statistic. And then you're adding up a bunch of Z statistics squared, which a Z statistic squared is a chi-squared 1. So when you're adding them up, you get a chi-squared. Now, because we're estimating components of the expected counts, then we lose degrees of freedom that way. And if you want to do a careful accounting of how the asymptotic works, then you have to account for it. But that's where this formula comes from. It comes from the Poisson distribution, and it really, you think of it as a bunch of squared Z statistics. And of course the asymptotics are a little bit more delicate than that, but honestly not that much more delicate than that. So that's where that formula comes from. Okay, so just to rehash, these equal distribution tests like we did for the word counts, that yields the same thing as the independence test. They're all the same test. And under the same under kind of the sort of similar modeling assumptions, similar testing assumptions. If your model is kind of binomial or multinomial with the row totals fixed, binomial or multinomial with the column totals fixed, the total sample size is fixed, and you assume multinomial and test independence, none are fixed, and you do a Poisson model and you test some form of row versus column additivity, all of these wind up in exactly the same chi-squared statistic, the same p-value, the same reject or not result. And if this bothers you, basically the best thing I've tried, I think, throughout the lecture to describe this on numerous occasions, but if it's still bothering you and gnawing at you, what I would say is this is really common in statistics. Mathematically equivalent results are applied in different settings. They have different interpretations, but the actual the mathematical results are equivalent. So that's how I like to rationalize it to myself, that all these things are coincidentally the same.
So, some final comments on the asymptotic test. The chi-squared result is an asymptotic test, so it requires that something be going to infinity. In the multinomial case, it's the overall sample size has to go to infinity. If you have, multinomial columns, then all of the column totals have to be going to infinity. And there's various strategies for checking whether or not you're close enough for the asymptotics to be reasonable. But we'll talk about an exact test that will get rid of the need to think about that. The degrees of freedom are always rows minus 1 times columns minus 1. And that's what we'll talk about now, is that generalizations of Fisher's exact test can be used. Or there's this other thing that continuity corrections can be used that will make the asymptotic approximations accurate even for relatively small sample size type problems. So let me show you how you can actually use Monte Carlo to calculate an exact p-value for contingency tables. Imagine if we got the individual data points, not just the contingency table, but the individual data points. So for the first couple, it was NN, and for the second couple, it was NN, for the third couple, it was NN, for the fourth couple, it was NN, and so on. And then, now here's a couple that was FN, and so on. And here I've clearly sorted them in some way, but this is the raw data. If you were to then take this data and create the counts of the number of NNs, FNs, VNs, ANs, and so on, FFs, AFs, and so on, you would get exactly the contingency table in the from the couple of slides ago. And here's the interesting fact. So this is the husband's data and the wife's data. So think about it. If they were independent, then the matching, the pairs of husband and wives would be irrelevant, whether or not you were talking about this specific couple or you just had a husband and a wife. Their answers shouldn't matter whether you line them up together with their correct husband and wife or not. So what you could do is either take the wife row here I have, or the husband row here, either way or both, but that would be unnecessary, and then just permute it. And then what you get is a realization of the contingency table where we've operated under the assumption that which particular member of the couple, the pairing of the couple is irrelevant. In other words, that husband and wives are independent. But notice if we were to permute that data and reconstruct the contingency table, we would still have the same number of husbands answering N, husbands answering F, wives answering N, wives answering F, wives answering V, wives answering A, and so on. So in other words, this procedure would constrain the margins, but would permute the interior of the table, which is exactly what Fisher's exact test did, right? And this is exactly the same thing as the Monte Carlo version of Fisher's exact test. It's just a general, with more possible outcome values for the row and the column variables. So you do this and you recalculate the contingency table, you calculate the chi-squared statistic for each permutation, and the percentage of times it's larger than the observed value is a so-called exact p-value. And in R, it's actually pretty easy to do this because you do chi-sq.test x and simulate .p-value equals true, and then it does this exact Monte Carlo version of the test, which is really neat. So this is just a generalization of Fisher's exact test, it's a very nifty little result, and it has a lot of intuition to it, right? It makes sense to think that, well, under the null hypothesis of independence, we should be able to permute the couple label, permute which specific pair it was, and recalculate the contingency table, and we should get roughly the same, discrepancy between the observed and the expected counts. Notice, I said use the chi-squared statistic, so we're using the chi-squared statistic, but we have an exact small sample p-value. This p-value is valid regardless of the size of the data. So of course then it tends to be a little bit conservative. But it's using the chi-squared statistic, but is not using the asymptotic the central limit theorem to compare your statistic to the chi-squared distribution.
I would say there's other choices for the test statistic, and because the way in which we're calculating our null distribution is through this permutation process, we could use whatever statistic we want right here. And so, the chi-squared distribution, the chi-squared statistic is not necessarily a bad choice. So anyway, this is an interesting way to get an exact p-value for contingency table test where you're interested in looking at things like independence between the rows and the columns. Okay, so now let's switch gears and talk about goodness of fit testing. Now this is the one instance I'm going to talk about where the degrees of freedom for the chi-squared is not rows minus 1 times columns minus 1. Okay, so imagine if you wanted to test R's uniform random number generator. So remember, a uniform is a number that's continuous number between 0 and 1, where in essence kind of every value is equally likely. What that means on the continuum scale is that the density is a brick that starts at 0, ends at 1, is height 1. So R simulates uniform numbers, and why don't we test it out to see, using the chi-squared distribution, to see whether or not we're getting kind of what we would expect. So I simulated 1,000 random uniforms. And how many uniforms would I expect to see between 0 and 0.25, between 0.25 and 0.5, between 0.5 and 0.75, and 0.75 and 1? Well, because it's uniform, it says that about 25% of them should be from there. Because it's uniform, it says that 25% should be between 0.25 and 0.5, and so on. Okay, so what we could do is simulate these 1,000. We have 254, 235, 267, 244. And we could calculate the how many we would expect to see under the true probability density function, or the assumed probability density function. So here our null hypothesis is that this first probability is exactly 0.25, the second probability is exactly 0.25, the third probability is exactly 0.25, and the fourth probability is exactly 0.25. And the alternative is that any one of these probabilities is different from its hypothesized value. Okay, and so that would be our test, and that would be comparing the observed counts to the expected counts. In this case, would be a not unreasonable way to check R's random number generation. Okay, so we observed 254 from the in reality when we simulated it. The expected would be 1,000 times 0.25, which is 250, and you can carry through the calculations. They're all 250 in this case, of course. And so our observed minus expected squared over expected sum works out to be about 2.3. This is 3 degrees of freedom. The p-value is 0.52. Now, it shouldn't surprise you that we get a large p-value in this case, because we're checking whether R's uniform random number generator, which we know is probably a pretty good uniform random number generator, whether or not it generates reasonably uniform numbers where we've broken the intervals up into 4. The test applies regardless of how we break up the intervals. We could have made some of them small, some of them large, and so on. And there's maybe, you could pick what's the most appropriate way to break up the intervals, but either way, the logic behind doing this goodness of fit testing applies. I would note that the degrees of freedom is just the number of cells minus 1, and the reason in this case is because we don't. We're not estimating anything. Under the null hypothesis, we're actually specifying the probabilities. So we don't. That's what changes the degrees of freedom. So let me also comment a little bit about testing random number generators. If you were going to do this, you would be concerned. You would want to generate thousands and thousands of variables. You probably want very fine intervals that you were looking at. And then the other thing is that this is only testing one aspect of the random number generation. It's only testing the uniformity, how uniform on the range it is. But there's other aspects of randomness that you would like to test, like whether or not you can detect whether the next value is it's somehow related to the previous or something like that, and it's some sort of autocorrelation or runs behavior. And those sorts of things are what people do to stress random number generators, which, by the way, are actually perfectly deterministic. There is no randomness built into them. The computer isn't, picking off the clock or something like that, somehow generating randomness. It's a deterministic sequence of numbers. They do those deterministic sequence of numbers in such a way that it's very hard to develop a statistical test that'll tell you it's not exactly uniform in IID. There's a whole discipline to this. It's quite interesting. Let's see. The other thing I would say about random number generators, I can't do this obviously in this class, but if you were to ask students in a class to generate random uniforms or random integers, and you could of course create a goodness of fit test to evaluate it, it's unbelievable how quickly you can determine that people aren't good at generating random numbers in the sense of being equally distributed. People can't distribute, just ask a room full of people to write out digits between 1 and 10, collect them up, and you will be able to diagnose immediately that that was not generated uniformly an IID from the digits 1 to 10. It's an interesting experiment. You might want to try it sometime. One of the easiest ways to do it is people don't give enough runs of specific numbers. So that, if you collect enough random digits, there should be of 1 to 10, there should be some instances of 3 consecutive 7s. But if you ask people to write out a bunch of random digits, they'll never write out 3 consecutive 7s for whatever the reason. It just goes to show our intuition about what randomness is not very accurate. We have to have the mathematics because our intuition is flawed. Anyway, let's move on to another example of goodness of fit testing. Okay, here's a famous example of goodness of fit testing. In Mendel's pea plant experiment, if you do out the Punnett square, you get under the, what is it called, the law of independent assortment, you should get about 75% of the yellow and 25% of the green plants. And so here's the observed data, 6,022, 2001, total 8,023, and here's the expected data. How would you get the expected data? Well, the true probabilities, I hypothesize true probabilities, let me put it to you that way. If the independent assortment laws were correct, you would get 0.75 and 0.25. So you're multiplying 0.75 times 8,023 to get 6,017.25, 0.25 times 8,023 to get 2,005.75. Using the observed minus expected squared over expected statistic, you get a very small chi-squared statistic. And continuing on to the next slide, this is a 1 degree of freedom test because it's cells minus 1, 2 minus 1, 1 degree of freedom. The p-value works out to be 0.90. In other words, the probabilities fit the hypothesis, the observed cell counts fit the expected probabilities quite well. At any rate, there's an interesting kind of famous discussion that occurred over this, is that the well-known statistician Fisher combined several of Mendel's tables, used the fact that sums of independent chi-squareds should be chi-squared. He got with the degrees of freedom adding up, that he got an associated p-value of perhaps almost exactly 1. And his accusation was then that maybe the data fit the Mendel's hypothesized probabilities too well, that maybe something fishy was going on. So anyway, you can read about that. It was kind of an interesting little study.
Okay, so for the final slide on um, goodness of fit testing, let's just summarize. It tests whether or not observed counts are consistent with theoretical values, theoretical hypothesized probabilities. The test statistic remains the same chi-squared test statistic. It follows a chi-squared distribution -1. The degrees of freedom are the number of cells -1. This is especially useful for testing random number generators. This is all for discrete data. We had to discretize the uniform distribution to use the chi-square goodness of fit test. There's a test called the Kolmogorov-Smirnov test that's an alternative that doesn't require discretization. It's often accused of having low power, but it's depends on what alternatives you're searching for and that sort of thing. But it is another test very well-known test for goodness of fit testing. So today's lecture covers a lot of chi-squared testing in a nutshell. And if you want to just remember a couple of things, make sure you remember the observed, the minus expected squared over expected. Some of those guys is the statistic. Remember the way in which you got the expected cell counts using independence that applies regardless of applies across all the settings that we considered today. Remember that the degrees of freedom for the goodness of fit testing was a little bit different, in the way in which you set up a goodness of fit test was a little bit different, but still uses the same observed minus expected squared over expected statistic. Okay? And we'll see you next time for the, let's see, what is this? I think the last lecture in this module. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 9 on Simpson's Paradox and Confounding. In this lecture, we're going to talk about a phenomenon called Simpson's Paradox. I don't find it to be a paradox, but it's called Simpson's Paradox. We'll talk about some examples like the Berkeley data of Simpson's Paradox, and then we'll talk about this related to the treatment of confounding. And then I want to cover a particular way to handle confounding through weighted estimators, and then talk a little bit about the Cochran-Mantel-Hansel estimator. Okay, so consider this data right here, which is taken from Agreste's categorical data analysis book. I think I've mentioned this book in the past. In this instance, there was a cross classification of defendants from criminal trials where they cross classified by the race of the victim. These are all murder trials, so the race of the victim versus the race of the defendant, and then whether or not the person got the death penalty. And here I present all of the possible cells plus all the possible marginals. So for example, here you see the 8 cells that classify victim's race, and here we're only factoring in 2 race denominations, white and black, and death penalty, so there's 8 cells. And then here I have the margin for the defendant, white versus black, summed over victim's race, and then here I have the victim, white versus black, summed over the defendant's race. Okay, so let's actually investigate this. So we're looking at the percentage of people that got the death penalty. So if you look, white defendants received the death penalty a fewer percentage of the time, 11 to 22%, for both white victims and black victims. 0 of the white defendants received the death penalty for the black victims versus 2.8%. Okay? But then something kind of paradoxical occurs. If you disregard the race of the victim, it actually comes out that white defendants received the death penalty a greater percentage of the time, 11% to 8%. Okay?
And then if you look at the race of the victim, disregarding the race of the defendant, actually in the instance where the victim was white, the defendant received the death penalty a higher percentage of the time, 12% to 2.5%. But let's forget this last two, race of the victim, marginal, and let's just compare the table itself, in which case, in both cases, the white defendants got the death penalty a smaller percentage of the time than the black defendants, regardless of the race of the victim, versus the marginal here, 11 to 8%, where the white defendants got the death penalty a greater percentage of time than the black defendants. So what's happening? If you were asked to, this was related to a court case about whether or not the death penalty was being equally applied. And so what would you conclude? If you condition on the race of the victim, you get a totally different, the opposite answer than if you look at the race of the defendant disregarding the race of the victim. So what is the right answer? So let's just discuss a little bit about what's going on. So marginally, white defendants receive the death penalty a greater percentage of time than black defendants. Across white and black victims, black defendants receive the death penalty a greater percentage of time than white defendants. And Simpson's paradox refers to the fact that marginal conditional associations can be opposing. In this case, if you take the margin across victim's race, you get a different answer than if you condition on victim's race. Here, so here the death penalty was enacted more often for the murder of a white victim than of a black victim, and then whites tend to kill whites, just demographically, hence the larger marginal association. And I want to, kind of do a little bit of a commentary before I go through more of examples. So I'm going to cover several examples. First of all, when you state Simpson's paradox in the following way, it doesn't seem that paradoxical at all. And the paradox is the apparent relationship between two variables can change when factoring in a third variable. And then that seems obvious. Of course that's true. It just seems difficult when you start to get mired in the specifics. And later on I'll go through the math to say that there's nothing paradoxical about the mathematics of Simpson's paradox. And Larry Wasserman on his blog, The Normal Deviate, has the most wonderful discussion of why Simpson's paradox is difficult and what the mistake people are making. And the mistake people are making is they're equating the statements, the causal statements, with the probabilistic statements. And the probabilistic statements can be misleading and paradoxical, and you're trying to make difficult conclusions in the light of noisy evidence. So, and in addition, even if you knew the exact probabilities, the probabilities themselves can exhibit the paradox. However, the causal statements cannot exhibit a paradox. Okay, so the problem, I think, his statement is that the real confusion is equating the cause. In this case, if you were, the cause would be, you would say that, for example, juries tend to causally convict black defendants more often than they convict white defendants. If you were to make that causal statement, then it is impossible for marginal and conditional causal statements to disagree. And so, the real details of this, I'll put up the link to his blog post, which is wonderful. But the real details of investigating the causal statements is beyond the scope of this class. We're not going to cover causal inference in this class. But I think it was a great discussion on his part to basically show or demonstrate that it is this conflation of cause with describing probabilities and associations that is the apparent paradox. But mathematically, there is no paradox, and I think when we go through it, you'll see. So here's another example that was on Wikipedia, which is a wonderful example. It's kind of a famous example in this area, just to describe the numbers, how this numerically can happen. So in American baseball, a batting average, so if you've never seen or heard of baseball, baseball is a game where a player, look it up, a player goes up with a bat and the pitcher throws the ball really hard. It's really, really quite difficult to hit a baseball, especially in the professional leagues. They throw the ball 100 miles an hour. So the player swings the bat and tries to hit the ball. The percentage of, basically, not exactly, but the percentage of time that the player hits the ball is going to be their so-called batting average, right? And really good players can do this, let's say 30% of the time. Excellent players, but most players are worse than that. Okay, so here's two players and their batting average. So player 1 had 10 at-bats in the first half of the season and got 4 hits. Player 2 had 100 at-bats and got 35 hits. So the player 1's batting average was 40%, player 2's batting average was 35%. The second half of the season, player 1 got 25 hits out of 100, 25% batting average. The second half of the season, player 2 got 2 out of 10 hits, 20% batting average. So in both the first half and the second half of the season, player 1 had a better batting average than player 2, right? However, if you just add up these numbers, 29 hits out of 110 at-bats for the whole season for player 1, and 37 at-bats for 110 for the whole season for player 2, you get 26% for player 1 and 34% for player 2. So player 2 has a better batting average. So it seems paradoxical that a person can have a better batting average for both the first half and the second half of the season, but have a worse batting average overall. But of course the numbers work out, right? You see it, the numbers actually work out. And so I put in consider the number of at-bats here because that's coming into play. That the player 1s had this very good batting average when they had relatively few at-bats, and a modest batting average when they had lots of at-bats, and vice versa for the other players. So that's, I think, really the culprit in this case. Okay, and another very famous example of Simpson's paradox is the so-called Berkeley admissions data, and it's fun and it's in R. So I'll cover it a little bit, and you can explore it because to get it, you can just do help UCB admissions, and then that'll describe the data set. Data UCB admissions will load it up, and then here I give a little command, apply UCB admissions C12 sum. It gets the appropriate marginal. So here we looked at whether or not so for admission versus rejected by gender, and we get that males, the acceptance rate was higher for males than it was for females, disregarding everything else. Okay, but I give another command here, and then it shows now the admissions rate. I'm not showing the counts because the table is getting a little bit unwieldy. So I'm showing the admission rates by department A, B, C, D, E, F, and E and F. And then what you can see among, for department A, males got admitted fewer percentage of the time. Department B, males got admitted fewer percentage of the time. Department C, males got, got admitted a slightly larger percentage, lower for D, slightly larger for E, and lower for F. So clearly the admissions, gender imbalance in the admissions is dependent on whether you're conditioning, the evidence of gender imbalance in admissions is dependent on whether or not you're conditioning on department. And there's different application rates, and you can explore this yourself. There's different application rates by gender for each of the departments. And so look here, in fact, you don't even have to explore it yourself. I apparently have it on here on the next slide. So gender, male, female, by department, and you can explore this a little bit more because the data is just in R. I don't think you have to have any other packages installed. You can just do data UCBA admissions and play around with it. So let me talk a little bit about what in the world is going on here, because it's confusing. It seems confusing. To me, there's a couple things that help me understand Simpson's paradox. First thing is the math. There's no problem with the math, right? If you're saying that A over B is less than C over D and E over F is less than G over H, but if you can find integers that satisfy the following equations, where B has to be greater than A and F has to be greater than E and so on. But if you can find integers that satisfy these equations, then you've found an example of Simpson's paradox. You just have to put context around it. But it doesn't seem at all paradoxical when you state it as a couple of relationships between integers this way. Right? Then it just doesn't seem very paradoxical anymore. It's the context that adds the paradox. And you know, just from a statistical standpoint, it says the apparent relationship between two variables can change in the light or absence of a third, which again doesn't sound that paradoxical. It's only when we conflate the probabilistic statements and the evidence associated with the probabilistic statements vis-a-vis the data with the causal statements, right? So the problem is we're going to try and get at the cause, the truth, by virtue of the probabilistic statements and the associations obtained from the data. But that's a quite hard thing. The question in all these cases is what's the right answer? What should you condition on, or should you not condition? And that's a hard problem. We're not going to really cover that in this class. To me, the real answer of this is that it's quite hard to exactly figure out when you've conditioned enough, right? And in some cases, no conditioning is exactly the right answer, and in some cases, conditioning is exactly the right answer. To really handle this formally, you've got to do something called causal inference, basically, and that is really the discipline that's really the subdiscipline of statistics that is really entirely designed towards addressing this question in a formal manner. In the meantime, but let me say this. In the meantime, what can you do? And the idea is to not decouple the statistics from the scientific discussion. In the case of the death penalty, you would want to have a discussion about hypotheses for the causal mechanisms between the various associations. Does it make sense to be conditioning on the race of the victim? In the Berkeley admissions data, you'd want to talk about, well, are there very different acceptance rates by departments, and then are there different application rates by gender to each department? And does the fact that, say, are women applying to departments that are harder to get into? That would explain the marginal association quite well. And is that really the driver? And that's a discussion, kind of in a sense, a discussion that's informed by the statistics, but extra statistical. And at this point, I think it is this kind of interplay between the data and a scientific discussion is the best solution I can offer to you for dealing with confounding. When you take further statistical courses, you can learn some of the formal mechanisms for trying to account for confounding. But suffice it to say, it's one of the harder issues in statistics, knowing how to balance the over-adjustment with under-adjustment in terms of confounding is one of the central problems in observational data analysis. And it's what makes observational data analysis so hard compared to, say, for example, where you randomize a treatment or something like that. So I've been using the word confounder a lot in confounding, so let me define it. So variables that are correlated both with the explanatory and response variables are confounders, and they can distort an estimated effect. So in this case, victim's race was correlated with both the defendant's race and whether or not the death penalty was executed. This is a I think a kind of old school definition of confounding. There's a modern definition given by causal inference inference classes that I think you might be, if you're interested in the field of statistics, would be worth learning. I think ultimately with a confounder here, we haven't really distinguished between something that's causally related with the race and the death penalty versus something that has a statistical association with race and death penalty. In this class, we're mostly going to be talking about things that have a statistical association with the explanatory and response variables, where there is kind of a plausible causal connection between them. Okay, so again, putting aside the rather difficult and lengthy discussion of what is a confounder, how do we select our confounders, how do we, that discussion, putting it to the side, let's assume we have a single confounder. How do we adjust for it? Well, there's several ways. Regression is probably the biggest and most common way to adjust for confounders. But kind of an old school way in categorical data analysis is to stratify by the confounder and then combine the strata specific estimates. And so this requires appropriate weighting of the strata specific estimates, and we'll talk in a minute about how do you do the appropriate weighting. And unnecessary stratification has its own set of problems. So again, just bringing back this discussion, the solution to the confounding problem is not just to stratify or adjust for everything in sight, right? That's not the solution, because that has its own host of consequences. For example, in any of these Simpson's paradox examples, imagine you had a giant database and you were interested in, say, the death penalty, and you had a giant database with lots of other variables. For sure, you could find one variable that reverses the association but has no bearing on whether or not a person received the death penalty, right? So adjusting that for that confounder will reverse the association but has no business being adjusted for. And so it's a hard topic. Admittedly, it's a hard topic of selecting confounders and achieving balance between the right amount of confounder adjustment and the with over adjustment, balancing between that and over adjustment. So let's stipulate for the time being we have a confounder, we want to adjust for it, and what I really want to talk about is the method of stratifying and then combining strata specific estimates, and because then we'll be able to teach you some nice methodology, and then as you take more statistics courses, you'll learn more about the delicate surgery of dealing with statistical confounding. Okay, so here I have an aside, but it's an important aside. Suppose you have two scales, and what I mean by scales, I mean things for weighing objects. And let's assume both the scales are so-called unbiased. They both have some variance associated with them. If you weigh the same thing over and over again, you get different answers. But one has a variance of 1 pound, and the other has a variance of 9 pounds. They're both unbiased. Confronted with weights from both scales, would you give both measurements equal credence? So let's just suppose we weighed an object, and that our first weight was this variable x1, and we're going to assume that it's normal, mu, and the variance of the first scale, sigma 1 squared, and then x2, because both scales are unbiased, we're going to assume that it's normal and it has the same population mean, mu, and the same, a different variance, sigma 2 squared. And let's assume both sigma 1 and sigma 2 are known. We want to estimate mu, this unknown weight of the object. Okay, so we measured it with one scale with one precision, another scale with another precision. We're assuming both scales are unbiased in that if we measured the same object over and over and over again, the average would be about right. If we characterize this in this way, I'm hoping what everyone can do in the class is set up the likelihood, multiply the two, add the two log likelihoods or multiply the two log likelihoods and take the log, and then come up with the fact that the log likelihood for mu, disregard any terms that don't involve mu, and I'm hoping everyone can come up with the fact that the log likelihood for mu looks like this, bottom equation right here. Okay, and let's solve for a maximum likelihood estimate. So the easiest way to do that right now would be to take the derivatives, set the derivative equal to 0, and you get this answer, x1 times r1 plus x2 times r2 divided by r1 plus r2, or in other words, x times p plus x2 times 1 minus p, where p is r1 over r1 plus r2, and 1 minus p is r2 over r1 plus r2. And then in this case, ri is 1 over sigma squared sub I, and then p is, of course, 1 over r1 divided by r1 plus r2.
So why does this make sense? This makes a lot of sense to me now. But the first time you see it, you might say, this makes no sense. But let me describe why this makes a ton of sense. Okay, so notice what each Ri is. It's 1 over the variance. So if, let's say, sigma 1 is huge, in other words, that scale stinks, it has this huge variance, then the weight, R1 times X1, the weight given to the measurement from that scale is very low. And then conversely, if sigma 2 is very small, then I get R1, which is 1 over sigma squared, will be a huge number, and then X2 is given a gigantic weight. And then we divide by R1 plus R2 so that when we weight these two things, X1 and X2, we get a convex combination, P times X1 plus 1 minus P times X2, so that it's an average. It's just a weighted average. Okay? And by the way, you can do this always. If you want to take a generalized form of average, right, and you want R1 is the weight for X1 and R2 is the weight for X2, they have to be positive, of course, and you want to turn it into an average, then just divide the whole thing by R1 plus R2, and then you'll turn it into P times 1 and 1 minus P times the other. If R1 equals R2, they'll be the strict arithmetic average of the two numbers. If R1's different from R2, it'll weight one of the observations more than the other. Well, the answer in this case is that we want to weight by the inverse of the variance, giving high variance measurements low weight and low variance measurements high weight, which to me then makes a ton of sense. Okay, so anyway, the general principle, instead of averaging over several unbiased estimates, take an average weighted according to the inverse of the variances. And this is so ingrained in statistical practice now that people do it without thinking. They don't go through this exercise of deriving maximum likelihood equations. So in our case, sigma 1 squared was 1, sigma 2 squared was 9. So in this case, you can work it out. P works out to be 0.9. So it works out to be 0.9 times the first measurement plus 0.1 times the second measurement. The first measurement getting a lot more weight because the scale, has 1/9 the variance of the other one. So there's a great example of this. Imagine just going back to our death penalty example. And here we had two 2-by-2 tables. We had the defendant's race and whether or not they got the death penalty. And then we stratified that by a third variable, victim's race. So let Nijk be the ijk entry of table K. So in this case, K equals 1 to 2. K equal 1 would be the first victim's race. K equal 2 would be the second victim's race. And then I and J would index defendant's race and whether or not the person got the death penalty. So in our first example, we had two 2-by tables stacked one on top of the other. K indexes the first one, K equal 1 indexes the first one, K equal 2 indexed the second one, and then Nij indexed the individual elements of that 2-by-2 table. So then the kth odds ratio, the kth sample odds ratio, so remember the odds ratio was the cross product ratio, so the main diagonal divided by the off diagonal, so n11 times n22 divided by n12 times n21. So in this case, everything indexed by k, referencing the kth table. So the kth sample odds ratio is sigma hat sub k. Then the Mantel-Hansel estimator is exactly our weighted average of these stratus-specific estimates. It's summation weight rk times theta hat sub k divided by the sum of the rk's. And by the way, when we had two, it was r1 times x1 plus r2 times x2 divided by r1 plus r2. But if we had 3, it would be r1 times x1 plus r2 times x2 plus r3 times x3 divided by the sum of the r's. And if we had 4, same thing. Anyway, this is the Mantel-Hansel estimate. This is the sum of the weights times the stratus-specific odds ratios, theta hat sub k, divided by the sum of the weights. So we just get a weighted average, a simplicial convex combination of the stratus-specific odds ratios. And then what are the weights? Well, Okay, so the weights in this case are this little formula right here, and I'll describe where they come from. But the 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 motivation for the weights is that they're inverse variances. That's 100% the motivation for the weights. They're inverse variances from a hypergeometric distribution. So you can just think of, we're exactly doing the same thing we did with the scales, only now in terms of the odds ratio. And then anyway, this simplifies the so-called Mantel-Hansel estimator. Here's the formula right here. I would suggest that you look in Agreste's book, page 235, in the version I was looking at, but you can look it up. The version's probably changed. Rosner's book, which is very comprehensive, page 656. They give the standard error. It's a long formula. I'm sure you can find it on the internet as well. This is the so-called Mantel-Hansel estimator, named after the two great epidemiologists, Mantel and Hansel. Okay, so here's an example, and here's a great example of this Mantel-Hansel estimator. So here we had an active drug, T, and C being a placebo control, I guess. And then here we had success versus failure. And I'm going to abstract what the specifics were of the experiment. And then what people were concerned about was whatever policies and practices existed at the various centers in which the data were collected. So they stratified by center. 1, 2, 3, 4, 5, 6, 7, 8 centers. So they got 8 odds ratios, right? And they were worried that the center was a confounded. There's several reasons actually you might want to do the Mantel-Hansel estimator in this case. But let's talk about it in terms of confounding first. So imagine if you thought that the center was specifically associated with the treatment application. Some centers tended to apply the treatment more than others, and that the center was associated with the success of the treatment because of different policies associated with the center and how the treatment was delivered or something like that. Then you would want to adjust for the center as a potential confounder. And then here you would, we're going to adjust for this confounder by stratifying by center, getting an odds ratio specific to every center, and then averaging over the odds ratio, but factoring in the inverse variance of the odds ratio. Some centers had more patients, right? This one had 73, this one had 14, so we want to weight the one with, say, 73 more than the one with 14, because they have a better, more precise odds ratio. And so that's what the Mantel-Hansel does. And so you get this, you get an odds ratio of 2.13. The log odds ratio is 0.758, and the standard error, because of the standard error calculation, it uses a delta method type argument. Standard error of the log odds ratio works out to be 0.303. You would take 0.758, add and subtract, say, 2 standard errors, and exponentiate the endpoints to get a confidence interval for the odds ratio. Let me talk a little bit about the another rationale for why we might want to do some sort of stratified estimate. It's also often the case, in this case, we think that center is at some level this random effect type modifier of the treatment of efficacy. And we are willing to think of these centers as sort of a random draw from the population of centers. Then in that case, it still actually makes a lot of sense to combine them, because we're not so much interested in center-specific effects. We don't care if the treatment works at center number 1. What we care is if it works overall. And it turns out, even if the center isn't just a confounder, but it really modifies the effect of the treatment, then some places are just better at doing the treatment than the others. Then really kind of what you but if you're willing to make the assumption that the centers are this sort of random draw from a population of centers, then this CMH estimate makes a lot of sense, saying, okay, averaging across centers, here's the effect of the treatment. And that's another instance where you would consider doing something like a Mantel-Hansel log, a common odds ratio estimate. So this is what is often called as the common odds ratio across centers. So then there's a famous test for testing whether or not the odds ratios are the common odds ratios are equal to 1. So the test is usually stated as the null hypothesis that all of the strata-specific odds ratios are equal and they happen to be equal to 1, versus the alternative. And there's some amount of dispute over the alternative, but I'm going to teach the alternative this way. The alternative is that they're all equal, right, but they're not equal to 1. Okay? So notice this is different than the alternative that they're not necessarily equal even. So here we're assuming that we have a common odds ratio under the null and alternative, and we just want to test whether that common across strata odds ratio is 1 versus not. And it turns out that the CMH test applies to other alternatives, but it's more powerful for the particular alternative given above. I'll also mention that this test is exactly the same as testing for conditional independence of response and exposure given the stratifying variable. And so this Cochran-Mantel-Hansel test, the way it's executed is it conditions on the rows and the columns for each of the contingency tables exactly like Fisher's exact test, resulting in hypergeometric decay, hypergeometric distributions, and then leaving only the upper left-hand cell of each table free, just exactly like we did in Fisher's exact test, only this time doing it for each specific cell. So I'll go through the mechanics now. Okay, so under this conditioning and under the null hypothesis, under both those circumstances, then the expected value of the upper left-hand cell of each table is this value. The variance of the upper left-hand cell is this value. So the Cochran-Mantel-Hansel test statistic works out to be this guy right here, kind of the sum of the deviations of the upper left-hand cells from their expected values, but summed up and then squared, unlike the chi-square test where they're squared and then summed up. So summed up and then squared. And then regardless of how many tables you have, under the null hypothesis, this is a chi-squared 1. Remember, this is a different test than the chi-square testing we talked about in the previous lecture, so that's why it's a different test statistic. And the idea of testing conditional independence or testing for this confounder relationship is a different idea, and that's why you get a different test statistic. I think it's a little bit beyond the scope of this class to derive the CMH test statistic. But the idea is here you want to test for whether or not the odds ratio is 1, given that it's common across all strata, versus the odds ratio, given that it's common across all strata, is not 1. So here I'm going to implement it. It's a bit of a pain to actually execute the CMH test by hand. So here I'm putting the data into an array. In this case, 8 2x2 tables, and then you can do this Mantel-Hansel test. Correct equals false. I put again correct equals false here so that if you do the calculations by hand, you'll get an agreeing result to the R output. You generally want to leave this correct equals true. The result is the test statistic is 6.38. Compare that to a chi-squared 1 value, or again, you only reject for larger values the test statistic. Again, it being a two-sided test because it's a squared statistic. And so in this case, the p-value is 0.012, so the test presents evidence to suggest that a treatment and response are not conditionally independent given center. Some final notes on this testing is, it's possible to perform an analogous test using a kind of what I consider to be a little bit more modern of approach, using a random effects logit model. And the reason I like, but again, we're not, we haven't covered regression, so we can't cover mixed models, and then we can't cover generalized linear and mixed models and all the machinery that you would need to cover this. It's possible, at any rate, I think, you should take the time, if you're going to work as a statistician or use a lot of statistics in your life, you should take the time to build your way up to where you're studying mixed effect models and generalized linear mixed effect models. And there, you can do exactly things like what the CMH test is doing, only you can do it in a very general way that allows for other variables to be specified in the model and so on. The reason for presenting it this way in this class is to just give you a sense about the idea of confounding, to give you a sense of what you can do just in particular in the case of 2x2 tables. And then later on, I'm hoping that you'll take some more statistics classes and learn about mixed models and generalized linear mixed models. It's also, so here we assumed all the odds ratios were equal versus the alternative that they were all equal but not equal to 1. It's also possible to test whether or not all the odds ratios are equal. There's a test for that. I think it's called Wolf's test. That's a very good test. I don't have time to cover it. The final thing I would mention also is that we have these K hypergeometric distributions that we used in the CMH test statistic. So you can probably guess that you can exactly do some sort of exact test in this case. And you can, in R, you can just do exact equals true as an argument in the Mantel-Hansel test. But you could probably envision how it's done. Imagine is within each center, you were to permute do this permutation process that we talked about for Fisher's exact test. Imagine if you were to do that now within each strata, then recreate the chi-squared statistic each time, the Mantel-Hansel chi-squared statistic each time, and do that over and over and over again, and that simulation would yield an exact p-value. So I think you could actually probably come pretty close to doing exactly what the exact equals true argument is doing in R by that permutation process. Of course, in this case, they can do the calculations exactly without Monte Carlo. So it's faster, but conceptually, that's exactly what they're doing. Okay, well, that's the end of the lecture. And so anyway, this was a teaser on the idea of confounding. And confounding is, one of probably the biggest obstacle to generating knowledge from observational data where you don't have a heavy amount of control over the design of the experiment, which is most data, right? The easy data to collect is observational data. So this gives you a teaser in how that data is collected, how that data is analyzed, and there's a tremendous art to analyzing that data that I hope as you learn more statistics, you'll get more refined at that art. And just like any other art, you can spend a lifetime perfecting your craft and you'll never really hit a limit. It's a very hard topic. And then again, I highly recommend considering learning something about causal inference, which is the most modern attempt at addressing this problem in a mathematically formal way. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2, Lecture 10 on case control data. In this lecture, we're going to briefly talk about case control methods. We'll talk about an instance where using retrospective case control data and a so-called rare disease assumption, we can estimate prospective odds ratios. And then because this is kind of a lot focused on the odds ratio, I thought I'd talk a little bit about exact inference for the odds ratio. Okay, so let's talk about retrospective, kind of case reference sampling. And again, this is a deep subject. We're going to scratch the surface of it. So in this case, imagine if we wanted to study lung cancer, and here we had some cases and controls, and we ascertained whether or not they were a smoker. Now there's two ways we could collect it. Well, there's conceptually two ways we could collect this data. One is we could follow a bunch of people up over time. Some of them would smoke and some of them wouldn't. And then we could see who obtained lung cancer. That's very hard to do, right? I mean, I think conceptually you can all see that experiment is basically impossible. A much easier experiment would be to go to hospital records and find a bunch of people that were cases that had lung cancer. Let's say in this case we found 709 of them. And then we also found 709 controls that were at some level comparable. and then we retrospectively determined whether or not they were smokers. Now in this case, the 709 is fixed, right? And it's whether or not they were a smoker that we are has the ability to vary. Now I should also say that the most common way to do case control methods would be for every case to try and very closely match a control, so that for every case there's a specific matched control. But in this case we're not doing that. Let's say we had a group of cases, a group of case hospital records, and a group of control hospital records, and or a group of control patients, and we figured out, a reasonable strategy for getting control patients. And now these 709 is fixed, so what we wanted to ascertain is who was a smoker and not, and whether or not the cases had a greater proportion of smokers, and to kind of make prospective conclusions from this retrospective data. So just, in terms of probability, right, we cannot estimate the probability of being a case given that you were a smoker directly from the data. But we can estimate the probability of being a smoker given that you were a case, right? And so we want to work with that, kind of probability rubric. What is interesting is we can estimate an odds ratio. So the odds ratio that we would want to estimate is the odds of being a case given that you were a smoker relative to the odds of becoming a case relative to being given that you were a non-smoker. Okay, so we want the odds of developing lung cancer given that you smoked compared to the odds of developing lung cancer given that you didn't smoke. Well, it turns out that odds ratio is exactly equal to the odds of being a smoker given that you're a case relative to the odds of being a smoker given that you are a control. So in the bottom one we can estimate, the top one we cannot. So here I just directly go through the calculations. The odds of being a case given that you're a smoker divided by the odds of being a case given that you're a non-smoker, the odds ratio of interest, right? And let me just replace case and not with C and S. A case and non-case with C and C bar, and smoker and non-smoker with S and S bar. And here I just churn through the calculations. You can go through these three steps and make sure that you agree. So here I carry through the calculation, and look, this works out to be the probability of being a case and a smoker times the probability of being a not case and a not smoker divided by the probability of being a case and a non-smoker divided by the probability of being not a case and not a smoker. So it's sort of like the probability cross-product ratio. The probability of caseness and smokerness times the probability of being not case and non-smoker divided by the kind of off-diagonal probabilities. Now, and I say this actually proves the result, and I think it does, because honestly, you can just see that if you were to exchange the words case and smoker up at the top, that nothing changes when we get down to the bottom line here, right? Because probability of C comma S is the same as probability S comma C. So I think you can tell to me that this is exactly equal. Or if you want to be very particular, you can then keep working and get to the other odds ratio. But to me, this proves the result from the previous page. And I would also remind you that these are the probability statements, but we estimate those probability and odds ratios from data. And of course, the sample odds ratio is the cross-product ratio n11, n22 divided by n12, n21. And the odds ratio is invariant to transposing the rows in the columns. So our estimator has this kind of invariance property, which we would hope, right? It would be weird if we said that the two odds ratios probabilities were equal, but the sample estimates were not equal depending on which one you were treating as the outcome and which one you were treating as the predictor. So that's nice. By the way, the sample odds ratio is unchanged if a row or a column is multiplied by a constant. And then the last thing, this is what we'll talk about, the odds ratio turns out to be related to the relative risk. So the thing is, if you want odds ratios, we've just kind of demonstrated that the odds ratio works out really well, and you can kind of reverse conditioning a little bit when talking about the odds ratio. But we'll talk about specifically the relative risk, which is what people often want to estimate, and how it relates to the odds ratio. Okay, so the odds ratio is here, right? Probability of a smoker given that you're a case divided by the probability of non-smoker given that you're a case, and so on. You can read this top line. Okay, then we can reverse the odds ratio, right? Using the argument from the other page, right? So now we have probability of case given smoker divided by probability of non-case given smoker divided by probability of case given non-smoker divided by probability of non-case given non-smoker. Okay. Then in the next line, just everything is multiplied out. Denominators are raised up to numerators and so on. And then look at this first term here, probability of case given smoker divided by probability of case given non-smoker. That's the relative risk, right? That's if we want to determine who develops lung cancer comparing who smoked to who didn't smoke. That's the relative risk, the ratio of the two probabilities. And then that's multiplied times these things, but I wanted to refer them with respect to case status, so I just 1 minus each of the probabilities. And what you can see is if this ratio that we're multiplying the relative risk times, if it's about 1, then the odds ratio is approximating the relative risk. Often is the case if these two numbers, 1 minus this number and 1 minus that number, that they're similar enough if in fact the case is very rare. In other words, regardless of whether or not you smoke, the probability that you get this disease, let's say lung cancer, is quite small. If that's the case, this so-called rare disease assumption, if that's true, then this ratio will be about 1, and then the odds ratio will approximate the relative risk. And that's what people often talk about, the rare disease assumption, and they use the retrospectively collected data along with the odds ratio to then approximate the relative risk. It's so common. Often people don't even really talk about what they're doing, they just do it. I think that's so common in the epi literature. It's generally not described in a say American Journal of Epidemiology article or something like that. So now just make the small point that the disease has to be rare among the exposed and the non-exposed, not just rare overall. So here's a simple example. Chuck Rohde reminded me of this at one point. So here we have the exposure, yes or no, disease, yes or no. We have 911, 999. So just from the data, and let's assume that this is just cross-sectional data, so all the margins and everything are estimable. So the probability of disease, the estimated probability of disease, is about 1%. The odds ratio works out to be almost 9,000. The relative risk works out to be about 900. So clearly the odds ratio is not estimating the relative risk. And in this case, like I said, because of the sampling, I'm assuming the two are directly estimable from the data. So in this case, what happens is disease is rare among the exposed. I'm sorry, D is rare overall, right? Let's see, what is it? 10 out of 1,010. But D is not rare among the exposed, right? So among the exposed, you actually had 9 times the number of people having the disease rather than not. So anyway, I think this is if you look at the equation, right, it's clear, that both the P of C given S bar and P of C given S both have to be small. in order for the rare disease assumption to apply. That's the real criteria. I think this is just a numerical. This is a numerical illustration in a hypothetical circumstances where we can estimate all the probabilities well, and we can show that the two aren't approximately equal to each other. So let's just recap about the odds ratio. So an odds ratio of 1 applies no association. Odds ratio greater than 1 is a positive association. Odds ratio less than 1 is a negative association. For retrospective case control studies, odds ratios can be interpreted prospectively. For diseases that are rare among the cases and controls, the odds ratio approximates the relative risk. And the delta method standard error for the odds ratio is the square root of 1 over the cell counts added up. And just to remind you, that's the standard error for the log odds ratio, not the standard error for the odds ratio. So let's just go through our example. We have our lung cancer cases and controls, smokers, yes or no. We get our odds ratio, it works out to be 3. We get our standard error for the log odds ratio, it works out to be 0.26. If we want a confidence interval, it's log of 3 plus or minus 2 standard errors. We get 0.59 to 1.61. We would compare this interval to whether or not 0 is in that interval. If we exponentiate it, then we would compare whether or not 1 is in the interval. In this case, if we exponentiate it, we get 1.8 to 5.0, so 1 is not in the interval. And our estimated odds of lung cancer for smokers is 3 times that, the odds for non-smokers. Okay, so let's talk about exact inference for the odds ratio. This is the last thing I'll talk about in this lecture. Let's let X be the number of smokers for the cases and Y be the number of smokers for the controls. And remember, in this case, X and Y are the random numbers because we're thinking about case reference sampling. So X and Y are the random numbers. The 709 margins are fixed, and we're going to assume that both of them are, say, binomial. And we want to calculate an exact confidence interval for the odds ratio, not an approximate one. So the square root 1 over the cell counts formula is an approximate one. And I'll show that you have to eliminate a nuisance parameter, and I'll show you how to do that. So let's define the logit function as the log of the odds. So logit p is log p over 1 minus p. That's the logit function. So notice that differences in logits are log odds ratios. So if you logit p1 minus logit p2, that's the log odds ratio for p1 to p2. So as an example, logit p, so let's define the logit of the probability of being a smoker given that you're a case as delta. And by the way, this implies that the probability that you're a smoker given a case is e to the delta over 1 plus e to the delta. So if you invert the logit function, you get that. The logit of the probability of being a smoker given that you're a control, let's call that delta plus theta. So it's a different number, but we're describing it relative to delta. But because we're not constraining theta, it can still be any number. But theta, okay. Then we get probability of being a smoker given a control works out to be e to the delta plus theta divided by 1 plus e to the delta plus theta. In this case, theta works out to be the log odds ratio. Okay, so actually just, of course it's the log odds ratio because if we subtract the two logits, the delta cancels out and we get theta. So theta is the log odds ratio. And in the way that we've parameterized this, delta, this other parameter, is a so-called nuisance parameter. We don't care about that. What we care about is the log odds ratio, comparing smokers to case status. Okay, so let's keep working on the model here. So here we're going to assume that X is binomial with N1 trials, and then we already stipulated that the probability that the logit is delta, so the probability is e to the delta over 1 plus e to the delta. And then Y is binomial with N2 trials, and success probability e to the delta plus theta divided by 1 plus e to the delta plus theta. So then our probability x is the capital X takes on realized value little x is going to be this binomial probability, and you can kind of work with it and get to where it's this formula right here, n1 choose x, etc. Then, so this is just carrying this over from the previous slide. This is the probability x takes on realized value little x, and then I'm going to look at the probability y takes on realized value z minus x, and you'll hopefully see why in a minute. And that's just plugging directly into the binomial formula. And again, I have z minus x right here instead of a particular value, say little y. Okay, now the probability that x plus y, the random variable x plus y, takes on realized value z is a little bit harder to calculate because x and y are not identically distributed. If they were identically distributed, then x would be the sum of a bunch of Bernoulli trials, y would be a sum of a bunch of Bernoulli trials, so x plus y would be the sum of a bunch of IID Bernoulli trials. So they're still both the sum of a bunch of Bernoulli trials, but not the same. Okay? So here's what we can do. We can factor this into, let's suppose that we decompose z into u and z minus u, u parts going into x and z minus u parts going into y. Then that probability would be this product right here. Probably x is u and y is z minus u. And so the probability x plus y takes on the value z is going to be the sum over all the possible values of u. In other words, all the different ways we could allocate some of the elements of z to x, then whatever we can allocate the remaining to y. Okay, so that's a quick little formula you can do. Okay, now we're going to get to the point. So now let's look at the probability x takes on particular value x, given that the sum x plus y takes on particular value z. And I'm just going to plug in these three lines up here, right? So the probability x takes on value x is going to be the probability, this numerator probability right here, probably x equals x, probably y equals z minus x. And so just to elaborate on that point, the probability x takes on value x and x plus y takes on value z is this the and probability. Then given that, because we're stipulating that x is value x, that's the same thing as the probability y takes on value z minus little x, and then we can factor those probabilities into the product. So that's the numerator right here, and then the denominator I'm just plugging directly in the probability x plus y takes on value z. Okay, so then you put it all in. Just, you know, if you can follow the mathematics, hopefully you follow the mathematics. If you can't, if you're having trouble with this, because I realize it's a little bit in depth, then if you plug it all in, you wind up with this formula right here. And again, this is very similar to our development of Fisher's exact test. The only difference is now we haven't assumed the null hypothesis to be true. And so what we have here is it depends on theta, this log odds ratio. Okay? So here, but notice it doesn't depend on delta, right? So we've gotten rid of delta, and that's this idea of conditioning away the nuisance parameter. Here, conditioning on x plus y, it conditions away the nuisance parameter. So, but nonetheless, now we have a distribution for our two variables, because remember, if I know, I don't need to talk about x and y if I've conditioned on x plus y. If I know x, then I know y, given that I know x plus y. Okay, so you can use this distribution to calculate exact hypothesis test for theta equal to theta naught, other than 0. The specific case 0 results in Fisher's exact test, the ordinary hypergeometric distribution. And then you can invert these tests to yield exact confidence intervals for the odds ratio. And that is exactly what R does. If you do Fisher.test, it'll give you a confidence interval for the odds ratio. It is exactly doing this, this procedure right here. It's inverting this distribution here, which is called the non-central hypergeometric distribution. So we're not going to go through any calculations with this because, as you can tell at this point, it's gotten rather involved. But I did just want to show everyone where these exact odds ratio calculations come from. They basically come from this formulation of the problem as a non-central hypergeometric distribution. So what I'm hoping you got from today's lecture, though, was a little bit of information about the odds ratio, about some of its more general purpose uses, for example, in case control studies, and then also now to talk about a little bit about where some of the more complex formulas for performing inference on the odds ratio come from. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp 2. And today we're going to be talking about matched 2x2 tables. Okay, so today we're going to be talking about matched pairs data, which is basically going to be like the paired t-test, but only now we're going to have binary data. So to discuss that, we'll have to talk about the subject of dependence. Then we'll go over some specific tests associated with matched pairs, contingency tables, and then talk about some other details like relationships with the Cochran-Mantel-Hansel test. So here I have some example data from Agreste's categorical data analysis of matched pairs binary data. So the data in this case was a survey where they were asked approval or disapproval of the politician, I believe it was a prime minister, or a British prime minister, on 2 occasions. So they had a first survey, approve or disapprove, and then they had a second survey, approve or disapprove. Okay, so in this 2x2 table is a little different than some of the other ones we've studied. So in this case, 794 of them approved on both occasions. So you know, every one of these 794 measurements then represents 2 measurements where 794 people said approve once, then approve again. 150 said approve the first time, then disapprove the second time. Okay? So a very common example of matched pairs data is case control data. So here we have cases and controls. We have an exposure and then an unexposed group. And in this case, we have 27 that were exposed that were both cases and controls, 29 that were exposed controls and unexposed cases, and so on. So how did this data wind up being matched, since a person, for most exposures, can't be both exposed and unexposed? For example, you can't both smoke and not smoke. So the way this usually works is they will say, let's say this is a retrospective study. They would take a collection of cases from charts and ascertain whether they were exposed or unexposed. And then they would go find, with respect to lots of demographic variables like age and other things, very closely matched subjects, closely matched controls, and then ascertain whether those controls were exposed or unexposed. So this process of matching pairs each individual observation because they were matched on all these other variables like age and perhaps other demographics. So it's different from an instance where you have a bunch of cases, then you just select a bunch of controls and hope that they're comparable. In this case, you've made subjects directly comparable by at least on everything that you can think of that's important, you've matched on. So here's 2 very common instances of matched binary data. Okay, so just expanding on these points, matched binary data can arise from several circumstances. For example, when measuring response at 2 occasions, or matching on case status in a retrospective study, matching on exposure status in a prospective study or a cross-sectional study,
and all of these cases, matching in general, right? Matching in general induces a dependence, and that has to be accounted for in the analysis. So the pairs on binary observations are independent. The pairs are dependent. In other words, your response at time 1 is correlated with your response at time 2, so our existing methods don't apply. However, we assume that person 1 who responded at time 1 and time 2 is independent of person 2 who responded at time 1 and time 2. So we're assuming independence across pairs, but dependence within pairs. Okay, so let's look at some notation. So here we're going to use our standard contingency table notation, where we have N11, N12, N21, N22 for the 4 cells, and then we have N plus 1, N plus 2, N1 plus, N2 plus. And so here's our data, the N's, and we're going to assume that the 4 cell counts, N11, N12, N21, N22, are multinomial, with N, which is the sum of them, trials, and then the associated probability is conveniently labeled pi11, pi12, pi21, and pi22. So in other words, we're going to assume that every pair of measurements, every time 1, time 2 collection pair of measurements is going to be a 1 or a 0 in exactly 1, 1 in one of these 4 locations. So the person will have either said yes at both occasions, a yes and then a no and then a yes, or a no and then a no. So there are going to only be a 1 in each one of those occasions, and the probability of being a 1 in that particular cell is pi ij. Okay, and then the multinomial is just the sum of all of these multivariate Bernoullis. Okay, and then we would denote the margins with plus N1 plus for the row margin, pi1 plus for the row margin of the probabilities, and so on. And so pi1 plus and pi plus 1 are the marginal probabilities of a yes response at the 2 occasions, disregarding the other occasions. So pi1 plus is the probability of saying yes at time 1, regardless of whether or not you said yes at time 2, and pi plus 1 is the probability of saying yes at time 2, regardless of whether or not you said yes at time 1. Okay? So marginal homogeneity is the hypothesis that these 2 marginal probabilities are the same. That's how it gets its idea, marginal homogeneity. Pi1 plus equals pi plus 1. And of course, because there's only 2 probabilities, right, if pi1 plus equals pi plus 1, pi2 plus equals pi plus 2. So the marginal probabilities are the same, and so we call it marginal homogeneity. You can do a very quick calculation, right? Pi1 plus is pi11 plus pi12. Pi plus 1 is pi11 plus pi21, right? And the pi11 is common in both of those. If you subtract them out, this hypothesis is identical to pi12 equal to pi21, okay? And so that hypothesis is referred to as symmetry because it is the off-diagonal elements of the table, and it's basically saying that the true probability matrix, the true probability 2 by 2 table, would satisfy being identical under the transpose if you were to transpose the table. And so that property is called symmetry, and hence this marginal homogeneity hypothesis is equivalent to symmetry only in the case of a 2 by 2 table. In more general cases, it's not true. So we clearly have an estimate for all of the pi's. So pi12 estimate is just the n12 divided by n. Pi21 estimate is n21 divided by n, and so on. Simply the proportion, the estimates of the true probabilities of landing in each cell would be the proportion of people who landed in each cell. So the obvious estimate of the difference between pi12 and pi21, i.e. how far away from symmetry you are, or in other words, how far away from marginal homogeneity you are, is just n12 over n minus n21 over n.
And it turns out, and this is maybe a little bit involved for us to go through, but under H0, a consistent estimate of the variance turns out to be n12 plus n21 divided by n squared. And so if you were to take this numerator and take this as our statistic n12 over n minus n21 over n, and divide it by the standard error, square root n12 plus n21 divided by square root of n12 plus n21 divided by n, divide those two, you would get a so-called z statistic. The preference in this case is typically to square that statistics. I think that matches the traditional development. And so the square of that statistic works out to have this convenient form, n12 minus n21 squared over n12 plus n21. And this follows a chi-squared distribution because, of course, the z statistic squared follows a chi-squared distribution with 1 degree of freedom. So this is the famous McNemar's test statistic, and you reject marginal homogeneity if this test statistic is large. So this test is called McNemar's test, and notice what's interesting about McNemar's test is that only n12 and n21 are used. They're the only ones that carry the relevant information about pi 1 plus and pi plus 1 being different. Now, n11 and n22, the concordant cells, contribute to the magnitude of this difference, but in testing whether or not they differ, it's only the discordant cells, n12 and n21, where people disagreed from time 1 to time 2. So that's an interesting fact about this test, and it's called McNemar's test, and it's a very famous statistic. Okay, so let's look at our test statistic from the approval rating example. We have 86 and 150 as the off-diagonal cells, so that's 86 minus 150 quantity squared over 86 plus 150. That works out to be 17.36. The p-value is extremely small then, right? Because, right, a chi-squared with 1 degree of freedom, it's going to be extremely unlikely to be above 9, 3 squared, where 3 is a way out in the tail of a standard normal. Hence, we reject the null hypothesis and conclude that there appears to be some sort of change in the opinion between the poles. At any rate, in R, you can just do McNemar.test. You have to give it a matrix. And again, this is one of these options. This is one of these instances where if you want to get exactly the statistic you work out by hand, you have to put correct equals false because it does a continuity correction by default. You want, in general, to leave the continuity correction in. I'm just putting it as false here so it matches exactly your by hand calculations. So it's not just enough to have a testing procedure. We'd also like to have some sort of confidence interval. So let's let pi ij hat be the sample proportions, and imagine if we want to estimate d equal to the difference in the marginal proportions. So in this case, this would be the difference in the marginal probability of an approve vote. So then this is equal to n12 minus n21 over n. So that estimates the difference in the marginal proportions. So we talked in the previous slide about the variance of this estimator, but the variance of this estimator under the null hypothesis. Let's talk about the variance of the estimator in general, and the variance works out to be this format, this form, pi 1 plus 1 minus pi 1 plus pi plus 1, 1 minus pi plus 1. So that's the, divided by n, that would be the kind of a difference in binomial type variance that you would expect to see. And because the samples are correlated, we have this correlation term minus twice pi 1 1 pi 2 2 minus pi 1 2 pi 2 1. Okay, and so that's subtracting off the correlation here, and what would happen, if basically there's a lot of counts in these off diagonal cells, pi 1 2
and pi 2 1, right? Then pi 1 2 and pi 2 1, pi 1 2 times pi 2 1 would be a big number. We'd have minus twice that big number, which would result in a larger variance. If the off-diagonal cells are really small and most of the data lie on the main diagonal, then pi 1 2 times pi 2 2 would be very large, and we'd have minus twice that number, and we'd wind up with a much smaller variance than the standard kind of difference in binomials variance. Okay, so we could take d minus the true difference in proportions divided by the standard error estimate here, and that follows an asymptotic normal distribution, we can use that again to create confidence intervals. I hope everyone at this point in the class could do something like that. So this last bullet point here, I say compare sigma d to what we would use if the proportions were independent. So compare the result to if, instead of asking the same people on 2 occasions whether or not they approve, what if we asked a different set of people each time? Then this minus twice part would go away. Okay? But what do we kind of think? We kind of think that people who approve on the first occasion would be more likely to approve on the second occasion. You might think, if you're in the U.S., if you're a Democrat, you might, approve of, say, President Obama on a first question. You would be more likely to approve on the second question, on the second time point. And the same thing with the people who would disapprove. If you were a Republican and you disapproved on the first time point, you'd be more likely to disapprove on the second time point. So, and that follows, that's a very frequent form of correlation, where the measurements tend to be concordant, they tend to agree. So that is exactly this case where pi 1 1 times pi 2 2 will be much larger than pi 1 2 times pi 2 1. In other words, things will tend to lie on the main diagonal of that 2 by 2 table, of the matched 2 by 2 table, in that people will tend to agree. And so if that's the case, this covariance term here will be positive, so we'll have minus twice this positive number, and you'll get a dramatic reduction in the variance. So in other words, failing to account for the fact that the same people were asked twice in this case would be a really kind of dumb thing to do, because you have a reduction. You'd have a reduction in precision. You get a much wider confidence interval if you fail to do that. So I think it's interesting in general. But even if it resulted in a wider interval to account for the dependency, you'd still want to do it, because that would give you the correct interval rather than one that's based on completely incorrect assumptions. Okay, so let's go through our example. Our density estimate is, our D estimate of the difference in the marginal proportions works out to be 0.04. You can plug into the sigma hat D squared formula here. It works out to be about 0.0095. For the sigma, not sigma D squared, and then the confidence interval you can do right here. It's plus or minus the standard error, the difference plus or minus 2 standard errors, and we get about 0.06 to 0.02. And notice what happens, though, if you ignore the dependence and just chop off this covariance term here and forget about it, then you wind up with a much significantly inflated standard error. Sigma D works out to be about 0.0175. So there's kind of an interesting relationship between the Cochran-Mantel-Hansel test and the matched 2 by 2 table. So imagine if you took each pair and represented their time first and second and gave their responses yes or no. And so we can really think of this as an extremely stratified setting, right, where every strata just has the 2 measurements, first, second, if you do that, then there's only 4 possible tables: time, first, second, response, yes, no. We get a 1 1 0 0, a 1 0 0 1, a 0 1 1 0, and then a 0 0 and a 1 1 like this. Okay, so imagine if you represented the table like represented all the tables like this, and I hope you can agree with me that this would exactly reproduce the 2 by 2 table. If you knew all these tables, you would exactly reproduce the 2 by 2 table. So here's a kind of a famous old result, that the McNemar's test is equivalent to the Cochran-Mantel-Hansel test, where the subject is the stratifying variable and each 2 by 2 table is the observed 2 by 2 table from the previous slide. So you can almost think it's, and again, I put here that this representation is only interesting for conceptual purposes, but I think it is interesting to note that you can really view the subject, or if you're doing matched pairs, if you really think of that as an incredibly stratified circumstance where there's, only two counts per table, then and analyze the data that way with a Cochran-Mantel-Hansel test, you wind up with exactly the same test as McNemar's test. It's just kind of a conceptually neat idea that, I don't know, it's just kind of a fun little fact. Another fun little fact is that McNemar's test has an exact version. And so consider only the off-diagonal cells, the discordant cells. And then under the null hypothesis, pi12 over pi12 plus pi21 is 0.5, right? Just look back at the null hypothesis. If the two are equal, then 1 over the sum would be 0.5. Okay, then it turns out also under H0 that N21, given the sum, right? So N21 or N12 given the sum is binomial with success probability 0.5 and N1 plus N2 trials. So you can exactly use this to come up with an exact p-value for matched pairs data. Basically, what we're doing is saying under the null hypothesis whether that the two off-diagonal probabilities are identical, whether you landed in the upper right-hand cell or the lower left-hand cell, is a coin flip for every matched pair, and we would have evidence against the null if a lot more wound up in one of those two cells. Okay, and so this is an example of, it's actually highly related to and we'll cover this as well, the so-called non-parametric sign test. And what you're saying is kind of under the null hypothesis, things should be exchangeable, whether they agree in terms of approving then disapproving or disapproving then approving, related to our approval example. And so let's actually work out an example. Okay, so here we want to test H0 that pi21 equals pi12 versus HA pi21 less than pi12, and I put in parentheses that this is pi1 plus less than pi plus 1. Pi plus 1 is less than pi1 plus. So pi plus 1 is the approval at time 2, and pi1 plus is the approval at time 1, disregarding time 2. Okay, so this is testing whether or not the approval at time 2 is lower than the approval at time 1. Okay, so that's the direction that the margin is looking at. So we saw 86 people that disapproved on the first survey and approved on the second survey, the N21 cell, and we want to test whether or not that's smaller than one would be expected by chance. So we want the probability of getting data as or more extreme in favor of the alternative. So probably X is less than or equal to 86, and then because we're doing the exact version, we'll condition on the total sample size, the 86 plus 150, the number of off-diagonal counts, and we'll use a binomial with success probability 0.5, and that probability is about 0. So we would reject the null hypothesis. This, for a two-sided test, just double the smaller the one-sided test for the purposes of this class. If you do it in R, it'll maybe do a slightly better procedure than that. Okay, I want to cover another thing that's often omitted when discussing these things. The marginal odds ratio would be the odds of approval at the first, the comparison of the odds of approval at time 1 relative to the odds of approval at time 2. So here I put time 1 in the numerator of the odds ratio and time 2 in the denominator of the odds ratio. So what I have are the odds of approval at time 1 in the top versus the odds divided by the odds of approval at time 2 in the denominator. So that is it's a marginal odds ratio because these are all marginal probabilities, right? And that is of interest exactly in the same way the difference in the marginal probabilities is of interest. But it's a different setting, right? It's a different setting than if we just sampled some people at time 1 and a different set of people at time 2, and we could assume they're independent. These are exactly the same two people sampled twice, so we need to account for that. At any rate, just like the ordinary odds ratio, the way that we conduct the odds ratio confidence interval, the marginal odds ratio confidence interval, is first we first calculate directly the marginal log odds ratio. It's given by theta hat here, and then the variance of that estimator, hence you square root it to get the standard error, is given by this guy right here, where you put hats over everything and estimate them with the relevant sample proportions in order to get the estimated standard error. And so you can use that to create a confidence interval for the marginal log odds ratio when you have matched paired data, would match 2x2 data. Okay, so in the approval rating, the marginal odds ratio compares the odds of approval at time 1 to the odds of approval at time 2. The log odds ratio works out to be 0.16. The standard error works out to be 0.039. And then the confidence interval for the log odds ratio then would be 0.16 plus 2 standard errors. It gives you this right here, about 0.084 to 0.236. You want to compare these to 0 because it's all in the log scale, and then exponentiate it if you want the confidence interval for the marginal odds ratio rather than the marginal log odds ratio. Okay, I wanted to cover something that always comes up when I teach this class in person because several people have seen a different formula for the odds ratio for 2x2 tables. And so I want to cover the one that they see, and there's a difference. One of them is a conditional odds ratio, and the other is a marginal odds ratio. So imagine if we created a logit model for our approval rating data, where we say the logit, the probability that person I says yes at time 1 is alpha plus ui, and a logit of the probability that person I says yes at time 2 is alpha plus gamma plus ui. So ui is this person-specific effect, alpha is common across both times, and gamma is the log odds ratio comparing the approval rating for a given person at time 2 to time 1, right? So notice you have to compare the same person because otherwise these UIs would not cancel out when you took the difference in these two logits. So each UI contains a person-specific effect. So a person with large UI is likely to answer yes at both occasions. A person with small or negative UI is likely to answer no at both occasions. So and then gamma here is the log odds ratio comparing a yes at time 1 to a response of yes at time 2. And in this case, gamma is a subject-specific effect. You only interpret gamma if, in fact, these UIs cancel out. And that's where you get the conditional, this so-called conditional formula for the odds ratio. So one way to eliminate UI is to do a so-called conditional estimator and a condition on the total number of yes responses for each person. So what you wind up with is only looking at the discordant cells again, and then the conditional ML estimator for this log odds ratio and its standard error turn out to be log of the ratio of the off-diagonal counts, and the standard error turns out to be square root of 1 over the off-diagonal counts.
So I think people prefer this because it's a simpler formula. But notice it has a very different interpretation. In one case, we were comparing the marginal probabilities. In the other case, we had this formulation where we had these person-specific random effects that had to cancel out. In other words, one of them averaged across people, and then the other one conditioned on people. So they have different interpretations. One is called, the marginal one is called a marginal odds ratio and its confidence interval, and this one is called a subject-specific odds ratio and its confidence interval. So they have different interpretations. The difference in interpretation is extremely subtle, but it still exists, and that's why you get different answers. So let me just summarize here. The marginal ML has a marginal interpretation, and the effect is averaged over all these UI values if you want to put it back to the same model. Okay, the conditional ML estimate has a subject-specific interpretation, and so you know, if you ask me when would you want to use one versus the other, I kind of think if you were talking about kind of policy type questions, then you would want marginal statements. And then if you want like kind of clinical type questions, then you probably want subject specific type statements. But it's you know, it's not perfectly clear. But nonetheless, that's where the difference comes from. It's the fact that basically the logit is not a linear function, and so you get a difference between sort of averaging over people and then creating odds ratios, or creating odds ratios then averaging odds ratios. You just get different answers, and so that's the difference between those two. I think it's a very subtle thing, and I think for the purposes of this class you can ignore it. I just wanted to present it in case you were among the subset of people that happened to see this formula log n21 over n12 plus the standard error, that the reason that it's different is because we're kind of taking a different approach. And the reason I do the marginal approach, especially in this class, is because we talk about everything related to 2x2 matched 2x2 tables that we discuss is marginal. So we talk about McNemar's test, the exact version of McNemar's test, and then the marginal odds ratio. Everything is related to the marginal probability. So if you're okay with that, then just leave it. But if you're not okay with that and you need to know why is this different from the formula that you saw before, perhaps in an epi class or in another biostat class, that's the reason. It's a different formulation. Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 12. We're going to be talking about nonparametric statistics. Okay, in this video we're going to be talking about nonparametric tests, which include the sign test, which was useful for paired tests, which is kind of related to McNemar's test, the signed rank test, which is also for paired data. We'll talk about Monte Carlo versions of that test. We'll talk about independent group test, and then from that the Mann-Whitney test and Monte Carlo versions of that, and then their relationship to permutation test, which are very closely related. Okay, so very briefly, we're going to be talking about here about so-called nonparametric tests, but very kind of classical nonparametric tests. And these are often called distribution-free. That, of course, doesn't mean that they're assumption-free. They involve assumptions, for example, sampling assumptions such as IID-ness. But they require fewer assumptions than parametric methods. They have a tendency to focus a little bit more on testing rather than estimation. Which maybe is a problem, but there are estimation techniques that follow, though they also tend not to be very sensitive to outlying observations. And they're especially useful for data like ranks, if the data actually come in the form of ranks, because they often involve transforming data to ranks. They're not uniformly wonderful because they do throw out some information, which is their problem. So and because of that, they may wind up being less powerful than their parametric counterparts when the parametric assumptions are true, of course. And then, you know, for larger sample sizes, they become about as efficient as their parametric counterparts, so they are pretty good tests. So here's some data from this wonderful book from Rice called Mathematical Statistics and Data Analysis. I highly recommend this book. I use the second edition. I don't know if that's what they're still on. Anyway, this data concerned 25 fish. They were taking mercury levels from the fish in parts per million,
and they had them at 2 locations on each fish. So fish 1, they had a measurement of 0.32 and 0.39 and so on. Okay, and then just for reference here, I've added the difference between those 2 measurements, subtracting the p from the SR one each time, and then I'll show the ranking and the signed ranks. I'll explain those in a minute. But this is the data we're going to use as motivating data. Here we want to test whether the mercury levels taken at location P differ from those of location SR. Where here, you know, we're taking 2 measurements per fish, trying to control for the fish-to-fish variability by taking both measurements on each fish, having each fish serve as its own control. But we're going to be talking about non-parametric tests. So what we're interested in or concerned about is the validity of the assumptions that go into typical tests, such as normality. Okay, so let's let DI be the difference for each fish. In this case, I'm subtracting P minus SR. And then let's let theta be the population median of the difference of the differences DI. And we want to test whether that median is 0 versus the median being non-zero. Now, by the definition of the median, if theta equals 0, only if the probability of a difference being greater than that value, 0, is exactly 0.5, right? That's the definition of a median. Same thing for less than 0. So as a test statistic, why don't we just count the number of times that D is bigger than 0? And if it's excessively large or excessively small, then that's going to dispute the idea that the median is exactly 0. So just as an example, if all the differences were positive, then 0 couldn't be the median, because you wouldn't expect a large sample where every single measurement was larger than the population median. Okay. Anyway, then X here, each difference, if we're assuming the fish pairs are IID, then each difference is a coin flip with a 50% chance of being above the median or 50% chance of being below the median. So the number of times it's larger than 0 is binomial, n in P, and in this case P is 0.5. So our sign test just tests whether P is 0.5 using this data X, and you can do an exact binomial test like we've talked about before. Okay, so let's go back to our example. So theta is the median difference of P minus SR. Our null hypothesis is that theta equals 0 versus the alternative that it's different from 0. The number of instances where the difference is bigger than 0, in this case, go back to the table, it works out to be 15 out of 25 fish. And the binomial test then is the question of whether 15 is large, 15 positive instances out of 25 is large. Now our expected number out of 25 is 12.5. So, you know, 15, we don't know whether 15 is excessively large. Well, in this case, it turns out that no, 15 is not excessively large. It has a 0.42% chance of happening under the null hypothesis for a 2-sided test in this case. And again, we could have used a large sample test. I don't know why, because we can do an exact test in this case, but we could have used a large sample test, and that's prop.test, and you get a chi-squared statistic then of 0.64, a p-value that's quite similar, 0.42. So at any rate, the idea is that this is simply just testing. If you're going to assume that levels of one are higher than the other, then you're just going to count the number of pairs from the matched pairs where it's higher, and is that excessively large relative to a coin flip for each pair. So that's the sign test. Now you might be wondering what's wrong with this. So let's discuss some potential problems with this test, because it doesn't use very many assumptions, right? We aren't using very many assumptions. We're using that the fish pairs are IID, and that's about it, right? That's the only assumption that we're using. But let's talk about what's maybe some of the problems. Okay, so the biggest problem is, of course, that the magnitude of the differences is discarded. So it's potentially not as powerful as you'd hope, right? It'd be different if maybe if you only got half of them as being positive, but all the ones that were positive were much larger differences, and all the ones that were negative were really small differences. Then that would be different than if they were kind of spread equally between above and below 0. So I would say that. But then the other thing I would mention is there's nothing specific about 0. You could have tested any median, theta equal to theta naught, by calculating the number of times the difference is bigger than any specific value, testing whether the median is bigger than any specific value. What's interesting about that, then, we won't talk about this, but it is kind of interesting, right, that you can do this for any value of theta. So that means you can find the values of theta for which you fail to reject and the values of theta for which you reject. And then, of course, if you can do that, by a grid search or say, something like that, then you can invert that and get a confidence interval for the median. And so this is kind of an interesting way, a very highly non-parametric way to get a confidence interval for the median of a set of data. Okay, so the biggest problem is, of course, that the magnitude of the differences is discarded. So it's potentially not as powerful as you'd hope, right? It'd be different if maybe if you only got half of them as being positive, but all the ones that were positive were much larger differences and all the ones that were negative were really small differences, then that would be different than if they were kind of spread equally between above and below zero. So I would say that. But then the other thing I would mention is there's nothing specific about zero. You could have tested any median, theta equal to theta naught, by calculating the number of times the difference is bigger than any specific value, testing whether the median is bigger than any specific value. What's interesting about that, then, we won't talk about this, but it is kind of interesting, right, that you can do this for any value of theta. So that means you can find the values of theta for which you fail to reject and the values of theta for which you reject. And then, of course, if you can do that, by a grid search or say, something like that, then you can invert that and get a confidence interval for the median. And so this is kind of an interesting way, a very highly non-parametric way to get a confidence interval for the median of a set of data. So Wilcoxon thought about this problem of discarding the magnitude of the differences. And he said, well, why don't we, instead of using just the signs, why don't we also use the ranks of the differences? So using the ranks saves some of the information regarding the magnitude of the differences. We're still testing whether the median is zero versus the three potential alternatives. And we can create a statistic, and I'll say that appropriately normalized, this statistics follows exactly a normal distribution. But if there's no ties, then the exact small sample distribution is known, and then why use the normal distribution? The one benefit of the normal distribution in this case is because the small sample distribution is known, we can evaluate how accurate the normal distribution is in general. So it's different than a standard normal distribution where you don't know the exact the associated small sample distribution, so you can't tell how well the normal approximation is working. So I would say at least that one aspect of normal approximations in non-parametrics test is a little bit different than normal approximations in general, because we can evaluate we have a much better sense of how well the normal approximation is working. So here's the signed rank procedure. So we take all the paired differences, just like we did before. We take the absolute values of the differences, which is new. Now we haven't done that. And then we rank these absolute values from least to greatest, throwing out the ties, throwing out the zeros, is what I mean. And if there's ties, right, there's a difference between ranks of zero and ties. If there's ties, in other words, two differences are identical but non-zero, then we use the average rank. We assign the average rank to those. And then after we've done the ranking, we multiply them by the sign of the difference, +1 for a positive difference and -1 for a negative difference. And then we calculate the sum of the positive ranks, and that's the sign rank test. Now, so think about what this is doing. Let's suppose we did have the case where all the big measurements were positive and all the smaller measurements were negative. Smaller differences were negative, smaller in absolute value differences. Then what you would see is that all the small ranks would have a negative sign and all the large ranks would have a positive sign. So the sign rank statistic would be very different from what you would expect by chance, where the signs are distributed equally among the ranks, versus the sign test by itself, which if roughly equal numbers were above and below zero, then you would get the same, then you could get a statistic that was highly looked a lot like it was from the null. So just to reiterate this point, if the median is large, then W plus should be large. If the median is small, then W plus should be small. And this W plus, it does follow a normal distribution for large samples. For small sample sizes and large sample sizes, but especially for small sample sizes, we can work with an exact distribution under the null hypothesis, and we can you can get critical values from a table, but you can get the critical values in R pretty easily. So it's maybe a bit involved to exactly work with the null distribution. We'll do some of it, of the exact distribution of the statistic. We'll do some of it. But I wanted to at least talk about Monte Carlo so you could at least see that, okay, so we can pretty easily figure out what the exact distribution is provided there's no ties. What you could do, so if this procedure is invariant to the distribution being used, you have to simulate. So what you could do is simulate n observations from any distribution that has theta as its zero, theta is zero, its median is zero, and then rank the absolute values of the data, retain the signs, calculate the signed rank statistic, and apply this procedure over and over again. And you'll have just used Monte Carlo to get the exact distribution, especially because we're assuming this distribution is invariant to, we could use any distribution, like for example the normal distribution, the standard normal, and that would give you the exact small sample distribution. But we can actually go further than that. This distribution under the null hypothesis, right? The signs are equally likely to be distributed anywhere among the ranks. So all you have to do is actually take the ranks of the numbers between 1 and n and just randomly allocate the signs, okay? And that's exactly the, flip a coin for each rank value. So take the rank 1, flip a coin with success probability 0.5, take the rank 2, flip a coin, and so on. And then you've just generated this distribution exactly. You haven't had to mess around with a normal distribution or something like that. But I present it this way just to show you conceptually that, well, if this test really doesn't depend on the distribution, then you could pick any distribution and just simulate under a null distribution. But I'm contending that it's even easier than that. All you have to do is take the ranks, i.e. the integers from 1 to n, and flip a coin for each rank, and then you'll have exactly giving a +1 and a -1 for a head or a tail for each rank, and then you'll have exactly calculated the null distribution of the signed rank statistic. So it works out very conveniently. Okay, so I in fact actually say this explicitly on this slide here, where here's a little bit more elegant way to do it. Take the ranks 1 to n, randomly assign the signs as binary with probability 0.5 of being positive and 0.5 being negative, and then calculate the signed rank statistic. At any rate, if you wanted a Monte Carlo p-value, you would just apply this procedure, simulate over and over again, and calculate the percentage of times your test statistic was more extreme, and then that would be the probability of obtaining a test statistic as or more extreme. The average of the number of instances where your simulated test statistic was more extreme than your observed test statistic would be a Monte Carlo approximation to your p-value. And then let me just go through the large sample distribution. I'm not going to derive it. Am I going to derive it? No. It's actually pretty easy to derive, to be honest. If you think about it, right, it's really a binary times 1 to n, so it's really pretty easy to work with. But so maybe as a homework assignment, derive these things that I put right here. You need some finite sum results for the sum of the integers from 1 to the n and sum of the integers squared, but other than that, it's a pretty easy problem. But let's not waste time with that, because I don't see the true benefit of using the large sample approximation when you can use the small sample one anyway, unless there's ties or something like that. At any rate, the expected value of our statistic is n times n plus 1 over 4. Under the null hypothesis, the variance is this guy right here, and so our test statistic is just w plus minus its expected value divided by its standard error. That limits to a normal 0, 1. You can do you can do the correction for ties if you want, but under the null hypothesis, we can still do an exact small sample test, so why not just do that? Okay, so here, let's go through our example. Here we take our differences. We can do Wilcox.test, diff, exact equals false, and then it's going to actually go through, I go through the calculations right here. It'll agree with the results of Wilcox.test. So I think, now that I'm looking at this, I'm not sure, you may have to put correct equals false or something to make sure you're not correcting for ties. But anyway, double check to make sure that they're the same. They should be either exactly the same or very close, and the correction for ties is the distinction, which we don't really cover the little technical details like that in this class. At any rate, you get an expected value W plus is 150, the variance is 1,225, so our test statistic is our observed W plus 194.5 minus this expected value 150 divided by the standard error, works out to be 1.27. Of course, that's not significant on the z-scale, and so our p-value in fact works out to be 0.21. So what is this suggesting? This is suggesting that we can't rule out that the median is in fact 0. Okay, so that's the non-parametric equivalent to the paired test. Let's talk about the non-parametric equivalent to the unpaired test. And here we're comparing two measurement techniques, again from this wonderful book from Rice, Mathematical Statistics and Data Analysis. Anyway, they were comparing two measuring techniques, and the units are in degrees Celsius per gram. And here we have a group measured with method A and a group measured with method B. And we want to kind of test, are the measurements the same? And we'll be a little bit more formal about the hypothesis in a minute. But so let's talk about how we can do that. And so what basically the method we're going to use is, not to be confused with method A, method B, the technique we're going to use for testing whether the two methods are the same is to kind of take the A-B labels and shuffle them on every measurement. But because to be non-parametric, we're going to shuffle them on the ranks. But then we'll talk later on about shuffling them on the observed values themselves. That's the so-called permutation test. Okay, so what we're going to do is test whether or not the two measurements, two treatments have the same location. What I mean is kind of the distributions are centered at the same place. We're going to assume that the measurements are independent and identically distributed, have independent identically distributed errors that are not necessarily normal. So there's a difference between the errors being normally distributed versus the measurements being normally distributed. And that's one way to, so this is the problem with this test, is that's one way to write out the assumptions. Another way is to view this as a test of a kind of a distributional shift, that the distribution for method B is kind of uniformly shifted relative to that of distribution A. And that's called a stochastic shift for the two arbitrary distributions. So you can either kind of specify the hypothesis kind of tightly, that they're centered in the same location with IID errors, and then you get the same test statistic and it has a set of power for that particular collection of hypotheses, versus a very general one about a stochastic shift and it has a different kind of power for that set of hypotheses. So all we're going to use is we're going to disregard labels, method A, method B labels. We're going to rank the observations, and then we're going to use the sum of the ranks by discarding within each treatment label. And this is called the Wilcoxon rank sum test. It's equivalent to the so-called Mann-Whitney test as well. So you might call it, I don't know, the Wilcoxon Mann-Whitney test. In R, it's Wilcox.test. And I should say that there are some slight differences between the tests depending on how the tests work out to be the same, but they characterize the test statistic in slightly different ways. But it's still, I think, correct to attribute the test to Wilcoxon and Mann-Whitney. Mann and Whitney being two researchers. So the procedure is to discard the treatment labels, method A, method B in this case, rank the observations without concern over which treatment they were, calculate the sum of the ranks in the first treatment, which is arbitrary. You could pick either the first treatment or the second treatment, you get the same value, but you have to pick one of the two. And then you either compare your statistic with the asymptotic normal distribution of the statistic, or you can calculate the exact distribution under the null hypothesis. So here I show the ranks for method A, the ranks for method B. In case the two observations are tied, we give them the average rank and then move on. The sum of the ranks for method A was 180 and the sum of the ranks for method B was 151. By the way, the sum has to add up to 231, by the way. And let's show, just because that's a fun result, let's show why this is the case. So Gauss supposedly did this as a child. There's some hypothesis that this story is apocryphal, but whatever. Let's, for our purposes, let's assume he did it when he was a kid. So as the story goes is that his teacher asked him to add up the numbers between 1 and 100, and he went down, sat at his desk, and just came back with the answer. And the teacher said, "That's not possible. How did you do that?" And then he went and really did it and got the same answer. At any rate, I think the story is probably apocryphal, but here it's really a neat way to show it. Is we could write x as the sum of the digits from 1 to n, 1 plus 2 plus 3, and in that way. Or we could write it as n plus n minus 1 plus n minus 2. It's the same exact thing all the way down to 1. So if you add the two together, you get 2x equals, and in this case, notice 1 plus n is n plus 1, 2 plus n minus 1 is n plus 1, 3 plus n minus 2 is n plus 1, and so on. And so 2x is n times n plus 1, which is exactly what's happening here, is the number n plus 1 added up n times, so it's n times n plus 1. So then x has to be n times n plus 1 over 2. Okay, so let's let W be the sum of the ranks for the first treatment. And then, you know, if a treatment has more numbers in it, then it's under the null hypothesis, it's going to have a higher sum just by virtue of having more numbers. So we need to know NA and NB, the number in each sample. And it turns out that the expected value of the sum of the ranks under the null hypothesis from the first group works out to be this guy, NA times NA plus NB plus 1 divided by 2, and so on with a standard error given by this guy. And then we could create a test statistic, which is our W, our sum of our ranks in our first group, minus its expected value divided by its standard error. It turns out to be normal 0, 1. Of course, you can calculate the exact distribution as we described before. Okay. So let's go through our example. In this case, our sum of our ranks was 51. If we did method B, our sum of our ranks was 51. Here's our expected value and standard deviation of that statistic, 88 and 13. Our test statistic works out to be negative 2.68, p-value of 0.007 for two-sided. And then you can also do the function wilcox.test, and it'll perform the test to you, both for the 1 and 2 sample version. You have to read over the documentation for wilcox.test. If you give it 1 vector, it's going to do the sign rank test. If you give it 2 vectors, it's going to do the rank sum test. So some final notes about the non-parametric test is they tend to be more robust outliers than their parametric counterparts. They do not require normality assumptions. They often have exact small sample versions. And their big trick is to focus on the ranks rather than the raw data. There is some loss in power over their parametric counterparts, assuming the parametric assumptions are met, but the loss in power is often not so bad. And then I just want to emphasize, non-parametric tests are not assumption-free. They're often distribution-free. For example, the signed rank test, you really kind of have to assume that the distribution is symmetric. But either way, in all of the tests that we considered, you have to have a sampling model that the data is IID, right? That's an assumption, a big assumption, the biggest assumption. So it's, you know, so just to emphasize that non-parametric tests are not assumption-free. They're often distribution-free, but not assumption-free. And then, so I just wanted to remind people about permutation tests, because we've already talked about them a little bit, sort of with regard to Fisher's exact test, but here we could also talk about them in general. So permutation tests are similar to these rank sum tests, though they use the data rather than the actual ranks. So under the null hypothesis for the rank sum test, we had the collection of ranks, and our null distribution was just obtained by permuting the treatment labels. You know, we had NA treatment A labels and NB treatment B labels, and we just permute those with respect to the ranks. That would retain NA labels and NB labels, but they would be randomly allocated among the ranks. a permutation test is exactly the same thing. You're just doing it to the raw data rather than the actual ranks, and you have to come up with the statistics. And I go through the procedure here. You could permute the ranks and then create a rank statistic. I also want to, I want to distinguish, there's two ways to think about this. One is, imagine if your treatment was actually randomized, then you can think of the permutation test as actually kind of redoing the randomization. And in that case, the permutation test is called a randomization test if you interpret it that way. But you can also kind of perform the permutation test even if the treatment wasn't randomized, because you're thinking along the lines of, well, my null hypothesis is that my labels A and B are exchangeable between the groups. So either way, it kind of makes sense, but it changes your interpretation a little bit of the test in either way. But at any rate, the Fisher's exact test, the rank sum test, Fisher's exact test, which works on collections of binary data, the rank sum test, which works on ranking the observations, and then the permutation test all have the same basic principle, is that under the null hypothesis, however we're interpreting it, is that treatment labels are, the NA and NB treatment labels are exchangeable, and our null distribution is obtained by permuting those labels across the values. In Fisher's exact test and the permutation test, we're permuting them across the actual observed values, and then in the rank sum test, we're converting the data to ranks first and then permuting across the ranks. So just to reiterate, this is an easy way to produce a null distribution for a test of equal distribution. It has kind of a similar flavor to the bootstrap, maybe not exactly. This produces an exact test. It's less robust but more powerful than rank sum test, because you're not throwing away the data. With rank sum test, you throw away the actual units and you go with ranks. So you gain robustness at the expense of power. This, you get a little bit more power under certain assumptions, but you lose some of that robustness. And it's very popular in large-scale big data applications like genomics, for example, and neuroimaging. So this final picture is just what you would aspire to get from a permutation test. You would permute method A, method B labels. You would say calculate the t-statistic as if the permuted labels were the observed labels, and you do that over and over again, and you get a null distribution of t-statistics, right? And then this vertical line is where our actual t-statistic occurred. And then if that's the case, then you, or whatever statistic, it doesn't have to be a t-statistic, but that's a reasonable statistic to do. And then the percentage of the simulated statistics that are more extreme than our observed statistic is our exact p-value. So that's a permutation test. If you were to do it with the ranks, then this would just be simulating the exact small sample distribution of the rank sum statistic. If you were to do it with the raw data, then it's a so-called permutation test, and so on. Okay, so let's move on to another very important distribution, maybe not quite so important as the normal distribution, but awfully darn important. Maybe the second most important distribution. I think a compelling case could be made for the Poisson distribution being the second most important distribution. I don't know. I have leanings in that direction. Okay, so the Poisson distribution is used to model counts. The Poisson mass function is this guy, lambda to the x e to the negative lambda all over x factorial, where this is the probability x takes value little x for parameter lambda. And it turns out that lambda is an easy parameter because it's just the mean. Its expected value of x is lambda. But what's interesting about the Poisson random variable is that its variance is also lambda. Well, we knew its variance had to be some function of lambda because the Poisson distribution only depends on the one parameter, but it is kind of neat that it works out that the mean and the variance are equal in this case. And then notice in this case x ranges from 0 to infinity. So you might use Poissons to model counts that are sort of unbounded, right? So however many people show up at a bus stop, sure, there's some bound, there's only so many people in the world, but for all intents and purposes, that's an unbounded number. You can't really put a number on
what the limit of that really is in a meaningful way. Of course, it's bounded by the number of total people, but it's kind of conceptually unbounded in a different way than if I flip a coin 5 times and I know I'm going to flip it 5 times. That's a different problem, right? We know that the most number of successes I can get is 5. Whereas if you're modeling how many people show up at a bus stop, then you really kind of don't know a realistic version of what that upper limit would be. So some uses for the Poisson: event time data. If you're counting anything like the number of people that show up at a bus stop, the number of photons that are detected from a nuclear reactor per given unit time, these are all reasonable things to model with Poisson. So radioactive decay is the classic one because you can kind of demonstrate via some limiting arguments that radioactive decay does follow a Poisson distribution. Survival data, it turns out there's this deep connection between a lot of these classic survival analysis models and Poisson models. Survival analysis being modeling the time until some event, classically time until death for looking at diseases. Any kind of unbounded count data you're going to model as Poisson. Contingency tables, so if I collect a bunch of people, collect a bunch of characteristics on them, and just create cross-classified tables of how many people fell into this different classification, that's called a contingency table, and it turns out modeling the counts of contingency tables, you model them with Poisson, usually. And then binomials, which are clearly not Poisson, if you have n being large and p being small, then people tend to model them as Poisson. In fact, people do this so frequently that they don't even bother to mention that they're approximating a binomial with a Poisson. So if you're modeling, say, for example, a disease that's very rare and you have large sample sizes, like what's the, let's suppose you're studying autism and vaccination rates. So the percent of kids with autism is very small. The number of kids that gets vaccinated is very large. So if you were to model the autism rates, you would do it probably more likely with a Poisson than you would with a binomial. I take that example because I saw someone doing that just the other day, that they were studying that question. Okay, so the Poisson derivation this is where it comes from. The Poisson distribution comes about from the so-called Poisson processes, and Poisson processes, if you define like a mean number of events per unit time, you let the kind of a window h that you're looking at be very small, and assume that in that interval of length h, the probability of an event occurring is lambda time h, while the probability of more than one event is negligible. So imagine you're monitoring your bus stop, you're saying, I'm going to look at windows of 0.1 second, and then only one person can show up at a time in that 0.1 second. So let's just assume no two people are showing up holding hands or something like that. Everyone's it's a commuter day where everyone's coming by themselves. That if you take a small enough time window, you're only going to get one person showing up to the bus stop at any given time. And then whether or not a person shows up in one interval doesn't impact whether or not a person shows up in another interval. That assumption, maybe all of these for the bus stop example are suspect, but at any rate, these are the underlying assumptions for something to be a Poisson process. And then if you take any interval and you count the number of events that occur in that interval, that's a Poisson random variable. And that's the original derivation of the Poisson random variable through Poisson processes. So I want to emphasize that Poissons are really high. The idea of studying rates and using Poisson is really kind of highly tied together. The lambda parameter from a Poisson is really has a unit, right? So if I'm looking at radioactive decay, right, this is the lambda is the decay per unit time, and t is the number of that many time points that I monitored. So if I wanted to look at radioactive decay per minute, t would be in minutes, and lambda would be the rate per minute. So note lambda is expected value of x over t is the expected count per unit time, and t is the total monitoring time. So we always use the Poisson distribution this way, where we think of t. Sometimes t is 1, in which case it kind of drops out. But in our heads we're always thinking of a Poisson random variable as being kind of a model for rates. Here's the Poisson approximation of the binomial if you ever need to use it. We assume that lambda is n times p, and x is a binomial np. Recall we're making lambda np, and n gets large and p gets small, but lambda stays constant. Then you can approximate x as Poisson. Let's do it. So imagine the number of people that show up at a bus stop is Poisson with a mean of 2.5 per hour, and you're watching the bus stop for, oh, I'm sorry, this is not an example of a Poisson approximation of the binomial. This is just a regular Poisson. So we want the number of people that show up at a bus stop is Poisson with a mean of 2.5 people per hour. We watch the bus stop for 4 hours. What's the probability that three or fewer people show up the whole time? That is exactly just a Poisson probability. 3, remembering that when we do P for probability distribution, it does 3 or less, okay, which is what we want, so we put 3 in there. Lambda is 2.5 times the number of hours that we monitored, 4, and that works out to be 1%. Okay, so see how we used it? Lambda was the event per unit time, and t was the number of units of time that we measured. Okay, so there's your Poisson example. Let's go through an example of the Poisson approximating the binomial. We flip a coin with success probability 0.01, so p is small. We flip it 500 times. What's the probability of 2 or fewer successes? So again, p binom 2, size equals 500, prob equals 0.1. Here's the exact calculation. It works out to be 0.12. Here's the Poisson approximation, p Poisson 2, lambda equals 500 times 0.01, right? N times p, and that works out to be 0.1247, so pretty close. Okay, so that's the Poisson approximation of the binomial. So here we just showed you exactly how accurate they were in this specific case. And then in your regression class, you actually cover modeling counts using kind of a Poisson version of regression. So it's a very convenient model, and it's great for modeling things like rates. And I would just say this, I would also mention this Poisson approximation of the binomial is so common that people don't even acknowledge that they're doing it. That it's just sort of done immediately in a lot of applications, particularly certain epidemiological applications. If you're studying something like an infection or something like that that's rare relative to the size of the population you're studying, people just automatically use Poisson approximations. Okay, so let's just discuss maximum likelihood a little bit more. The value of theta where the curve reaches its maximum is the so-called maximum likelihood estimator. So it is the value of the parameter that is most well supported by the data given the likelihood. So it's called the maximum likelihood estimator, or MLE. So we could just define the MLE as the argument maximum of the likelihood over theta. And it has this nice interpretation that the MLE is the value of the parameter that makes the data that we observed most probable, right? So the likelihood is kind of thinking of the joint probability of the data as a function of the parameter. So it's sort of like tuning that parameter to where it makes the probability that we observe the probability of the data that we observed most probable, which seems to make sense because we did observe the data that we observed, so it must be somewhat probable. So here's some results. If we have some normal data, IID normal data, the MLE of mu is x bar, and the MLE of sigma squared is the bias sample variance. We divide by n instead of n minus 1. If x1 to xn are Bernoulli, then the MLE of p is x bar, the sample proportion of 1s. If xi are binomial, ni, pi, then the MLE of P is the total proportion of ones. Okay? If the x's are Poisson lambda t, if an x is Poisson lambda t, then the MLE of lambda is x over t, the rate. If you have a bunch of IID Poisson random variables, then the MLE of lambda is the total number of events divided by the total rate. Okay? So let's go through this example right here where you saw 5 failure events for 94 days of monitoring a nuclear pump. Assuming a Poisson model, plot the likelihood. And by the way, right, we know what the MLE is, right? The MLE is 5 over 94. Okay? Let's see. So my lambda is the parameter I'm interested in. So I'm just going to create a grid of lambda values to create my function. My likelihood is just the Poisson density, now viewed as a function of all these lambda parameters, but remembering that in each case I sampled for 94 days with the data fixed at 5. And then the MLE for lambda, lambda hat, is equal to 5 over 94. So 94 times lambda hat is just 5. So if I plug in 5 for lambda, I will get the MLE. Okay. I will get not the likelihood at the MLE. So if I plot my lambda by my likelihood, and then I don't like the frame around it, line width is 3, type equals L connects it in a line, and my x, so if you type expression, it'll actually put the symbol lambda rather than the word lambda. So you can be fancy like that if you'd like. And then here's this red line is just showing where the MLE is, and then of course the likelihood achieves 1 at that point. And then I draw these two kind of reference lines. I'll talk about them in a second. Okay, so this is the likelihood. So this is a plot of the estimated rate by the evidential support for that estimated rate. So if we wanted to compare, you know, this point and this point, it would be that ratio of those two guys. Okay. Now, I like to draw these reference lines for the following reasons. So this reference line is at 1/8, and this reference line is at 1/16. Okay? And the reason I like to draw these reference lines is as follows. You know, this point, you know, so I know that this line is 1/8 right here. So take this value of lambda right there and compare it to the MLE value of lambda, right? This ratio, because the top is 1 and the bottom is 1/8, that ratio is 8 if you put the MLE in the numerator, and 1/8 if you put this value in the numerator. And the same thing would go for this value right here at that corner. So basically, the MLE is 8 times better supported than that point. But then if I take any other point in between the two, right, its height, you know, because its height is a little bit less than the MLE, we know that it's going to be slightly less well supported, and so that it'll be slightly less than 8 times better supported. Okay. But what's interesting, right? If you were to take now, remember this is 1/8 right here. Take this point right here, right? Okay. That value of lambda, right? Its value is less than 1/8. So when we were to compare it to the MLE, it would be worse than 8 times better support. The MLE would be better than 8 times supported than that point. Okay, so any other point in this range, right? You cannot find a point that's more than 8 times better supported, right? Every point outside of that range, you can find a point that's more than 8 times better supported. So these collection of points right here, these collection of lambda values right here, are exactly the points such that there is no other point that is more than 8 times better supported, if we draw that line at 1/8. Of course, this is all predicated at having normalized the likelihood with the MLE at 1. And this line right here, all of the points of lambda that fall within this interval, right, because it's 1/16th, are the points such that there is no point that is more than 16 times better supported, okay? And that's kind of useful, right? Because you can do these experiments. So where do I get 8 and 16? So 8 is 2 cubed and 16 is 2 to the 4th. I get those because if you do these coin flipping experiments where comparing the likelihood of whether a coin is two-headed versus the likelihood of the coin being fair, you find that kind of intuitively people start switching. If they get 3 consecutive heads, they start saying, oh, that coin appears to be fair, unfair, to the tune of being two-headed. And at about 4 consecutive coin flips, they're quite certain that the coin is unfair. So, I consider these kind of like moderate and sort of strong evidence in favor of the points within these line. So just to reiterate, if you take this interval, it's kind of like these are basically the likelihood equivalent of a confidence interval. And so if you take all of these points, there is no such point that is more than 8 times better supported given the data and the model. If you take a point outside of it, say this point, we know at least one point, namely the MLE, that's more than 8 times better supported. So those are little so-called likelihood intervals. And you might say, well, wait, the 1/8 is kind of arbitrary, but it's no more or less arbitrary than, say, constructing a 95% confidence interval. What you really want to give people is the full plot, because it conveys all of the relevant information. The only problem with likelihood is if you have multiple parameters, like in a regression setting, then you have to figure out how to do something that displays just the likelihood. But I wanted everyone to at least hear about the likelihood. The remainder of the class will be focusing more on kind of frequency style inference that does not show likelihood-based plots, but I wanted people to be aware of this style of inference. So there's a related idea, in fact, numerically equivalent idea of the so-called attained significance level. Our test statistic was 2 for h naught mu equal to 30 versus ha mu different from 30 when we said that n was 100. Okay? So here's our normalized test statistic distribution under the null. And our test statistic works out to be 2. And we said for a one-sided test that if we set alpha to be if we set alpha to be 5%, right? Then we got 1.645 there. We set that to be 5%. Our 2 was bigger than it, and we would reject the null hypothesis. What if it was 0.1%, right? That would be way out here, so that there was 0.1%, right? Then we would, if we set alpha to that level, we would fail to reject. So look at what would be the alpha level for which that you exactly achieve this balance, where if you pick if you were to have picked an alpha level larger than it, if you were to pick an alpha level larger than it, you would reject, and smaller than it, you would fail to reject. Well, I think you can see, if we picked up here, we're going to reject. If we picked down here, so that our alpha level is this guy, we would if we picked up here, we would fail to reject, and we picked up here, we would reject. So I think you can see if you were to move it so that the line exactly overlaps with your test statistic,
you would be exactly at that point, and then that alpha level would be the alpha level for which you fail to reject if the alpha level were smaller than it, and you reject if the alpha level were bigger than that. And that guy is called the attained significance level, kind of for obvious reasons. It's sort of saying, what's the smallest significance level I could choose and still reject? So you can see this is equivalent to the p-value, right? You can see that by moving these lines around until we get to that perfect alpha, that probability of being larger than our test statistic, well, that's also just the p-value. So it's philosophically different, but it's the same quantity. It's the same number. So anyway, there's a difference between there's a interpretation difference between the attained significance level and the p-value, but there's not a practical difference because they're the same number. One reason I like p-values is if someone gives you a p-value, then the reader or interpreter of your test can perform the hypothesis test at whatever alpha they like. If they reject if the p-value is smaller than alpha, and they fail to reject if the p-value is larger than alpha. Okay, so that's one reason why I like p-values, is because then the person can calibrate the test however they'd like. If you just tell them I rejected or I didn't reject, you haven't given them the same amount of information. For two-sided hypothesis tests, you double the smaller of the two one-sided p-values. Right? So, if your z distribution looks like this, and you got a test statistic right there, here's the p-value for that direction hypothesis test. Here's the p-value for that direction hypothesis test. You take that guy and double it, and that's your p-value. Okay, let's calculate a p-value not just for a normal example, which we've already done. Let's calculate a p-value for this binomial example. Your friend has 8 children, 7 of which are girls, none are twins. Of each gender has an independent 50% probability for each birth. What's the probability of getting 7 or more girls out of 8 births? That's a p-value. The probability of getting, if we're testing the hypothesis that h naught p equal to 0.5 versus ha p greater than 0.5, more evidence would be more of the children being girls, and so the probability of getting our observed amount was 7. The probability of getting 7 or more, right, is probability of 7, and then plus the probability of 8 works out to be about 4%. Okay, and then you could just do this with p-binomial. Remember, you have to do 6 because if you do lower tail equals false, it does strictly greater than, so it starts counting at 7 when you put in 6. But if we were to put in 7, it would start counting at 8. Let's do a Poisson example. Suppose that a hospital has an infection rate of 10 infections per 100 person days of risk, which is a rate of 10 over 100 or 0.1 during the last monitoring period. Assume that an infection rate of 5% is an important benchmark. Given the model, could the observed rate, I shouldn't say 5%, the given infection rate of 0.05 per day at risk is an important benchmark. So given the model, could the observed rate being larger than 0.05 be attributed to chance? That's what we want. That's what we want to test. So we want to test whether h naught lambda equal 0.05. So if lambda was 0.05, then lambda naught times 100 is 5, right? So if the rate is 0.05 per day, then the rate when monitored for 100 days should be 5. So we want to test HA lambda greater than 0.05 because we're interested in whether our infection rate is higher than this benchmark. So we would do our Poisson probability of getting 9 or more than 9 with a rate of 5. We do this again more than 9 because it calculates the probability was strictly greater than. So this will count 10, 11, 12, so on. Okay, and that gives us a probability of 3%. So we would, if it was a one-sided test, we would reject. If it was a two-sided test, you double it, right? You double the smaller of the two one-sided hypothesis tests. And so that gives you 3 different settings in which you can calculate p-values. We went over a normal p-value, which is pretty easy. We went over a binomial p-value, and then we went over a Poisson p-value. And in each case, we did the same thing. We specified our hypotheses. We calculated the probability of getting a test statistic as or more extreme than was actually observed, where this probability was calculated under the null hypothesis. That quantity is a p-value. You're going to reject if your p-value is smaller than your alpha level, and you're going to fail to reject if your p-value is larger than your alpha level. And then now that you know what a p-value is, you can go and read some of those references and see all the fighting about it.